What if everything we know about the universe is just a mere fragment of a reality far more expansive than our comprehension can grasp? Imagine a reality where our entire cosmos, with its countless stars, galaxies, and intricate laws, is simply one piece of a much grander puzzle, an ever-expanding tapestry of existence that stretches beyond the limits of our understanding. This thought-provoking notion invites us to explore the concept of multiverses, a mind-bending idea that suggests the existence of countless other realms, each potentially as diverse and astonishing as our own. As we delve deeper into the cosmic mysteries of dark matter and dark energy, we are confronted by the unseen forces that govern the very fabric of the universe. Forces that, despite their overwhelming influence, remain hidden from our direct perception. At the heart of these cosmic puzzles lies the fascinating theory of multiverses, often referred to as the multiverse. This idea has emerged from several groundbreaking theories in modern physics and cosmology. One of the most compelling ideas comes from quantum mechanics, a branch of physics that delves into the behavior of the smallest particles in existence. Quantum mechanics proposes that for every possible outcome of any given event, there exists a corresponding universe in which that outcome occurs. This implies that the universe we inhabit is not the sole reality, but one among an infinite array of parallel universes that constantly branch out, each representing a different possibility. In this view, the universe does not follow a single fixed timeline, but instead splinters into an infinite number of alternate realities, each unfolding its own unique course. Another influential theory that supports the idea of a multiverse is the inflationary model of the universe. This theory posits that after the Big Bang, the universe underwent a brief but explosive period of rapid expansion, a phase known as cosmic inflation. According to this model, certain regions of space stopped inflating, while others continued to expand at an exponential rate. This process could have given birth to what are known as pocket or bubble universes, distinct realms that coexist alongside our own. These universes could have vastly different physical laws, constants, and properties, potentially resulting in realities that we might struggle to even conceptualize. Imagine a universe where time behaves differently, where gravity is stronger or weaker, or where entirely new forms of matter exist. String theory adds another layer of intrigue to the multiverse hypothesis. According to string theory, the fundamental building blocks of all matter are not point-like particles, as once thought, but rather tiny, vibrating strings. These strings can vibrate in a multitude of ways, and each mode of vibration corresponds to a different particle. The theory also introduces the possibility of additional dimensions beyond the familiar 3 dimensions of space and 1 dimension of time. These extra dimensions could provide a way to explain how multiple universes might emerge from different configurations of strings and their interactions in various dimensions. In this framework, the multiverse is not merely a collection of parallel realities, but a dynamic, multi-dimensional web of universes, each with its own set of physical properties, timelines, and even forms of life. The anthropic principle, which suggests that we find ourselves in a universe capable of sustaining life, because such a universe is one of many, further supports the multiverse concept. This principle argues that the very conditions necessary for life, such as the precise balance of forces and constants in our universe, are not unique, but rather the result of an endless array of possibilities. In a multiverse where infinite universes exist with varying characteristics, it is not surprising that we would find ourselves in one that supports life as we know it. If there are indeed countless universes, some with vastly different properties, the mere fact that we exist in one capable of sustaining life is a statistical inevitability. These various theories, each grounded in different aspects of modern physics, all point toward the same tantalizing conclusion. Our universe may be just one thread in a rich, intricate fabric of realities. Each of these universes could be completely different from our own, governed by its own set of rules, laws of physics, and forms of existence. Together, they form a sprawling multiverse, an almost unimaginable vastness of reality that stretches far beyond the confines of our own experience. As we continue to explore the implications of these ideas, particularly through the lenses of string theory and quantum mechanics, we are forced to reconsider the very nature of existence itself. These theories suggest that our universe is not a solitary entity, but part of a grand cosmic orchestra, with each universe playing its own unique melody in the symphony of the multiverse. But what does this mean for our understanding of reality? What might these parallel universes look like? And how could they challenge our very perceptions of what is possible? When we begin to explore the potential differences between our universe and these alternate realities, we enter a realm of infinite possibilities. The fundamental laws of physics, for instance, might be completely different in other universes. In our universe, the interplay between gravity, electromagnetism, and the strong and weak nuclear forces creates the environment in which stars, planets, and galaxies can form. However, in another universe, the forces that govern the behavior of matter and energy might work in entirely unexpected ways. The speed of light could be different, or gravity might not even exist at all. In some universes, the very concept of time could be fluid, while in others, space itself might have a radically different structure. Moreover, the nature of life itself could vary dramatically across the multiverse. Just as we exist as complex life forms based on carbon chemistry, other universes might harbor entirely different kinds of life, perhaps built on silicon or even on elements we haven't yet discovered. The possibilities are as limitless as the multiverse itself. Perhaps in one universe, life is purely energy-based, existing in forms that are completely alien to us, with no physical bodies or tangible senses. In another universe, life might exist in a state of perpetual motion, never experiencing the stillness or stability that defines our experience of existence. As we push the boundaries of scientific exploration, the idea of the multiverse offers us a glimpse into a cosmic landscape far grander and more diverse than we ever thought possible. Whether or not these parallel universes truly exist remains an open question, one that continues to fascinate and puzzle physicists and cosmologists alike. But as our understanding of the fundamental forces of nature deepens, we may one day uncover the means to peer beyond the veil of our own universe and glimpse the countless other realms that exist just out of reach. Until then, the mystery of the multiverse remains one of the most profound and captivating frontiers of human knowledge, an enigma that invites us to reconsider our place in the cosmos and to imagine a reality that stretches far beyond the horizons of our own universe. However, in a parallel universe, things could be very different. The fundamental laws that govern our universe, laws that we understand as immutable, might not hold in another realm. For example, gravity, the force that keeps us grounded, could behave in entirely different ways. It could be weaker or stronger than what we experience, influencing the behavior of celestial bodies in unpredictable ways. This would dramatically change the formation of stars, planets, and galaxies. In such a universe, galaxies might not have formed at all, or they could have evolved in ways we can't even begin to imagine. The very fabric of the cosmos could be unrecognizable, governed by forces that we don't yet understand. Now, think about the initial conditions that shaped the development of our universe. In a parallel universe, these conditions could differ significantly, leading to the creation of entirely different elements or even different atomic structures. While carbon-based life is what we are familiar with here, in a parallel universe, life might be built on entirely different foundations. Perhaps life forms there would not rely on carbon at all, but on other elements or compounds that are yet to be discovered in our reality. These possibilities stretch the limits of our imagination and challenge everything we know about what life can be. And yet, even within a universe where the laws of physics remain similar to ours, small changes in events or conditions could lead to vastly different outcomes. Imagine a world where the dinosaurs never went extinct, where the cataclysmic asteroid that wiped them out 66 million years ago missed its mark, and the great reptiles continued to dominate the Earth. Or consider a world where humanity never evolved, perhaps due to a small shift in environmental conditions or evolutionary triggers. Every event, whether small or large, can set off a chain reaction, creating endless divergent realities. This highlights just how delicate the balance of history is, and how small changes can echo through time, shaping the future in ways that we may never fully grasp. These alternate universes would not only differ in their physical laws or the progression of life, but would also manifest their own social, cultural, and historical realities. Societies in these parallel universes could be shaped by technological advancements or challenges that are entirely foreign to us. The cultural and social fabric of these worlds would be different, influenced by their own set of circumstances. Perhaps one universe's civilization revolves around the mastery of a technology we can barely conceive, while another might be defined by entirely different values, beliefs, and social structures. The art, literature, and politics of these worlds could be completely distinct, offering a fascinating glimpse into what civilization might look like under different rules. Parallel universes, then, represent a playground for the imagination, a way to explore alternate realities that are shaped by the subtle and not-so-subtle interactions of physical laws, initial conditions, and historical events. These possibilities offer us a window into realities where the only limit is the scope of our imagination, where even the most profound aspects of existence are open to reinterpretation. The idea of a multiverse, where countless other universes exist alongside our own, pushes the boundaries of both science and philosophy. It is a concept that has emerged from theoretical physics and a range of curious observations, all of which point to the tantalizing possibility that the reality we know is just one tiny part of something far grander. One of the most compelling pieces of evidence for the multiverse comes from the study of cosmic microwave background radiation. This faint glow left over from the Big Bang holds clues about the early universe. Scientists have found that certain patterns within this radiation might suggest that our universe is interacting with others. These anomalies hint at the possibility that our universe is but one bubble in a vast cosmic sea, with other universes coexisting alongside it. The idea that our universe might be part of something much larger is not just a wild fantasy. It's a real scientific hypothesis based on observable data. The theory of cosmic inflation also supports the multiverse idea. According to inflationary theory, in the moments following the Big Bang, the universe underwent a rapid exponential expansion. Some scientists propose that this expansion could occur in different regions of space, simultaneously creating different universes with their own physical properties. If this is true, it would mean that our universe is just one of many bubbles, each with its own set of rules and conditions, floating in an endless cosmic expanse. This idea suggests that the universe we observe today is simply a product of our universe's specific history, and that there are countless others that have evolved in entirely different ways. The large-scale structure of the universe also provides hints that we may not be seeing the full picture. The arrangement of galaxies and the vast emptiness of cosmic voids are suggestive of underlying patterns that might extend beyond the observable universe. If certain regions of space behave in ways that can't be fully explained by our current understanding, they may be influenced by the presence of other universes. These interactions, while still speculative, provide tantalizing clues that our universe is not an isolated entity, but part of a larger, interconnected multiverse. In the realm of quantum mechanics, the many worlds interpretation provides another avenue for thinking about parallel universes. According to this interpretation, every quantum event, every time a particle behaves in a way that is not fully determined, creates multiple potential outcomes, each unfolding in a separate, branching reality. While these realities may not be exactly like our own, the idea that there could be numerous parallel versions of ourselves, each with different choices and outcomes, challenges our understanding of reality itself. This theory invites us to consider the possibility that the multiverse could consist of an almost infinite number of alternate timelines, each existing simultaneously. Although there is no direct evidence for the existence of other universes, the evidence we do have, ranging from cosmic radiation to the principles of quantum mechanics, suggests that the multiverse is a possibility that we must seriously entertain. Whether or not we can ever gather definitive proof, these ideas push us to expand the boundaries of our understanding and challenge our assumptions about the nature of reality. The multiverse concept, as fascinating as it is, goes beyond the realm of science and into the realm of imagination. Popular culture has embraced the idea of parallel universes, using it as a narrative tool to explore the what-ifs of existence. In movies, television series, and books, the multiverse serves as a backdrop for thrilling stories, where characters encounter alternate versions of themselves, experience radically different worlds, or face challenges that defy their understanding of reality. Comic books, for example, have long used the multiverse as a way to explore alternate versions of iconic superheroes and villains, creating complex storylines and character arcs that span multiple realities. These fictional portrayals allow us to ask deep philosophical questions about fate, free will, and choice. What if we had taken a different path in life? What if we made a different decision at a crucial moment? These questions are at the heart of multiverse stories, as they explore the endless possibilities that arise from each choice we make. The multiverse becomes a mirror reflecting the complex web of decisions that define our lives, as well as the broader mysteries of existence. For scientists, the multiverse remains a speculative and unproven concept, yet it is one that continues to captivate the imagination. With each new discovery in physics and cosmology, we inch closer to understanding the true nature of our universe, and perhaps the possibility that we are not alone in the cosmos. Meanwhile, in the realm of fiction, the multiverse offers a rich and diverse canvas for exploring human experience and emotion. The dialogue between science and fiction encourages us to consider what lies beyond the horizon of our known universe and to ponder the profound mysteries that remain just out of reach. This intersection between scientific inquiry and creative imagination is what makes the multiverse such a compelling concept. Whether as a framework for storytelling or a subject of rigorous research, the idea that our universe might be part of a vast multiverse invites us to explore the very nature of existence, to question our place in the cosmos, and to open our minds to the possibility of realities beyond our own. Dark matter and dark energy are two of the most enigmatic and fundamental components of our universe, each playing a vital role in its structure and evolution. Despite their immense influence, these phenomena remain largely invisible, undetectable by traditional means. Dark matter, which doesn't emit light or energy, cannot be observed directly with telescopes. Yet scientists know it exists because of its gravitational effects on visible matter, stars, galaxies, and clusters of galaxies. Without dark matter, the behavior of galaxies would be vastly different, and they wouldn't hold together the way they do. Similarly, dark energy, an even more mysterious force, is thought to be responsible for the accelerated expansion of the universe. While dark matter acts like a sort of cosmic glue, binding galaxies together, dark energy appears to be pushing everything apart, accelerating the rate at which the universe is expanding. Together, dark matter and dark energy account for about 95% of the universe's total energy content, leaving us with a universe that is mostly invisible to us, two vast and mysterious forces shaping the destiny of all that exists. Understanding dark matter and dark energy is one of the biggest challenges in modern physics, and solving these puzzles could unlock some of the deepest secrets of the cosmos. However, its presence becomes evident through the gravitational effects it exerts on visible matter, such as stars and galaxies. Imagine walking through a dimly lit room and hearing the faint sound of a shopping cart. Even though you can't see the cart, you notice the way it pushes items out of its path as it moves. In this analogy, dark matter acts as that unseen cart. You can't directly observe it, but its gravitational influence is unmistakable. This invisible force affects the motion of galaxies and clusters of galaxies, pulling them together, binding them in a delicate gravitational dance. It is this unseen presence that holds the structure of the universe in place, providing the necessary gravitational pull that prevents galaxies from flying apart. In fact, dark matter is believed to constitute a significant portion of the total mass of the universe. Estimates suggest that dark matter far outweighs the ordinary, visible matter that makes up the stars, planets, and everything we can observe directly. Ordinary matter, the matter we are familiar with, accounts for only a small fraction of the mass in the universe, while dark matter comprises roughly 85% of the mass in the cosmos. Yet, despite its abundance, dark matter remains an enigma, eluding our direct detection. On the other hand, dark energy, which is an even more baffling and mysterious force, plays a completely different role. While dark matter pulls objects together, dark energy pushes the universe apart, driving the accelerated expansion of space itself. If dark matter is the architect of cosmic structures, dark energy is the force behind the universe's stretching and expanding. Imagine blowing up a balloon. As more air is added, the balloon expands, its rubber stretching to accommodate the growing volume of air inside. In the same way, dark energy acts like an invisible force pushing galaxies farther apart. This expansion is not a simple stretching of space, but an accelerated process, one that has been taking place for billions of years. The exact nature of dark energy remains one of the greatest mysteries in modern physics. Though scientists are slowly piecing together clues, they have yet to uncover a comprehensive explanation for this elusive force. In fact, understanding dark energy and dark matter is vital for unraveling the complex history and future of the universe. They are not just abstract concepts, but the essential building blocks that shape the very fabric of reality. While dark matter draws galaxies and stars together, dark energy acts as a counterforce, pushing everything farther apart. Together, these two forces work in opposition to one another, creating the vast and dynamic universe we observe today. Detecting dark matter, however, remains one of the most challenging and elusive tasks in modern astrophysics. Unlike ordinary matter, dark matter does not emit, absorb, or reflect light, making it completely invisible to traditional telescopes. It interacts only through gravity and possibly other unknown forces, leaving scientists to explore indirect ways to infer its presence. Despite these challenges, astrophysicists have developed innovative methods to uncover dark matter's hidden secrets, using both groundbreaking technology and imaginative theoretical models. One of the primary methods to detect dark matter involves studying its gravitational influence on visible matter. This approach takes advantage of the way dark matter warps space-time with its gravitational pull, affecting the motion of stars and galaxies. For instance, by observing the movement of stars within galaxies or tracking the orbital patterns of galaxies within galaxy clusters, scientists can detect discrepancies between the observed motion and what would be expected based on visible matter alone. In some galaxies, the stars move so rapidly that, without the presence of dark matter, they should be flying apart. Yet they remain bound together. This discrepancy suggests the presence of an unseen mass, invisible but powerful enough to hold them in place. It's as if a puppeteer is controlling the movements of marionettes, but the strings, representing dark matter, are invisible, guiding the action from the shadows. Another method used by researchers to study dark matter is gravitational lensing, a phenomenon that occurs when light from distant objects is bent and distorted as it passes through the gravitational field of a massive object, like a galaxy or galaxy cluster that contains large amounts of dark matter. The bending of light causes the distant objects to appear warped or magnified, much like looking through a curved piece of glass. By carefully analyzing these distortions, scientists can map out the distribution of dark matter in the universe, detecting how it clumps and interacts with the surrounding visible matter. This technique provides an invaluable tool for revealing the hidden presence of dark matter and understanding its role in shaping the cosmos. Particle physics also offers a window into the world of dark matter. Scientists have constructed sensitive particle detectors that are often buried deep underground or placed in remote locations far from the noise of cosmic rays and other background radiation. These detectors are designed to be shielded from all forms of interference, allowing them to pick up the faintest traces of dark matter particles should they ever interact with regular matter. It's like trying to listen for the faintest whisper in a noisy room. Scientists are on the lookout for rare, subtle interactions that might signal the presence of dark matter. Though the search has been ongoing for decades, dark matter particles remain elusive, and detecting them directly remains one of the holy grails of modern physics. Finally, cosmological observations of the cosmic microwave background, CMB, provide further insights into the role of dark matter. The CMB is the faint radiation that permeates the universe, a remnant of the Big Bang itself. By studying the minute variations in this radiation, scientists can glean crucial information about the early stages of the universe. These small fluctuations can reveal how dark matter influenced the formation of galaxies and large-scale structures in the cosmos. Just as a fingerprint can provide clues to the identity of a suspect, The patterns left by dark matter in the CMB offer a unique glimpse into the early universe, allowing scientists to trace how dark matter contributed to the formation of the universe as we know it. Through these various methods, gravitational studies, lensing, particle detection, and cosmological observations, scientists are gradually piecing together the complex puzzle of dark matter. Each discovery brings us closer to a clearer understanding of its role in shaping the cosmos and reveals the hidden forces that govern the universe's behavior. At the same time, the search for dark energy, which remains an even greater mystery, continues. This invisible force is responsible for the accelerated expansion of the universe, yet its exact nature is still unknown. Some scientists believe it might be a property of space itself, while others speculate that it could be related to quantum field theories or even new forces of nature. Whatever the answer may be, the discovery of dark energy and its connection to dark matter will undoubtedly be one of the most groundbreaking revelations in the history of science. Together, dark matter and dark energy are among the most profound mysteries in modern physics. Understanding them is essential for completing the grand narrative of the universe, how it began, how it evolved, and where it is headed. As our tools and techniques improve, it seems inevitable that the veil surrounding these two enigmatic components will eventually be lifted. Until then, dark matter and dark energy will remain central to our understanding of the cosmos, shaping the future of astrophysical research and inspiring new questions that will drive scientific inquiry for generations to come. The universe is an incredibly complex and mysterious entity, with much of its makeup remaining unseen and unknown. A key part of this cosmic enigma lies in two fundamental forces that shape the very fabric of our existence: dark matter and dark energy. These unseen forces, despite their elusiveness, exert an undeniable influence on the universe's structure, evolution, and future. While dark matter is crucial in the formation and cohesion of galaxies, dark energy pushes the boundaries of our understanding by driving the accelerated expansion of the cosmos. Dark matter, though invisible and undetectable by traditional means, can be recognized through its gravitational effects on visible matter. Think of the universe as a vast whirlpool. The galaxies we can observe are like the water spiraling within it. The invisible, hidden part of the whirlpool, however, is the dark matter, which provides the necessary gravitational pull to keep everything from falling apart. Without dark matter, the gravitational forces of visible matter alone would be insufficient to hold galaxies together. The invisible mass of dark matter forms an intricate cosmic web, weaving throughout the universe, binding galaxies in a structure we cannot see, but one we are acutely aware of through its gravitational influence. However, while dark matter is responsible for the cohesion of cosmic structures, dark energy, in contrast, has an entirely different role. Dark energy is believed to be the force accelerating the expansion of the universe, pushing galaxies away from one another at an ever-increasing rate. Imagine blowing air into a balloon. Initially, the balloon inflates at a steady pace, but eventually, it starts expanding faster and faster. This is analogous to the effect of dark energy on the universe. It is causing the fabric of space itself to stretch, and rather than simply expanding, the universe is doing so at an accelerating rate. It is this mysterious force that stands in opposition to the gravitational pull of dark matter and visible matter, accelerating the disintegration of cosmic structures and driving the universe to grow faster with each passing moment. Together, dark matter and dark energy orchestrate a cosmic dance, with dark matter pulling galaxies and clusters of galaxies together, while dark energy pushes them apart. This intricate balance creates a paradox, one that challenges our understanding of the cosmos and leaves scientists with more questions than answers. How will these forces evolve? What will be the ultimate fate of the universe? The interplay between dark matter and dark energy not only shapes the current state of the universe, but will also dictate its future trajectory. As researchers continue to study these mysterious forces, we begin to entertain several possible scenarios for the universe's end. If dark energy continues to dominate, the universe could experience what scientists call the Big Freeze. In this scenario, galaxies will drift so far apart that stars will burn out, and the universe will ultimately reach a state of cold darkness with no energy left to sustain life or even the structure of matter. Alternatively, if dark matter outweighs dark energy, we might witness the Big Crunch, where the gravitational pull of dark matter overpowers the expansion, causing the universe to collapse inward upon itself, potentially leading to a dramatic implosion. Some theories even suggest a more violent fate known as the Big Rip, where dark energy grows so powerful that it begins tearing apart galaxies, stars, and even atoms themselves, unraveling the very fabric of the universe. These scenarios not only underscore the uncertainty surrounding the universe's fate, but also challenge our understanding of the laws of physics and the nature of reality itself. Dark matter and dark energy represent the unknown, forces so profound that they could shape the universe's destiny in ways we have yet to fully comprehend. Their presence compels us to look deeper into the nature of the cosmos, sparking both awe and existential questions about the origins of the universe and where it is ultimately headed. The implications of understanding dark matter and dark energy extend far beyond cosmology. As researchers unravel the mysteries of these elusive forces, they may uncover insights that drive technological advancements across various fields. Dark matter, which makes up a substantial portion of the universe's mass, could lead to breakthroughs in the development of highly sensitive detectors. These detectors could enhance our ability to observe faint cosmic phenomena, opening new possibilities in fields like astrophysics, security, and medical imaging. The search for dark energy's secrets might also inspire novel methods of energy generation and storage, offering solutions to some of humanity's most pressing energy challenges. Moreover, the pursuit of knowledge about dark matter and dark energy often leads to the creation of new tools, algorithms, and materials with applications that extend far beyond astrophysics. For instance, advancements in computational techniques used to analyze vast amounts of data from cosmic observations could also improve systems in artificial intelligence, big data analytics, and even machine learning. The technologies developed in the search for a deeper understanding of the universe's hidden forces have the potential to revolutionize various industries, sparking innovations that we cannot yet fully predict. As our understanding of dark matter and dark energy deepens, we move closer to uncovering not only the ultimate fate of the universe, but also unlocking the potential for technological breakthroughs that could transform life as we know it. The study of these cosmic forces is more than just an academic pursuit. It is a journey into the unknown that could change the way we understand reality, our place within it, and the very fabric of the universe itself. In the vast, seemingly infinite reaches of space, dark matter and dark energy remind us of how much there is still left to discover. The quest to unlock the secrets of the universe has long been a shared endeavor, fostering collaboration across disciplines. Scientists, engineers, and technology developers come together, each bringing unique expertise to the table. This multidisciplinary effort, born out of a mutual desire to understand the cosmos, drives breakthroughs that ripple through all areas of human endeavor. Often these advancements extend far beyond the realm of astrophysics, leading to revolutionary innovations in fields like medicine, communications, and even artificial intelligence, technologies that shape the future in ways we have yet to fully imagine. At the heart of this grand pursuit is the understanding of the universe's fundamental workings. The deeper we probe into the cosmos, the more we uncover the underlying principles of nature, which in turn fuel groundbreaking discoveries. These revelations do not just satisfy our intellectual curiosity, they serve as a catalyst for the development of technologies that redefine our relationship with the world around us. Indeed, by studying the universe, we not only expand the horizons of human knowledge, but we also open the door to entirely new possibilities for the future. The observable universe, which forms the foundation of this inquiry, is a concept that continues to fascinate astronomers and laypeople alike. It represents the portion of the universe that we can observe and study from our vantage point here on Earth. Bound by the limitations of the speed of light and the age of the cosmos, its boundaries are not fixed in space, but are shaped by the fundamental constraints of time and distance. The observable universe encompasses everything we can currently measure: galaxies, stars, nebulae, and cosmic structures that provide tantalizing clues about the origins and evolution of the cosmos. The boundary of the observable universe is defined by the maximum distance light has traveled since the dawn of time. With the universe estimated to be around 14 billion years old, this gives us a glimpse of objects roughly 14 billion light years away. However, due to the expansion of the universe, these distant objects are now much farther than that. The universe is not static, rather, it is expanding, causing galaxies to move away from one another over time. This phenomenon is akin to the stretching of the surface of a balloon as it inflates. As the balloon grows, points on its surface, representing galaxies, move away from each other. In the same way, the expansion of space itself causes light from distant galaxies to travel longer distances, meaning that the objects we observe are actually farther away than their light's travel time would suggest. To measure this vast expanse, astronomers employ a variety of techniques. One of the most important is the study of redshift, the stretching of light to longer, redder wavelengths as objects move away from us. By analyzing redshift, scientists can determine how fast galaxies are receding from us and map the scale of the universe with impressive accuracy. Additionally, the study of cosmic microwave background radiation, the faint afterglow of the Big Bang, provides another crucial tool. This radiation offers a snapshot of the universe in its earliest moments, allowing researchers to probe its initial conditions and better understand its evolution. The observable universe, then, is not just a static limit on our perceptions of space. It represents a dynamic, ever-expanding realm that holds within it a wealth of mysteries and unanswered questions. As light continues to travel across the vastness of space, we gain new insights into the cosmos. Yet this observable boundary also serves as a reminder of how much there is beyond our current reach. Vast regions of the universe that remain hidden from view, shrouded in the mists of space and time. One of the most captivating aspects of the observable universe is that it is not a fixed, unchanging entity. It is defined by the age of the universe and the speed of light, two factors that constrain what we can observe. But these limitations are not absolute. As time progresses and the universe continues to expand, new regions come into view. In essence, the observable universe is constantly growing, offering us an ever-expanding horizon to explore. This transformation of our cosmic view allows astronomers to refine their models of the universe's structure and its evolution, offering new insights into phenomena such as dark energy and dark matter, two of the most mysterious and elusive components of the cosmos. However, the observable universe is but a fraction of what may lie beyond. While the farthest reaches of our observational capacity remain shrouded in mystery, scientists have long speculated about the existence of an infinite expanse stretching far beyond our view. The universe, some theorists argue, may be infinitely large, extending in all directions beyond the observable boundary. In this vast unseen realm, the laws of physics could operate differently. Perhaps gravity behaves in ways we have not yet imagined, or the fundamental building blocks of matter differ from those we are familiar with. Some even propose the idea of a multiverse, a collection of multiple, distinct universes, each with its own set of physical laws. If this theory holds true, the universe we observe might be just one of many, each with its own unique properties and structures. Such theories challenge our understanding of existence itself, pushing the boundaries of imagination and inviting us to reconsider the very nature of reality. But even as we push the limits of our observational reach, we must contend with the fact that there may always be regions of space beyond our grasp. The expansion of the universe, coupled with the finite speed of light, means that some areas will forever remain beyond our ability to observe. Yet, these uncharted realms continue to fuel curiosity and wonder, inspiring scientists to develop new ideas and methods that might one day allow us to peer into the deepest corners of the cosmos. In our ongoing exploration of the universe, scientists have made significant strides in understanding its earliest moments. One of the most invaluable tools in this regard is cosmic microwave background radiation, which serves as a direct window into the conditions of the universe just moments after the Big Bang. This radiation, often referred to as the afterglow of the Big Bang, has been traveling through space for billions of years, carrying with it a wealth of information about the universe's early state. By studying this faint, ubiquitous radiation, astronomers can gain insights into the temperature and density of the universe in its infancy, shedding light on how the cosmos evolved from a hot, dense state into the vast expanse we observe today. The fluctuations in the temperature of the cosmic microwave background, though minuscule, provide vital clues about the universe's structure and composition. These variations can be compared to ripples on the surface of a pond, offering a glimpse into the density of matter in the early universe. By examining these fluctuations, scientists can reconstruct the universe's history, map the distribution of galaxies, and determine key factors such as the rate of cosmic expansion and the overall geometry of space itself. The study of this radiation is, in many ways, a journey back in time, allowing us to peer into the very beginnings of the cosmos and understand the forces that shaped its evolution. Through this ongoing investigation, we continue to expand our knowledge of the universe, constantly refining our understanding of its vastness, complexity, and the fundamental forces that govern it. Yet the further we look, the more questions arise about the nature of dark matter and dark energy, about the ultimate fate of the universe, and about the mysterious expanse that lies beyond the observable universe. As we continue to explore, one thing is certain. The more we uncover, the more we realize just how much there is left to discover. Cosmic microwave background radiation, often regarded as one of the most profound discoveries in modern astrophysics, serves as a crucial tool for understanding the universe's origins and its current structure. This faint, pervasive radiation is a relic from the early stages of the universe, providing us with a snapshot of a time just a few 100,000 years after the Big Bang. Through its study, scientists have been able to approximate the universe's age, which is estimated to be around 13 billion years. This timeline not only helps us comprehend the universe's overall age, but also offers a framework through which we can trace the evolution of various cosmic structures over eons. The cosmic microwave background, CMB, serves as an invaluable tool in probing some of the most enigmatic forces that shape the universe. One of these is dark energy, a mysterious phenomenon that is believed to be responsible for the accelerated expansion of the cosmos. By examining the subtle variations in the CMB, scientists are gaining critical insights into the nature of dark energy, a force whose properties remain largely elusive. The discovery of this radiation was pivotal in reshaping our understanding of the universe, particularly in challenging earlier notions that the universe was static and unchanging. Instead, it reinforced the now widely accepted theory that the universe is expanding, an idea that was once revolutionary. This radiation also tells us something profound about the boundaries of our universe. It suggests that the universe is not confined only to the observable regions, but that it extends far beyond what we can detect, veiled by the limits of current technology. These findings hint at a larger cosmic context, one that we are only beginning to fathom. The study of the CMB is not merely a look back into the past, but a crucial part of our ongoing quest to understand the universe's vastness and complexity. It is a vital tool that continues to reveal new dimensions of the cosmos, expanding our knowledge and pushing the boundaries of human understanding. In parallel to these advancements in cosmological studies, developments in telescope technology have revolutionized our ability to peer deeper into the universe. Imagine standing under a night sky, the vast expanse above you, filled with countless stars and galaxies, each point of light holding a story of the cosmos. Thanks to improved telescopic technologies, we are now able to uncover these secrets in ways that were once thought impossible. The primary key to this new frontier lies in the development of larger mirrors for telescopes, which allows them to collect significantly more light. The more light a telescope can gather, the fainter and more distant objects it can detect. This means we are now able to observe light that has traveled across billions of years, offering a direct glimpse into the early stages of cosmic history, a time when stars and galaxies were still taking shape. Alongside this, advancements in adaptive optics have greatly improved the clarity of images captured by telescopes. Earth's atmosphere, filled with turbulence, often blurs the images we receive from distant objects. With the advent of adaptive optics, telescopes can now continuously adjust to atmospheric distortions, allowing them to produce clearer, more precise images. These innovations help reveal fine details in far-off galaxies, nebulae, and other celestial phenomena, providing deeper insights into their composition, formation, and evolutionary history. This enhanced clarity also allows astronomers to better understand the intricate structures within these distant objects, deepening our understanding of the processes that govern the universe's vast expanse. Infrared technology has opened yet another new frontier in cosmic exploration. Many celestial objects, particularly those in the process of formation, are obscured by thick clouds of cosmic dust. Traditional telescopes, which rely on visible light, struggle to penetrate these clouds. However, infrared telescopes are capable of detecting heat emitted by these objects, unveiling star-forming regions and other hidden phenomena. This infrared vision allows us to observe parts of the universe that were previously invisible, offering a more comprehensive picture of the cosmos and its ongoing processes. These observations are vital for understanding the life cycle of stars and the formation of galaxies, as well as the conditions that lead to the creation of planetary systems. Space-based telescopes have taken our observations even further, eliminating the interference caused by Earth's atmosphere. By positioning telescopes beyond our planet, we gain access to a complete spectrum of electromagnetic radiation, including ultraviolet and X-rays. These wavelengths are absorbed by the atmosphere and would otherwise be inaccessible to ground-based telescopes. This ability to observe high-energy phenomena such as black holes, neutron stars, and supernovae provides us with crucial insights into some of the most extreme and dynamic processes in the universe. The clarity and breadth of these observations continue to expand our understanding of the universe's violent and ever-changing nature. In addition to these technological advancements, the rapid progress in data processing and analysis has had a transformative effect on our ability to interpret the vast amounts of data collected from telescopes. Powerful computers now enable researchers to conduct complex calculations and simulations, analyzing light from distant galaxies to determine their distances, motions, and roles within the larger cosmic web. These tools have allowed scientists to map the structure of the universe with unprecedented accuracy. As we refine these techniques and technologies, we continue to expand the boundaries of our knowledge, exploring the furthest reaches of the observable universe and uncovering the mysteries that lie beyond. Meanwhile, the discovery of exoplanets, planets orbiting stars outside our solar system, has added another fascinating chapter to our understanding of the cosmos. For centuries, the existence of such planets was purely speculative, but with the advent of modern observational techniques, these distant worlds have become a reality. Imagine looking up at a night sky filled with stars, each one potentially hosting its own planetary system. With each new discovery of an exoplanet, our perspective on the universe broadens, and we are confronted with the possibility that the cosmos is teeming with planets, some of which might harbor the conditions necessary for life. Various methods have been developed to detect these exoplanets, each with its own set of challenges. One of the most widely used techniques is the transit method, which involves monitoring the brightness of a star. When a planet passes in front of its host star, it causes a small but detectable dip in the star's light. These tiny fluctuations, though seemingly insignificant, can provide clear evidence of an exoplanet's presence. The challenge, however, lies in distinguishing these slight dips from other potential sources of variation, such as the star's own natural activity or even the limitations of our observational tools. Another widely used method is the radial velocity technique. When a planet orbits a star, its gravitational pull causes the star to wobble slightly, leading to a shift in the star's light spectrum. By analyzing these shifts, astronomers can infer the planet's mass and its distance from the star. While this method has proven highly effective, it comes with its own set of challenges, particularly in measuring the minuscule changes in the star's movement amidst the noise of the vast cosmos. Direct imaging is another exciting, albeit challenging, technique for observing exoplanets. This approach involves capturing actual photographs of the planets, which, due to the overwhelming brightness of their host stars, is akin to trying to spot a firefly next to a glaring light bulb. Advanced technology, such as specialized filters that block out the star's light, is required to make this possible. Despite its difficulty, direct imaging has provided stunning images of exoplanets, opening up new possibilities for studying their atmospheres and conditions in greater detail. As our technologies continue to evolve and our understanding of the universe deepens, the study of exoplanets offers an exciting glimpse into the potential for life beyond Earth. Whether through the discovery of Earth-like worlds or the study of more exotic planets with extreme environments, these distant worlds continue to fuel our curiosity and expand our knowledge of the vast, dynamic universe we inhabit. The exploration of exoplanets, planets located outside our solar system, has sparked an intellectual journey into the unknown, driven by humanity's insatiable curiosity about the cosmos. As technology has advanced, the discovery of these distant worlds has not only expanded our understanding of the universe, but also posed new questions about life beyond Earth. The pursuit of exoplanets has become a cornerstone of modern astronomy, guided by both determination and innovation. One of the most intricate aspects of studying exoplanets is analyzing their atmospheres. This task requires highly specialized instruments capable of detecting subtle chemical signatures in distant, often faint, starlight. By examining these atmospheric compositions, scientists can glean valuable information about the planet's environment and assess whether conditions might be conducive to supporting life. The challenge, however, lies in the precision of these instruments, which must endure the harsh conditions of space while maintaining the alignment necessary for exact measurements. Every technological breakthrough brings new possibilities, yet each one also introduces hurdles that must be carefully navigated. It is a delicate balance of progress and persistence as the search for exoplanets continues to push the boundaries of what is scientifically possible. New observatories, such as the advanced telescopes launched into space, represent the cutting edge of our ability to peer into distant star systems. These observatories aim to enhance our capacity to discover and study exoplanets, providing sharper, more accurate data than ever before. However, as the tools of exploration evolve, so do the complexities of ensuring their functionality. Instruments must be meticulously engineered to survive the extreme temperatures, radiation, and vacuum of space. Furthermore, their alignment and calibration are crucial to ensuring they capture the correct data. The constant advancements in this field are emblematic of human ingenuity and a relentless desire to uncover the mysteries of the universe. Among the most striking discoveries in exoplanet research are those that challenge our fundamental understanding of planetary formation and characteristics. The discovery of hot Jupiters, massive gas giants that orbit incredibly close to their stars, has defied the conventional models of planetary system creation. These planets, often larger than Jupiter, complete an orbit in a matter of days, experiencing temperatures that can melt metals. The proximity to their stars generates intense heat, which causes the gases in their atmospheres to expand and move at supersonic speeds, creating winds of extraordinary velocity. The conditions on these worlds are so extreme that they offer an entirely new perspective on planetary environments, raising intriguing questions about the processes that govern their formation. Another fascinating exoplanet discovery is WASP-16b, a world with an orbit that deviates dramatically from the circular paths that most planets follow. This exoplanet's orbit is highly elliptical, causing it to experience extreme variations in temperature and gravitational forces throughout its orbit. This eccentric behavior suggests the planet may have been subjected to significant forces in its past, possibly from interactions with other celestial bodies in its system. Such dynamics point to a turbulent and complex history, one that continues to intrigue astronomers seeking to understand how these distant worlds evolve. TARAS-2b, one of the darkest planets discovered, offers another compelling mystery. Its color is an almost complete absence of light, making it darker than coal. The planet absorbs more than 98% of the visible light that strikes it, a feature that makes it one of the least reflective objects known in the universe. This characteristic has opened new avenues for scientists to investigate the composition of its atmosphere, prompting them to consider what materials might cause such profound light absorption. This exoplanet, like many others, holds secrets that are yet to be fully understood, adding to the intrigue of distant worlds. Perhaps the most extreme case is that of LHS 3844b, a rocky world that orbits perilously close to its star. The surface temperature on this planet is so high that it is unlikely to harbor any form of life. Researchers speculate that LHS 3844b might resemble a barren, scorched version of Earth, with its surface constantly subjected to the intense heat of its parent star. Yet, even in its inhospitable state, this exoplanet offers valuable insights into the potential for rocky planets to form and evolve under extreme conditions, providing a critical piece in the puzzle of planetary diversity. In a similar vein, K2141b presents one of the most dramatic cases of an exoplanet subjected to extreme environmental conditions. This planet is thought to be entirely molten, with its surface covered by vast seas of lava. The extreme temperatures of K2141b create an ever-changing dynamic atmosphere, which could lead to violent climatic shifts. The discovery of such a planet invites a deep exploration of the limits of planetary habitability and provides a stark contrast to the more familiar, Earth-like worlds we often envision when thinking about the potential for extraterrestrial life. These extraordinary exoplanets underscore the immense diversity of planetary systems that exist beyond our solar system. Each discovery adds a new layer of understanding, challenging our preconceptions about how planets form and what characteristics make a world habitable. But the quest for exoplanets is not merely about discovering unusual worlds. It is also about understanding the conditions that could support life. The search for planets that might lie within the habitable zone, the region around a star where temperatures allow liquid water to exist, is central to the ongoing exploration. Water, as we know, is fundamental to life as we understand it, and its presence or absence can offer clues to the possibility of life on distant worlds. Once a potentially habitable exoplanet is identified, scientists move on to assessing its size and composition. Planets that are roughly the same size as Earth may have the potential to retain an atmosphere, which is crucial for sustaining life. Spectroscopy is one of the primary tools used to analyze the light passing through an exoplanet's atmosphere. This technique allows astronomers to identify the chemical makeup of the atmosphere, searching for signs of life, such as the presence of oxygen or methane, gases often associated with biological processes. These atmospheric analyses can reveal vital information about the conditions on the planet and whether they might support life. Atmospheric pressure is another critical factor in determining the habitability of an exoplanet. For life to thrive, the planet's atmosphere must maintain a pressure that allows water to exist in liquid form, not too thin, as on Mars, nor too thick, as on Venus, where the intense pressure would crush most forms of life. Geologic activity is also an essential consideration, as a dynamic planet with active volcanoes and shifting tectonic plates can help maintain a stable climate and recycle nutrients, both of which are necessary for sustaining life over long periods. As astronomers continue to refine their techniques and technologies, the search for exoplanets grows more sophisticated, offering a clearer picture of the vast, unexplored reaches of space. With every new discovery, humanity takes another step closer to understanding not just the nature of distant planets, but also the broader implications for life elsewhere in the universe. Each new exoplanet discovered represents a potential key to answering one of humanity's oldest and most profound questions. Are we alone in the cosmos? The study of exoplanets, the worlds that exist beyond our solar system, opens up a fascinating window into the universe, offering clues not only about how planetary systems form and evolve, but also about the potential for life elsewhere in the cosmos. Every time astronomers discover a new exoplanet, they embark on a journey of discovery that involves analyzing its size, composition, and orbital patterns. These critical data points provide a foundation for creating models that simulate the processes of planetary formation, allowing scientists to unravel how planets like these emerge from clouds of gas, dust, and ice orbiting a young star. However, the discovery of an exoplanet is just the beginning. Researchers are particularly focused on understanding the factors that contribute to a planet's habitability. Among the most crucial factors are the star's stability and brightness. A more stable star provides a consistent environment, which is essential for a climate that remains relatively unchanged over geological timescales. Such stability is conducive to the development of life, as it ensures a steady energy supply and relatively predictable environmental conditions. By studying these characteristics, scientists gain a multidimensional view of an exoplanet's potential to host life, ultimately refining our understanding of where life might exist beyond Earth. This evaluation process is not limited to the exoplanets themselves. The findings also provide invaluable insights into the dynamics of planetary systems in general. For example, astronomers have discovered gas giants, massive planets made primarily of hydrogen and helium, orbiting much closer to their stars than we see in our solar system. This configuration challenges previous assumptions about how planets form and the typical distances at which planets should reside from their host stars. It sparks further questions about planetary migration, where planets might have originated in colder regions of a system before being pulled inward toward their stars. Such discoveries help scientists better understand the arrangement of our own solar system. For instance, they offer a possible explanation for why gas giants like Jupiter and Saturn are located farther from the Sun, while the inner planets, Mercury, Venus, Earth, and Mars, are small and rocky. Additionally, by comparing the atmospheres of exoplanets to those of Earth, researchers are starting to build a clearer picture of what makes a planet truly habitable. These comparisons allow them to infer the environmental conditions that might support life, such as the presence of liquid water, stable temperatures, and protective atmospheric conditions. Studying exoplanets also leads to important revelations about the variety of planetary formation processes across the universe. It suggests that solar systems can form in a variety of ways, resulting in planetary systems that are distinct from our own. Our solar system may be just one example of many possible configurations, hinting at a rich tapestry of planetary evolution across the cosmos. This ongoing exploration of exoplanets not only broadens our knowledge of planetary systems, but also reveals much about the fundamental forces at play throughout the universe. As we look to the future, the potential for discovery is even greater. Upcoming missions to distant exoplanets promise to provide unprecedented insights into these alien worlds. Imagine spacecraft equipped with cutting-edge technology, designed to venture into deep space to explore planets located light years away from Earth. Each mission could uncover crucial information about the composition, atmosphere, and even the temperature of these distant worlds. One of the most exciting aspects of these missions is the ability to analyze light as it passes through a planet's atmosphere. This light carries a wealth of information about the gases present, offering clues about the planet's habitability and potential for supporting life. Robotic landers and rovers, advanced machines designed to traverse the surfaces of distant planets, will be instrumental in collecting samples and conducting experiments on site. These rovers could search for key resources such as water or essential minerals, which would revolutionize our understanding of what makes a planet capable of supporting life. Additionally, they could take high-resolution images of the planet's surface, revealing its landscapes, weather patterns, and seasonal changes. These visual observations would offer a unique perspective on how the planet functions and evolves over time, and provide valuable data for ongoing research into planetary formation and migration. In some future missions, scientists may even be able to collect samples from these exoplanets and return them to Earth. These samples would undergo detailed laboratory analysis, allowing researchers to investigate aspects of planetary chemistry and geology that current instruments in space are unable to fully explore. Through international collaboration and advancements in technology, these missions hold the potential to dramatically expand our understanding of the universe and the possibility of life beyond Earth. They may ultimately lead to groundbreaking discoveries that will reshape our perception of the cosmos. In a completely different realm of cosmic exploration, the mysteries of black holes captivate scientists and astronomers alike. These enigmatic objects, formed from the remnants of massive stars, represent some of the most extreme phenomena in the universe. The life cycle of a star that gives birth to a black hole begins with a massive star, often many times the size of our sun. In the star's core, nuclear fusion occurs, releasing energy that counteracts the immense gravitational force trying to collapse the star. This balance between the outward push of fusion energy and the inward pull of gravity keeps the star stable for a time. However, when the star exhausts its nuclear fuel, the balance tips. The core can no longer sustain the pressure of fusion, and gravity takes over, causing the core to collapse inward. The outer layers of the star may be expelled in a violent explosion called a supernova, one of the most powerful events in the universe. This explosion can briefly outshine entire galaxies. But after the outer material is ejected, the core remains, and if it is sufficiently massive, usually several times the mass of our Sun, the collapse continues unchecked. Eventually, the core becomes so dense that not even light can escape its gravitational grip, marking the birth of a black hole. A black hole is defined by a boundary called the event horizon, the point beyond which nothing can escape, not even light. This boundary represents a region where the laws of physics as we understand them begin to break down. Inside a black hole, the gravitational forces are so intense that they warp space and time, creating an environment that defies our conventional understanding of the universe. Black holes, especially supermassive ones, which are thought to reside at the centers of most large galaxies, play a crucial role in shaping the dynamics of their surroundings. Supermassive black holes exert an enormous gravitational influence on their host galaxies. They attract not only stars, but also vast amounts of gas, dust, and other cosmic matter. As this material spirals toward the black hole, it forms a rotating disk known as an accretion disk. Inside this disk, friction and intense pressure cause the release of immense amounts of energy, often producing brilliant emissions of light. The energy emitted can regulate the growth of the black hole and even create powerful jets of particles that shoot outward into space. These jets can interact with nearby gas, influencing the formation of new stars and altering the evolution of the galaxy itself. The study of black holes, particularly in the context of their role in the centers of galaxies, offers profound insights into the structure and behavior of the universe. These cosmic giants help to shape the environments around them, and by understanding how they function, we gain a deeper understanding of the forces that govern not just black holes, but entire galaxies and the universe as a whole. As our technology and methods for observing these mysterious objects continue to improve, the secrets of black holes will continue to unfold, enriching our understanding of the cosmos and our place within it. Supermassive black holes are thought to be central to the evolution of galaxies, influencing their development in ways that are both profound and far-reaching. These cosmic giants, which sit at the heart of many galaxies, possess immense gravitational power. This force is not merely passive. It actively interacts with the surrounding stars, gas, and dust, shaping the very structure and behavior of their host galaxies. During periods of high activity, particularly in phases when the black hole is consuming vast amounts of matter, the energy released can significantly alter the dynamics of the galaxy. It's believed that this energy can cause a ripple effect, impacting the movement of stars and gas clouds, potentially triggering bursts of new star formation, or conversely, depleting the materials needed to create new stars. One of the more intriguing scenarios occurs during a phase known as quasar activity, when a black hole is particularly energetic. The energy emitted during this phase can heat the surrounding gas to such extreme temperatures that it prevents new stars from forming. This process may even halt or significantly slow the evolution of galaxies, leaving them in a state of stagnation. The relationship between a supermassive black hole and its galaxy is far from simple. It's a dynamic and complex interplay between immense gravitational forces and the energetic feedback that the black hole produces. Over billions of years, these interactions can fundamentally shape the galaxy's evolution, causing it to either flourish or stagnate, depending on the black hole's behavior. As astronomers continue to delve deeper into this cosmic mystery, the excitement of discovery remains palpable. The study of supermassive black holes is not just about understanding these enigmatic objects themselves, but also about uncovering the fundamental processes that govern the evolution of galaxies across the universe. In recent years, groundbreaking achievements have dramatically advanced our understanding of these cosmic titans. Perhaps the most striking of these was the historic moment in 2019 when the Event Horizon Telescope, an array of radio observatories spanning the globe, captured the first ever image of a black hole's shadow. This iconic image revealed the supermassive black hole at the center of the galaxy M87, showing a dark circular region surrounded by a glowing ring of gas and dust. This breakthrough offered a never-before-seen glimpse into the mysterious forces at play around black holes, providing invaluable insights into their structure and behavior. Since that momentous achievement, scientists have been refining their techniques, improving both the quality and the precision of their observations. Enhanced data processing methods and more sophisticated algorithms have enabled researchers to create even clearer images of black holes and extract deeper, more accurate information about them. For example, astronomers can now study the motion of stars orbiting a black hole, using these observations to map the black hole's gravitational influence. This allows them to better estimate crucial properties such as its mass, spin, and the extent of its gravitational reach. Additionally, the development of gravitational wave detectors has opened up an entirely new avenue for studying black holes. When two black holes merge, they send ripples through the fabric of space-time, gravitational waves that can be detected here on Earth. By studying these waves, scientists can learn more about the properties of the black holes involved in the merger, offering another piece of the puzzle in the life cycle of these massive objects. In tandem with these observational advancements, theoretical developments have expanded our understanding of black holes under extreme conditions. For instance, researchers have been exploring the properties of rotating black holes, particularly the features of their event horizons. Some studies suggest that these black holes may allow for the extraction of energy in ways that could have revolutionary implications, perhaps even providing a new source of power for future generations. Such discoveries would not only deepen our understanding of black holes, but also challenge and refine the fundamental laws that govern matter and energy in the universe. Each new discovery about black holes raises fresh questions, pushing scientists further into the depths of this cosmic enigma. As technology continues to advance at an ever-accelerating pace, we are on the cusp of even more extraordinary revelations about black holes. The merging of different observational methods from imaging to gravitational wave detection is likely to yield a more comprehensive understanding of these enigmatic objects. This cross-disciplinary approach may refine existing models and potentially lead to the development of entirely new theories of physics. The ongoing quest to understand black holes underscores not just their mysterious nature, but also their crucial role in the broader narrative of the universe's evolution. Every breakthrough brings us closer to answering long-standing questions while simultaneously opening the door to new mysteries. One of the most perplexing questions in the study of black holes is the so-called information paradox. This paradox arises from a fundamental conflict between general relativity and quantum mechanics. According to general relativity, anything that falls into a black hole, whether it's matter or information, disappears from the observable universe. This would seem to violate a basic tenet of quantum mechanics, which posits that information cannot be destroyed. To help illustrate this paradox, imagine throwing a book into a fire. The book's physical material might be destroyed, but the information contained within it, the knowledge, the story, should not simply vanish. Yet, in the case of black holes, it seems that information is lost forever once it crosses the event horizon. This dilemma has sparked intense debate and led to a variety of potential solutions. One prominent theory involves the concept of holography, which suggests that all the information that falls into a black hole might actually be encoded on its event horizon. In this framework, even though objects and matter are drawn into the black hole, their information might remain imprinted on the two-dimensional surface of the event horizon, rather than being lost to the depths of the black hole. This would drastically change our understanding of how space and information interact, suggesting that the three-dimensional world we experience could be encoded in two-dimensional surfaces, such as the event horizon of a black hole. Another possible resolution to the information paradox comes from the concept of Hawking radiation, named after physicist Stephen Hawking. Hawking radiation proposes that black holes slowly lose mass over time by emitting radiation due to quantum mechanical effects at their event horizons. This radiation is thought to carry away information as the black hole gradually evaporates. If true, it might mean that information is not truly lost after all, but rather it is preserved in the radiation emitted by the black hole. This raises fascinating questions about the nature of information and the behavior of black holes on cosmological timescales. The ongoing exploration of the black hole information paradox has significant implications for the future of physics. It is pushing the boundaries of both quantum mechanics and general relativity, leading to the emergence of new theories such as quantum gravity. These ideas aim to reconcile the contradictory aspects of the two theories, offering the potential for groundbreaking insights into the fundamental nature of reality itself. While no definitive solution has been found, the research continues to challenge our understanding of the universe, suggesting that the path to solving these mysteries may lie in unifying quantum mechanics and gravity into a single framework. Another captivating concept that has captured the imagination of both scientists and the public alike is the idea of black holes acting as portals to other regions of the universe, or even to entirely different universes. While this concept is more commonly associated with science fiction, it's rooted in real theoretical physics. Black holes, as we understand them, are regions in space where gravity is so intense that not even light can escape. This point of no return, known as the event horizon, marks the boundary beyond which nothing can escape the black hole's grip. Some theorists have proposed that black holes might not just be one-way gateways to oblivion, but could, in certain models, be connected to other parts of the universe through wormholes. Imagine a black hole as a tunnel, with an entrance in one part of space and an exit in another, perhaps light years away, or even in an entirely different universe. This idea, while speculative, presents an exciting possibility for future exploration, one that challenges the very fabric of our understanding of space, time, and the limits of the universe. However, this remains purely theoretical, and many questions about how such wormholes might function, or whether they even exist, remain unanswered. Yet, the study of black holes is far from just a theoretical pursuit. It has real, tangible consequences for our understanding of the cosmos. With each discovery, we are slowly but surely unraveling the mysteries of these incredible objects. What we learn not only brings us closer to understanding the life cycles of the universe's most mysterious inhabitants, but also pushes the boundaries of what we know about the fundamental forces that shape all matter and energy. The quest to understand black holes is more than just a journey through space. It's a voyage into the deepest questions about the nature of reality itself. However, it's important to acknowledge that the stability of such cosmic structures is highly questionable. The concept of a wormhole, while an enticing idea in both science fiction and theoretical physics, presents enormous challenges when it comes to its practicality as a stable and reliable portal. For a wormhole to function as a usable passage between distant regions of space, it would need to remain open and stable enough to allow matter, whether that be a spacecraft, a probe, or even a human being, to traverse it. Yet, the forces at work near objects like black holes make this task seem almost impossible. The gravitational forces near a black hole are so immense and extreme that anything attempting to enter would be crushed into oblivion long before it could even reach the singularity at the center. Additionally, the very theoretical constructs of wormholes often demand the presence of exotic matter, substances that possess negative energy density, to keep them open. The existence of such matter is not only speculative, but has never been observed or confirmed by any experiment or observation. This lack of confirmation casts further doubt on the possibility of creating or stabilizing a wormhole for practical use. Moreover, the fundamental laws of physics, as we currently understand them, impose severe limitations on what could occur inside a black hole, adding to the mystery and danger. In theory, anything that crosses the event horizon, the boundary around a black hole beyond which nothing can escape, not even light, would be irresistibly pulled into the singularity, a point of infinite density where space and time cease to behave in ways we can comprehend. At this point, our understanding of the universe breaks down entirely. What happens inside a black hole is unknown, and it remains one of the most enigmatic questions in science. The journey through such a celestial object is thus not a clear passage to new realms, but rather a treacherous and unknowable journey, filled with catastrophic potential. Despite the tantalizing allure of black holes and their portrayal in popular media as cosmic gateways to distant galaxies, the reality of these objects is far less inviting. Current scientific evidence leaves us with the understanding that, for now, black holes are far more likely to be one-way trips, with no safe return. They remain enigmatic, their true nature shrouded in mystery, and perhaps more dangerous than we ever anticipated. The dream of traveling through such cosmic gateways, while fascinating, challenges our very comprehension of space and time. It is a notion that, at present, remains purely theoretical, a tantalizing concept that will require significant breakthroughs in physics before it can even begin to be considered a viable reality. Now, turning our attention to quasars and galaxies, these celestial wonders play a pivotal role in shaping our understanding of the cosmos. Quasars, in particular, act as incredible beacons of light from the distant past, allowing us to peer into the earliest epochs of the universe. These incredibly bright and energetic objects are powered by supermassive black holes at the centers of young galaxies. As vast clouds of gas and dust spiral inward toward these black holes, they are heated to extreme temperatures, emitting enormous amounts of radiation in the process. This radiation is so intense that it can outshine entire galaxies. What makes quasars so fascinating is that when we observe them, we are effectively looking back in time. The light emitted by these objects can take billions of years to reach us, meaning that when we observe a quasar, we are seeing it as it appeared during a period when the universe was still young, just a few billion years after the Big Bang. In essence, quasars are like cosmic time capsules, offering us a glimpse into the early stages of the universe's development. Through their light, astronomers are able to study the conditions that existed in the universe long before the formation of stars and galaxies as we know them. Quasars also provide invaluable clues about the growth and evolution of supermassive black holes. Their existence suggests that these black holes formed and grew rapidly during the early universe. By examining how the light emitted by quasars changes as it travels across vast distances, scientists can extract critical information about the density and composition of the universe during its infancy. This is accomplished by analyzing the spectra of quasar light, which reveals the chemical elements and compounds that were present at the time. Such studies help scientists trace the processes through which stars and galaxies formed, and in turn, how the universe itself transitioned from a hot, dense state to the expansive cosmos we observe today. Moreover, quasars also serve as markers in the broader structure of the universe. Their immense brightness allows them to act as beacons, helping astronomers map the distribution of matter in space. The light emitted by quasars can also illuminate the surrounding cosmic environment, providing valuable insights into the processes of cosmic inflation and the expansion of the universe. In this way, quasars are not just fascinating objects of study. They are crucial tools that help astrophysicists piece together the history of the cosmos, from its earliest moments to the present day. Shifting our focus to galaxies, these colossal collections of stars, gas, dust, and dark matter are the building blocks of the universe. Galaxies come in various shapes and sizes, with the three primary categories being spiral, elliptical, and irregular galaxies. Each type has its own unique characteristics that define its structure, composition, and behavior within the vastness of space. Spiral galaxies are perhaps the most visually striking, with their distinct winding arms that extend outward from a central bulge resembling the shape of a pinwheel. These arms are typically rich in gas and dust, and they are the sites of active star formation, making these galaxies bright and full of life. Our own Milky Way is a classic example of a spiral galaxy. At its center lies a dense bulge of older stars, while the galaxy's flat disk shape extends outward, surrounded by a halo of dark matter. The presence of these well-defined spiral structures is one of the key features that distinguishes spiral galaxies from other types. Elliptical galaxies, on the other hand, lack the well-defined spiral arms that characterize their counterparts. They tend to have a more rounded, oval shape, and can vary greatly in size. These galaxies are typically composed of older stars and contain much less gas and dust, which means that they are not as likely to host the formation of new stars. As a result, elliptical galaxies tend to have a more uniform, dimmer appearance compared to the vibrant, active spiral galaxies. The degree of ellipticity in these galaxies can vary widely, with some being nearly spherical and others highly elongated, reflecting a diverse range of structures within this category. Finally, there are irregular galaxies, which do not fit neatly into the categories of spiral or elliptical. These galaxies are often chaotic in appearance, with no defined shape or structure. Irregular galaxies can arise from various processes, such as gravitational interactions with other galaxies, which may distort their shape and prevent them from developing a more organized structure. Together, quasars and galaxies provide a window into the workings of the universe, from the earliest stages of its formation to the present day. Through the study of these fascinating objects, we continue to uncover the mysteries of space and time, striving to understand not only the distant past, but also the future trajectory of the cosmos itself. Irregular galaxies stand as a striking anomaly in the cosmic landscape, evading simple classification. Unlike their more familiar counterparts, such as spiral or elliptical galaxies, they are not bound by the constraints of symmetry or predictable structure. Instead, they appear as chaotic assemblages of stars, often lacking the well-defined shapes that typify other galaxy types. These galaxies can be likened to cosmic puzzles, their pieces scattered and seemingly unorganized. The unique and unpredictable nature of irregular galaxies suggests that their formation and evolution defy the standard models applied to more structured galaxies. One of the most defining features of irregular galaxies is their active star formation. Within their hazy structures, vast clouds of gas and dust swirl together, fueling the creation of new stars, often young and hot. This process is far from dormant, making irregular galaxies hotspots for stellar birth. Unlike elliptical galaxies, which are typically older and feature mostly ancient stars, or spiral galaxies, which have a steady pace of star formation within their arms, irregular galaxies are dynamic and continually evolving. The presence of vast amounts of gas and dust acts as the raw material for this ongoing stellar nursery. The chaotic nature of irregular galaxies is not without cause. Many of these galaxies have been shaped by powerful forces such as gravitational interactions, collisions, or even mergers with other galaxies. These encounters, often violent and sudden, can dramatically alter a galaxy's structure, leading to the formation of irregular shapes. The interactions between galaxies can stir up vast clouds of gas and dust, creating a fertile environment for new stars to form. In a sense, these galactic collisions and mergers can be seen as cosmic catalysts, sparking activity that would otherwise not occur in more isolated systems. As astronomers delve deeper into the study of galaxies, the classification system they use becomes more than just a way of organizing the universe. It is a window into the history and evolution of the cosmos itself. Each galaxy, whether spiral, elliptical, or irregular, has a story to tell, one shaped by its unique characteristics, interactions, and environmental influences. Through the lens of these classifications, scientists can piece together the broader narrative of how galaxies form, evolve, and interact across time and space. This story is one of constant change, shaped by both the internal dynamics of galaxies and the broader forces that govern the universe. The journey of galaxy formation and evolution begins, as with most cosmic tales, with the Big Bang. This momentous event, approximately 13.8 billion years ago, marked the birth of the universe in a violent explosion of energy. In the aftermath, the universe was a hot, dense soup of particles, with temperatures high enough to prevent the formation of stable atoms. However, as the universe expanded and cooled, gravity began to take hold. Regions of slightly higher density, clumps of matter, began to attract more particles, growing larger over time. This process, driven by the relentless force of gravity, ultimately led to the creation of the first stars and galaxies. One of the leading theories about galaxy formation is the bottom-up model. According to this theory, smaller structures, proto-galaxies, gradually merged over time, growing larger and more complex. Imagine a snowstorm where individual snowflakes slowly come together to form a snowman. In the cosmic context, these tiny proto-galaxies collided and merged, creating larger galaxies with more intricate structures. Over billions of years, this process of merging has played a crucial role in the diverse populations of galaxies we observe today. It is through these cosmic collisions that galaxies evolve, becoming more complex and diverse as they grow. Dark matter, an invisible and mysterious substance, also plays an essential role in galaxy formation. Though dark matter cannot be seen directly, its influence is far-reaching. It makes up approximately 27% of the universe's total mass, and its presence is felt through its gravitational effects. Dark matter creates vast gravitational wells, pulling ordinary matter into them. This interaction provides the conditions necessary for stars to form. Without dark matter, galaxies would not have the mass needed to sustain their structures, and the intricate dance between visible and invisible matter would not be possible. Within this framework of galaxy evolution, two major galaxy types emerge: spiral and elliptical. Spiral galaxies, like our Milky Way, are often dynamic, with rotating disks where new stars are constantly being formed. Their spiral arms, rich with young stars, gas, and dust, are the birthplaces of the universe's stellar populations. In contrast, elliptical galaxies are more mature. They consist primarily of older stars with little new star formation occurring. Many elliptical galaxies have undergone extensive mergers, which have led to the smoothing out of their shapes. Over time, these galaxies have shed much of the gas and dust that would otherwise fuel star creation, leaving behind a stellar population that is, for the most part, ancient. Recent advancements in observational technology and simulations of the early universe have provided scientists with a new understanding of the factors that influence galaxy evolution. It has become clear that the environment in which a galaxy resides plays a significant role in shaping its characteristics. Galaxies in crowded regions of space, such as galaxy clusters, may experience frequent interactions with their neighbors, leading to changes in their shape, like star formation rates and even the loss of gas and dust. In contrast, galaxies that are more isolated tend to evolve along different pathways, often exhibiting distinctive features not seen in their more crowded counterparts. One of the more intriguing theories to emerge in recent years is the idea that galaxies may experience periodic bursts of star formation, known as starbursts. These bursts of activity can be triggered by interactions with neighboring galaxies, like gravitational disturbances or the collapse of gas clouds within the galaxy itself. During a starburst, a galaxy can form new stars at an accelerated rate, dramatically altering its appearance and structure. These bursts of activity can also result in the formation of massive stars, some of which may eventually explode in supernova, enriching the surrounding environment with heavy elements. This process is a vital part of the cosmic cycle, as the remnants of supernovae provide the raw materials for the next generation of stars, planets, and possibly even life. As we look deeper into space, our understanding of these processes continues to evolve. Each new discovery brings us closer to unraveling the mysteries of galaxy formation and evolution. The universe is a dynamic, ever-changing place, where galaxies are constantly forming, merging, and evolving. Through the study of these celestial giants, we gain insight into the forces that shape the cosmos over vast timescales. The ongoing quest to understand the birth and evolution of galaxies promises to reveal even more about the history of the universe and our place within it. At the heart of this cosmic drama lie galaxy collisions. When two galaxies draw near each other, their gravitational forces begin to interact, triggering a chain of events that can alter the galaxy's structures. These interactions can lead to the distortion of the galaxy's shapes, the formation of new structures like spiral arms, and the merging of stars and gas. Imagine two clouds of gas and stars colliding. This collision produces tidal forces that stretch and pull at both galaxies, sometimes resulting in dramatic changes in their appearance. As a result of these interactions, immense amounts of gas are compressed, sparking a surge in star formation. This process, known as a starburst, can lead to the creation of stars at a rate far greater than what is seen in isolated galaxies. The birth of new stars in these chaotic environments is often accompanied by the violent deaths of some of them. Massive stars may end their lives in brilliant supernova explosions, sending shockwaves through the galaxy and enriching the surrounding space with heavier elements. This cosmic recycling is crucial as it ensures that the materials formed in one generation of stars are recycled into future generations. The very elements that make up planets and even life itself are born from the deaths of stars. This continual cycle of birth, death, and rebirth drives the evolution of galaxies, ensuring that the cosmic tapestry remains ever-changing, vibrant, and full of potential. When galaxies collide, the outcome is far from a simple merger. Instead, their gravitational forces set off a complex chain reaction, triggering the dynamic movement of stars and other cosmic matter. Some stars may be violently ejected from the galaxy, flung into the vast, empty expanse of intergalactic space. Others, however, are not so fortunate. They become trapped by the gravitational pull of the newly formed galactic core, dragged into new orbits, some spiraling dangerously close to the heart of the merging galaxy. These stellar interactions give rise to an intricate mix of stellar populations, each galaxy now bearing a unique fingerprint of its cosmic history. This process does not merely reshape individual galaxies, it also affects their long-term evolution, steering them down entirely new paths as they evolve over billions of years. The effects of these galactic collisions extend far beyond the galaxies themselves, influencing the structure of the universe on an enormous scale. As galaxies collide and merge, they group together into large clusters, which in turn form superclusters, vast assemblages of galaxies held together by gravity. These superclusters are not isolated islands. They contribute to the creation of cosmic filaments, the immense web-like structures that stretch across the universe, made of galaxies and dark matter. Over millions of years, these processes combine to mold the universe into the complex, vast arrangement we observe today. It's not just a simple collision of celestial bodies. These events are foundational forces shaping the very fabric of the universe. Understanding these galactic collisions offers a window into the universe's evolutionary processes, showing us that the cosmos is far from static. It's a living, breathing entity, one constantly shifting and reshaping, driven by the powerful forces of gravity, dark matter, and cosmic expansion. These events are not just the violent explosions of stars and galaxies. They are integral to the ongoing story of the universe, revealing a dynamic and ever-changing cosmic home. By studying ancient galaxies, we gain access to a cosmic time machine, a tool that allows us to peer back into the early universe, shedding light on the conditions that prevailed shortly after the Big Bang. This monumental event, which occurred around 13.8 billion years ago, marked the birth of the universe as we know it. As light from these distant galaxies travels vast distances, it carries valuable information about the chemical composition and structure of the early universe. By examining the light from these galaxies, scientists can uncover the types of elements that existed at the time, providing a glimpse into the universe's infancy. If a galaxy contains predominantly hydrogen and helium, it points to a very young cosmos, one in which heavier elements had yet to form. These elements, forged in the fiery cores of stars and released into space through supernovae, would later be the building blocks for new generations of stars, planets, and even life itself. Exploring the formation and evolution of these ancient galaxies is essential for understanding how the large-scale structure of the universe took shape. By studying how galaxies cluster together and interact with one another, we can begin to explain why larger galaxies tend to dominate the night sky, while smaller ones often linger in their shadows. This research also provides valuable insights into the role of gravity and dark matter in shaping the universe. It pieces together a detailed narrative of cosmic evolution, showing how forces we still don't fully understand helped give rise to the structure we observe today. Additionally, the study of ancient galaxies helps unravel the mysteries of dark energy, the enigmatic force driving the accelerated expansion of the universe. By comparing the brightness and distances of these distant galaxies, astronomers can infer how the rate of expansion has changed over cosmic time. Each new discovery about these ancient galaxies helps to refine our understanding of the universe's most fundamental forces and elements, offering clues about both its past and its future. Every piece of knowledge gleaned from these galaxies adds another layer to the complex puzzle that tells the story of our cosmic origins and the path the universe may take in the eons to come. Turning to cosmic phenomena like gamma-ray bursts, we encounter some of the most energetic events in the universe, capable of releasing vast amounts of energy in the form of gamma rays, the highest energy form of light known to science. Imagine a flash of light brighter than 1 billion suns, exploding outward in a fraction of a second. These gamma-ray bursts occur in the aftermath of two main types of cataclysmic events: the collapse of massive stars and the collision of neutron stars. Both events are violent deaths for the stars involved, but they also serve as cosmic milestones, marking the birth of black holes and offering a glimpse into the violent, energetic nature of the universe. The importance of studying gamma-ray bursts goes beyond their sheer power. These phenomena can reveal a wealth of information about the life cycles of stars, the processes that lead to their death, and the conditions that trigger such catastrophic events. Moreover, because gamma-ray bursts can travel across vast stretches of space, their light serves as a kind of time capsule, providing us with a look into the early universe. The light from these bursts can journey across billions of years to reach us, allowing astronomers to peer into the distant past, learning about the conditions that existed long before galaxies took their current forms. With each detection of a gamma-ray burst, scientists open a new door to discovery, gaining fresh insights into the extreme behavior of matter and energy. This in turn helps to advance our understanding of fundamental physics, making gamma-ray bursts a critical focus in astrophysics research. Cosmic rays, high-energy particles that streak through the universe, also play a vital role in shaping our understanding of the cosmos. These tiny messengers from the depths of space continuously bombard Earth, carrying with them information about distant regions of the universe. When cosmic rays reach our planet, they collide with atoms in Earth's atmosphere, sparking a cascade of secondary particles, including neutrons and muons. These secondary particles can penetrate deep into the Earth's surface, leaving behind traces of their journey. The Earth's atmosphere acts as a protective barrier, shielding life on the surface from the most harmful effects of these particles. However, this constant bombardment is not just a one-way street. Cosmic rays are also an important factor for space exploration, as they pose a challenge to astronauts and spacecraft traveling beyond Earth's protective atmosphere. Understanding the behavior and impact of cosmic rays is crucial for preparing future missions to distant planets and beyond. These rays not only shed light on the nature of the universe, but also remind us of the ever-present challenges posed by the harsh, unpredictable environment of space. In sum, the study of cosmic phenomena, whether it be the explosive force of gamma-ray bursts, the bombardment of cosmic rays, or the formation of galaxies through violent collisions, reveals the complexity and beauty of the universe. Each discovery builds upon the last, expanding our knowledge of the cosmos and bringing us one step closer to understanding the forces that shape our existence. Cosmic rays, though a minuscule fraction of the particles that reach the surface of Earth, have a profound ability to influence the biological processes that unfold beneath our feet. As they penetrate the atmosphere and reach the ground, these high-energy particles can interact with living organisms in ways that we are still discovering. Some studies suggest that cosmic rays might play an unseen role in the evolution of life on Earth, particularly in the way they can induce mutations in DNA. These changes, while largely neutral or harmful, are the raw material for biological variation and, over time, can contribute to the gradual evolution of species. A small subset of these mutations may even be beneficial, conferring some sort of advantage that drives evolutionary processes forward. This microscopic influence is a reminder that the forces of the universe, even those invisible to the naked eye, are always at work in shaping life on Earth. Yet, while their role in life's evolution may be seen as a subtle, hidden force, cosmic rays reveal their more overt and daunting nature when we look towards space exploration. Astronauts, traveling beyond Earth's protective magnetic shield, find themselves in a perilous zone where exposure to cosmic radiation is dramatically increased. Without the protection of Earth's atmosphere, these rays bombard space travelers, significantly raising their risk of cancer. But the dangers don't stop there. The central nervous system is also vulnerable to this radiation, and long-term exposure can lead to cognitive impairments, making the risks to human health in space particularly alarming. Engineers and scientists face the monumental task of mitigating these risks. Designing spacecraft that provide sufficient shielding from this invisible radiation is no small feat. The health and safety of astronauts on long-duration missions, such as those to Mars, rely heavily on this protection. A failure to adequately address the risks posed by cosmic radiation could jeopardize the very possibility of human exploration beyond our home planet. Ensuring that astronauts have the proper safeguards against cosmic rays is therefore critical, not just for their well-being, but for the future of space exploration as a whole. Cosmic rays are but one example of the myriad of complex phenomena that challenge our understanding of the universe. These particles are part of a broader, often mind-bending realm of cosmic events that push the limits of our current scientific knowledge. In fact, some of the most extreme and perplexing events in the universe occur when the densest objects we know collide. Take, for example, the merger of two neutron stars. These stars are the remnants of massive supernova explosions, each one compacted into an extraordinarily dense state. When two such stars collide, the energy released is unimaginable, creating gravitational waves that ripple through the very fabric of space-time itself. These waves, detected by observatories like LIGO, reveal the immense power of the universe and provide clues into the behaviors of matter and energy in these extreme environments. The event is not just a fleeting moment. The collision also produces bursts of light in various wavelengths, from gamma rays to X-rays, offering us a glimpse into the complex processes at play. Still, despite our growing understanding, these collisions challenge our theoretical models and continue to be an area of active research. What do these events tell us about the fundamental nature of matter, energy, and the very structure of space-time? Another remarkable cosmic event that fuels scientific inquiry is the gamma-ray burst. These bursts, though brief, are the most powerful explosions known to humanity, releasing more energy in mere seconds than the sun will over the course of its entire lifetime. Yet, despite their intensity, the mechanisms driving such colossal energy releases remain a mystery. Our current understanding of stellar evolution and high-energy astrophysics is stretched to its limits when confronted with these bursts, which seem to defy all previous predictions about how stars behave at the ends of their lives. The search for answers continues to push the boundaries of physics, forcing us to rethink the very foundations of the universe. And then there are black holes, perhaps the most enigmatic objects in the universe. These regions of space-time, so dense that not even light can escape their gravitational pull, have long captured the imagination of scientists and laypeople alike. But black holes are more than just mysterious. They are paradoxes that defy our understanding of physics. In particular, supermassive black holes, which reside at the centers of galaxies, exhibit behaviors that seem to contradict everything we know about gravity and quantum mechanics. As if their very existence weren't puzzling enough, these black holes appear to interact with surrounding matter in ways that we are only beginning to comprehend. The way they pull in material from their environment, the jets of energy they expel, and the way they warp space-time itself continue to provoke questions. One such puzzle comes from the concept of Hawking radiation, proposed by Stephen Hawking. According to this theory, black holes could slowly lose mass and energy over time, eventually evaporating. This presents an intriguing dilemma. If black holes can lose mass and energy, what happens to the information that falls into them? The information paradox is one of the most debated topics in modern physics, and solving it could revolutionize our understanding of both black holes and quantum mechanics. Thus, the universe presents us with an unceasing array of phenomena that challenge our knowledge and imagination. From the cosmic rays that subtly shape life on Earth, to the explosive events that tear through the very fabric of space-time, these forces remind us of how much there still is to learn. The questions they raise are not just about the physical processes that govern the universe, but also about the fundamental nature of existence itself. Each discovery, no matter how small, brings us a step closer to understanding the vast and mysterious cosmos in which we reside. The mysteries of dark matter and dark energy are radically transforming our understanding of the universe. Despite accounting for the majority of the cosmos, these phenomena remain largely invisible to our most advanced instruments, leaving behind only indirect evidence. This absence of direct observation has given rise to a wide array of competing theories and models, often challenging the fundamental laws of physics as we know them. Among the most intriguing clues is the puzzling behavior of galaxies. Observations show that galaxies rotate in ways that suggest the presence of vast, unseen masses, forces that, though invisible, seem to dictate how these galaxies behave. This discovery has profound implications for our conception of gravity, forcing scientists to reconsider the very laws that govern not just the formation of galaxies, but the entire universe. The rotation of galaxies doesn't quite fit with the predictions of classical physics. As a result, the need for new theories has never been more pressing, theories that can explain the complex, hidden forces shaping the cosmos. Each new finding invites a reevaluation of our scientific principles, pushing the boundaries of our knowledge and inspiring new frameworks that could unlock the secrets of the universe. As we venture deeper into the cosmos, our ability to observe and understand these strange phenomena grows ever more sophisticated. One of the most groundbreaking tools in this quest is the study of gravitational waves. These ripples in space-time are created by some of the most violent and energetic events in the universe, such as the collisions of black holes or neutron stars. When these massive cosmic objects collide, they generate waves that propagate outward at the speed of light, in much the same way that ripples spread across a pond when a stone is thrown into it. Gravitational waves are incredibly difficult to detect, but modern technology has made it possible. Using highly sensitive detectors placed in various parts of the world, including in the United States and Italy, scientists can observe even the most minute distortions in space caused by these waves. These detectors measure shifts that are smaller than the width of a single proton, which means they are capturing incredibly subtle signals from deep within the fabric of space-time itself. This remarkable precision allows us to observe phenomena that are completely invisible to conventional telescopes or other forms of measurement. As gravitational waves travel across space and reach Earth, they carry with them valuable information about their origins. By analyzing the properties of these waves, scientists can infer a range of details about the cosmic events that created them, everything from the masses of the colliding objects to their distance from Earth, and even the properties of the medium through which the waves passed. This level of insight allows researchers to piece together a more detailed history of the universe, providing crucial data about the fundamental physics at play during these extreme cosmic events. Gravitational waves have become a new frontier in cosmic exploration, providing us with a unique way to peer into the most extreme and energetic corners of the universe. They enable us to test and refine our understanding of gravity, offer fresh perspectives on the formation of black holes and neutron stars, and help to unravel the mysteries of space-time itself. By listening to the subtle vibrations of the cosmos, we are uncovering secrets that could reshape our view of the universe and its origins. Another enigmatic phenomenon that has captivated the attention of astronomers and physicists alike is the mysterious fast radio burst, or FRB. These bursts of intense radio waves last only milliseconds, but are so powerful that they release as much energy in that fleeting moment as the sun does over the course of many years. Despite their immense energy, the exact sources of FRBs remain elusive, and their unpredictable nature has made them one of the most fascinating puzzles in modern astrophysics. One of the defining features of FRBs is their transient and erratic behavior. Unlike many other cosmic signals, they don't follow a regular pattern, making it difficult for scientists to detect them multiple times from the same location. Most FRBs are observed only once, and the lack of repetition has left researchers with little to go on in terms of identifying their precise origins. Numerous hypotheses have been proposed to explain these bursts, with one leading theory suggesting that they may originate from supernova, stellar explosions that occur when a star reaches the end of its life and collapses in on itself. Other theories point to highly magnetized neutron stars, known as magnetars. These extraordinary stars have intense magnetic fields that can release bursts of energy during periods of stellar activity. The powerful magnetic fields surrounding these stars may whip the surrounding environment, creating high-energy emissions that could be detected as fast radio bursts. Despite the potential explanations, some have even speculated that FRBs might originate from more exotic sources, such as advanced extraterrestrial civilizations or alien technology. While this idea is fascinating and certainly fuels the imagination, there is at present no concrete evidence to support it. The truth about fast radio bursts could be more complex than we can currently comprehend. They might arise from a variety of cosmic scenarios, and ongoing research is dedicated to uncovering their true origins. Understanding these enigmatic signals is not just about solving a cosmic mystery. It also has profound implications for our broader understanding of the universe, including the behavior of matter under extreme conditions and the vast distances that radio waves must travel across space. Each discovery brings us closer to answering these fundamental questions and reveals more about the intricate workings of the cosmos. As we look outward, we also gain a deeper appreciation for the vast and complex architecture of the universe itself. The cosmic web, an enormous and intricate structure that spans the entire universe, provides a framework for understanding how galaxies and other cosmic entities are interconnected. Imagine a vast network spun from delicate strands, where each point in this web represents a galaxy, and the threads connecting them form an intricate lattice-like structure. These threads are made of dark matter, an invisible substance that exerts a gravitational influence, shaping the large-scale structure of the universe. The cosmic web is far from random. It is organized in a highly structured way, with distinct nodes, filaments, and voids. Nodes are regions that are densely populated with galaxies, creating massive clusters that act as hubs within this cosmic network. These clusters are interconnected by filaments, long, narrow strands that stretch across space, often containing galaxies and vast clouds of intergalactic gas. In contrast, voids are vast expanses of nearly empty space, where very few galaxies can be found. These voids create a striking contrast to the densely packed clusters, offering a striking visual and conceptual representation of the universe's grand design. The structure of the cosmic web is far more than a simple map of where galaxies are located. It provides insight into the forces and processes that govern the universe's evolution. From the distribution of dark matter to the formation of galaxy clusters, the cosmic web serves as a blueprint for understanding the large-scale structure of the universe. By studying the web's intricate patterns, scientists can gain a deeper understanding of how galaxies form and evolve, how matter interacts across vast distances, and how the invisible forces of dark matter shape the cosmos. Each new discovery about this grand cosmic architecture brings us one step closer to unlocking the universe's most profound mysteries. The cosmic web, a vast and intricate structure that governs the arrangement of galaxies, dark matter, and gas across the universe, has been shaping the cosmos since shortly after the Big Bang. It's a formation so fundamental that it represents the skeleton upon which the entire universe rests. To truly understand the magnitude of this creation, we need to trace its origins, where the very forces of gravity and the distribution of matter worked hand in hand to form an awe-inspiring, interconnected web of cosmic proportions. In the aftermath of the Big Bang, the universe was almost uniformly spread out with slight variations in density, minute fluctuations that would go on to have monumental consequences. These fluctuations acted as seeds, small disturbances in the fabric of the universe, which gravity would later nurture. Over billions of years, the gravitational pull of these regions began to gather matter together, much like a web drawing in particles from all directions. As matter clumped and collapsed under its own weight, larger structures emerged. These were the first seeds of the cosmic web, stretching across unimaginable distances. This process was slow, deliberate, and powered by the invisible force of gravity. The formation of the cosmic web wasn't just a simple accumulation of matter. It was a series of complex interactions between galaxies, gas, and an unseen player, dark matter. At first glance, the universe may have seemed empty, but the gravitational influence of dark matter was everywhere. dictating the flow of ordinary matter. The denser regions where matter congregated became the nodes of this web, the hubs where galaxies gathered to form clusters and superclusters, much like busy intersections on a vast network of cosmic highways. These nodes, connected by long, thin filaments of gas and dark matter, created an immense lattice that tied the entire structure together. The filaments, the very threads that connect clusters and superclusters, are not mere lines in space. They represent the conduit through which matter flows across the universe. Stretching out over billions of light years, these filaments form the very backbone of the cosmic web. They are born from the remnants of gas and dark matter, elongated into these narrow, tenuous structures that carry matter from one galaxy cluster to the next. Think of them as roads that carry travelers across an expansive and sprawling land, bridging the seemingly distant regions of space. Between these filaments and clusters lie the vast, nearly empty voids, areas where galaxies are few and far between. These voids, while seemingly barren, are as much a part of the cosmic web as the dense clusters themselves. They represent the spaces between the gravitationally bound structures, the silent gaps in the universe's otherwise full and thriving tapestry. Yet, even in their emptiness, voids are essential to the web's structure, balancing the clusters with their absence of matter and providing the universe with its expansive nature. The cosmic web's continual evolution is governed by a constant interplay between two forces, gravity and the expansion of the universe. Gravity relentlessly pulls matter together, while the expansion of space stretches everything apart. It's this delicate balance, this tug-of-war, that drives the growth and reshaping of the web. As the universe expands, matter is drawn into the filaments, continuing the slow but persistent evolution of the structure. At the heart of this intricate formation is dark matter, the invisible force that shapes everything in the universe. Despite being undetectable by conventional means, dark matter's influence is undeniable. It exerts a gravitational pull that directs the movement of visible matter, guiding galaxies to cluster together and form larger structures. Think of dark matter as an unseen hand, controlling the dance of galaxies, drawing them into a cosmic rhythm that governs the universe's structure. It is this invisible scaffolding that makes the cosmic web possible, providing a foundation for galaxies to group together and form the dense knots of the web. Dark matter's influence goes far beyond just the initial shaping of galaxies. It plays a role in the ongoing evolution of the cosmic web. The dark matter halos that surround galaxy clusters not only provide stability, but also guide the interactions between galaxies from their formation to the violent collisions that shape their future. These halos are like invisible roadways, leading galaxies along a predetermined path and influencing their ultimate fate within the grand scheme of the universe. While dark matter remains a mystery, its true nature still eluding scientists, it is clear that it has an undeniable presence. It is the silent architect of the universe, its invisible hand shaping the structure of everything from individual galaxies to massive superclusters. The cosmic web stands as a testament to dark matter's importance, showing how much of the universe's architecture is influenced by forces we can't directly see, but can observe through their profound effects on the visible universe. To study the cosmic web and its components, astronomers employ a variety of advanced techniques, using tools that allow them to peer deeper into the cosmos. Telescopes that observe different wavelengths of light, from radio waves to infrared, offer a rich array of data about the location and movement of galaxies, allowing scientists to construct detailed maps of the universe. By cataloging the locations of galaxies across vast expanses of space, astronomers can create three-dimensional maps that reveal the structure of the cosmic web in incredible detail. But it's not just observational data that reveals the true nature of the cosmic web. Computer simulations, grounded in the laws of physics and modeled after the conditions following the Big Bang, play an essential role. These simulations help scientists visualize how matter evolved over billions of years, from the earliest moments after the Big Bang to the present-day universe. By comparing simulations with real observations, astronomers can refine their understanding of the cosmic web's growth and evolution, making predictions about its future trajectory. Another method astronomers use to study the cosmic web involves analyzing light from distant galaxies and quasars. As this light travels through the web, it interacts with the matter along the way, altering its path and properties. This interaction, known as gravitational lensing, provides key insights into the distribution of dark matter. By studying these distortions in light, scientists can map the unseen presence of dark matter, identifying its location and influence throughout the universe. Spectroscopy, which breaks light into its component wavelengths, also allows researchers to study the composition and motion of cosmic objects. By examining how galaxies move within the web, as well as how materials flow through the filaments and voids, scientists can piece together the intricate mechanics of the cosmic web, revealing how galaxies and matter evolve in the vast expanse of space. In the end, the cosmic web is not just a collection of galaxies scattered across the universe. It's a living, evolving structure, intricately connected by dark matter, gas, and gravity. It reveals how the universe's architecture came to be and continues to change, offering us profound insights into the forces that shape our reality. Through the cosmic web, we are given a glimpse into the deep, interconnected nature of the cosmos, a vast network that holds the key to understanding the universe's past, present, and future. Sky surveys, conducted by multiple observatories working in tandem, are among the most essential tools in modern astronomy. These expansive efforts compile enormous amounts of data across vast sections of the sky. By pooling information from a range of telescopes, astronomers are able to piece together a more cohesive picture of the universe, enhancing our understanding of the cosmic web, the complex, interconnected structure that underpins the cosmos. This collaboration across different observatories allows researchers to fill in the gaps and correct the inconsistencies that might arise when using a single observatory's data. Together, these concerted efforts not only provide insight into the vast expanse of space, but also help us understand the distribution of galaxies, the forces that govern their motion, and the origins of the structures that dominate the universe. At the heart of the cosmic web lies an intricate network of galaxies, galaxy clusters, and other celestial objects. To visualize the cosmic web, imagine it as a three-dimensional map of the universe, like a vast tapestry woven from strands of dark matter and gas. The threads of this tapestry represent these filaments, vast stretches of dark matter and gas that extend across enormous distances. The knots, on the other hand, are the dense regions where matter has congregated, creating gravitational focal points. These knots are the locations where galaxies are most densely packed, forming massive clusters. Rather than being randomly scattered, galaxies are organized along these cosmic filaments, drawn together by the invisible hand of gravity. As gravity pulls them into these regions, galaxies align and congregate in a manner that reflects the underlying structure of the universe itself. Dark matter plays a pivotal role in this system, even though it remains invisible to the naked eye. Its presence is inferred through its gravitational effects, which can be observed as it shapes the motion of galaxies. Dark matter provides the structural backbone of the cosmic web, offering a framework in which normal visible matter can accumulate to form galaxies. As galaxies move along these filaments, their interactions become part of the dynamic evolution of the universe. Collisions and mergers between galaxies lead to the creation of new celestial formations, while also redistributing matter, such as gas and stars, further altering the cosmic landscape. In essence, the cosmic web serves as the universe's highway system, providing a structure for the movement and evolution of celestial bodies. It not only links distant galaxies and clusters, but also governs their behavior, shaping the universe over billions of years. This network of galaxies and dark matter weaves everything together, demonstrating that the cosmos is an intricate, interconnected system where everything, whether a small star or a massive galaxy cluster, affects everything else. In parallel with this celestial network, the search for extraterrestrial life stands as one of the most compelling questions in modern science. Researchers are pursuing this inquiry through multiple avenues, driven by the field of astrobiology, which investigates the origin, evolution, and potential for life beyond Earth. A central part of this search involves the use of cutting-edge telescopes that monitor exoplanets, planets orbiting stars outside our solar system. These instruments gather light from distant stars, detecting subtle dimming that occurs when a planet transits in front of its host star. This allows scientists to identify exoplanets in what is known as the habitable zone, a region around a star where conditions are potentially suitable for life, especially where liquid water could exist. Beyond telescopes, space missions have played a critical role in advancing our search for life. Rovers and landers sent to planets and moons within our solar system, such as Mars and Europa, are equipped with sophisticated instruments designed to search for signs of life. These machines analyze soil samples, rock formations, and atmospheric composition, looking for chemical markers or organic molecules that suggest the presence of life or favorable conditions for life. One of the most exciting aspects of this research is the ability to detect microbial life forms, or the conditions that might support them, deep within the surface of planets and moons that were once considered too inhospitable. Extreme environments on Earth also offer key insights into the possibility of life elsewhere in the universe. Scientists have turned to ecosystems like hydrothermal vents on the ocean floor and acidic lakes to explore how life can thrive under extreme conditions. These environments, where organisms live without sunlight and under intense pressure or high acidity, provide a model for how life might exist in similarly harsh conditions on other planets or moons. This research broadens our understanding of the potential locations where life could exist beyond Earth. In addition to searching for life within our own solar system, researchers are also investigating meteorites that have fallen to Earth. These space rocks may contain organic compounds or even microscopic life forms from other parts of the solar system. Such studies, which are part of planetary protection research, help scientists understand the potential for life to transfer between planets, an idea known as panspermia. This research could one day inform our search for life on planets far beyond our reach, offering clues about how life could have spread throughout the cosmos. Another crucial facet of the search for extraterrestrial intelligence involves the use of radio telescopes to scan the skies for signals that might indicate the presence of advanced civilizations. Scientists listen for patterns or anomalies in the cosmic radio frequencies that could suggest deliberate communication. These efforts, though still in their early stages, represent humanity's attempt to reach out and listen to the cosmos for any signs of intelligent life beyond our own planet. One of the foundational concepts in this search is the idea of habitable zones, also known as the Goldilocks zone. These are regions around stars where the temperature is just right for liquid water to exist on a planet's surface. Too close to the star, and the planet will be too hot for water to remain liquid. Too far away, and the water will freeze. In the Goldilocks zone, however, conditions are ideal for sustaining life as we understand it. Scientists assess not only the distance from the star, but also the type of star itself. Larger stars burn through their fuel too quickly to support life over long periods, while smaller stars may not provide enough heat. Medium-sized, stable stars like our Sun are considered the most likely hosts for habitable planets. The planet's atmosphere is another crucial factor in determining whether a planet falls within a habitable zone. An atmosphere acts as a shield against harmful radiation from the star and helps regulate the planet's temperature, creating a stable environment for life to develop. A thick atmosphere can trap heat, preventing it from escaping into space and creating a warm, hospitable climate. These factors, the star's characteristics, the planet's location, and its atmosphere, combine to define the potential for life, making habitable zones a key focus of the search for alien life. Together, these efforts form a diverse toolkit for exploring the possibility of life beyond Earth, each method adding a piece to the puzzle. Whether through telescopes, space missions, the study of extreme life on Earth, or the search for intelligent signals from distant civilizations, the quest for extraterrestrial life is a pursuit that captures the imagination and drives the scientific community forward. Each discovery, each piece of new data, brings us one step closer to answering the ultimate question: are we alone in the universe? Furthermore, the intricate and dynamic processes that govern a planet's environment can play a pivotal role in fostering the conditions necessary for life. These processes are not limited to a planet's geological activity, but extend to its magnetic field and even the presence of a natural satellite, such as a moon. Each of these factors works together to stabilize and regulate the planet's climate, atmosphere, and surface conditions. The geological activity of a planet, for instance, can result in the continuous cycling of elements essential for life, such as carbon and nitrogen, through various environmental systems. Similarly, a planet's magnetic field serves as a protective shield against harmful solar and cosmic radiation, preserving the atmosphere and creating a more hospitable environment. A moon, on the other hand, can play a significant role in stabilizing the planet's axial tilt, ensuring that the planet's climate remains relatively steady over long periods. Scientists combining these numerous elements have developed sophisticated models to simulate a variety of environmental scenarios. These models help researchers pinpoint potential locations in the cosmos where the conditions for habitability might exist. By taking into account a planet's distance from its star, its atmospheric composition, and its geological and magnetic characteristics, researchers can identify what are called habitable zones. These are regions in space where life as we know it might be able to flourish. As research into these factors advances, our criteria for what constitutes a habitable environment will likely evolve, expanding our understanding of where life could potentially thrive beyond the confines of our home planet. When we turn our attention to the search for extraterrestrial life, several locations in the universe stand out as particularly promising. These places are characterized by unique features that might make them capable of supporting life, as we understand it. Among the most intriguing of these locations is Europa, one of Jupiter's largest moons. Beneath its thick icy surface lies a vast subsurface ocean of liquid water. This ocean, which is believed to be in contact with a rocky seafloor, could provide the necessary conditions for life to take root, similar to the deep-sea ecosystems found on Earth. The potential for life here is further heightened by the fact that Europa experiences tidal heating, a phenomenon caused by the gravitational interaction with Jupiter. This heating process could provide the energy needed to sustain microbial life beneath its icy shell. Enceladus, another moon of Saturn, is also an exciting candidate in the search for life beyond Earth. Like Europa, Enceladus harbors a subsurface ocean, but what sets it apart is the presence of geysers that shoot water vapor into space. These geysers, discovered in 2005, are rich in organic compounds, which suggest the possibility of chemical reactions necessary to support life. The plumes of water vapor and the compounds within them have prompted scientists to propose that microbial life could be thriving beneath the icy crust of Enceladus. The exploration of these plumes, using spacecraft like the Cassini probe, could yield significant clues about the possibility of life elsewhere in our solar system. Mars, often regarded as the most Earth-like planet in the solar system, has long been a focus of exploration. The surface of Mars bears striking evidence of a once water-rich environment. Ancient riverbeds, dry lake beds, and minerals that form in the presence of water all point to the fact that Mars may have once harbored conditions suitable for life. While the planet is cold and arid today with a thin atmosphere, scientists believe that microbial life may have once flourished on its surface. There is also a possibility that life could still exist underground, where it would be shielded from the harsh radiation of the Martian surface. Current missions like NASA's Perseverance rover are analyzing soil and atmospheric samples for any signs of past or present life, as scientists continue to search for microbial fossils or other life indicators. As we look beyond our solar system, exoplanets, planets that orbit stars outside our sun's influence, are rapidly becoming central to the search for extraterrestrial life. These exoplanets, particularly those located within the habitable zone of their respective stars, offer a tantalizing glimpse of other potential Earth-like worlds. The habitable zone is the region around a star where the conditions are just right for liquid water to exist, considered one of the key ingredients for life. One exoplanet that has garnered significant attention is Proxima Centauri b, which orbits the closest star to our solar system, Proxima Centauri. This planet is similar in size to Earth and resides within its star's habitable zone, making it a prime target for future observation. Another exciting star system in the search for habitable worlds is TRAPPIST-1, a star system located about 40 light-years away. This system contains 7 Earth-sized exoplanets, 3 of which are located in the habitable zone of their parent star. The discovery of such a system with multiple Earth-like planets presents a unique opportunity to study the varying conditions that might support life. Each of these planets could offer distinct environments, with some possibly possessing water and the key elements necessary for life, making them prime candidates for further exploration. Each of these locations, Europa, Enceladus, Mars, Proxima Centauri b, and the TRAPPIST-1 system, offers a distinct set of conditions that could potentially harbor life. They are at the forefront of humanity's quest to answer the age-old question, are we alone in the universe? As technology continues to advance, our ability to explore these distant worlds grows exponentially. The launch of more advanced telescopes, robotic spacecraft, and future missions to distant exoplanets will bring us closer to discovering whether life exists beyond our Earth. This pursuit of knowledge is driven not only by the desire to find life, but also by the hope that one day we might encounter our cosmic neighbors. The search for extraterrestrial intelligence, SETI, a field of study dedicated to detecting signs of intelligent life beyond Earth, has evolved considerably over the years. What began as a speculative idea, grounded in centuries of scientific thought and philosophical musings about the existence of intelligent beings in the cosmos, has transformed into a practical endeavor with real-world applications. In the mid-20th century, with the advent of radio technology, the search for extraterrestrial intelligence took on a more concrete form. The possibility of using radio telescopes to scan for signals from alien civilizations became a real focus of study. One of the earliest and most significant projects in the search for extraterrestrial intelligence was Project Ozma, conducted in the early 1960s. Researchers used a radio telescope to scan nearby stars for unusual signals, hoping to detect transmissions sent deliberately by intelligent alien civilizations. While Project Ozma yielded no conclusive results, it marked an important milestone in the development of SETI as a scientific discipline. The project laid the foundation for future efforts and established a systematic approach to searching for extraterrestrial signals. As technology improved, so too did the capabilities of SETI. More powerful telescopes and advanced computer algorithms allowed researchers to analyze vast amounts of cosmic data. The establishment of a global network of observatories further enhanced our ability to monitor the skies continuously, expanding the scope of the search. By the 1970s and 1980s, the concept of narrow bandwidth signals gained prominence. Scientists hypothesized that such signals, which are distinct from the natural cosmic background noise, might indicate intentional communication from an extraterrestrial civilization. Over the decades, SETI efforts expanded beyond merely passive listening. Private organizations like the SETI Institute began to secure funding and galvanize public interest, leading to collaborative initiatives that aim to scan a broader range of frequencies and search for signals from solar systems far beyond our own. The discovery of exoplanets in the 1990s added a new dimension to the search for extraterrestrial intelligence. These planets, located in the habitable zones of distant stars, became prime candidates for the search for life. Researchers now focused on these Goldilocks zones, areas around stars where the conditions might be just right for liquid water to exist. In recent years, the advent of artificial intelligence has revolutionized SETI. Machine learning algorithms now assist in the analysis of vast amounts of data, identifying potential signals that might have otherwise been overlooked. The field of SETI has expanded to include not only the search for radio and optical signals, but also the hunt for biosignatures, chemical patterns that might indicate the presence of life on distant exoplanets. Despite decades of research and numerous technological advancements, no definitive evidence of extraterrestrial intelligence has yet been found. However, the search has deepened our understanding of the universe and our place within it. It has sparked an unyielding curiosity that continues to drive scientific exploration and discovery. The possibility of contact with alien civilizations raises a multitude of profound ethical questions. How would we, as a species, respond to such an encounter? What would be our moral obligations, both to the alien civilization and to ourselves? Would we treat these beings with respect, acknowledging their rights and autonomy, or would we view them as subjects to be studied or exploited? Another pressing question is how we would communicate with an extraterrestrial civilization. The challenge of establishing mutual understanding is monumental. How do we ensure that our messages are clear and not misinterpreted? Could our well-meaning attempts at communication be perceived as hostile, unintentionally leading to conflict instead of cooperation? These are difficult questions that will need to be addressed as the search for extraterrestrial life continues, bringing with it the possibility of transforming humanity's role in the cosmos. When we look to the stars, we are faced with a staggering responsibility. As we advance in our exploration of the cosmos, we must also consider the profound ethical implications of our actions. Should we choose to share our technology, knowledge, or resources with an alien civilization, the decision would carry with it a host of risks and consequences that could alter the course of both civilizations involved. The question we must ask ourselves is, what are the potential costs of such an encounter? One immediate concern is the risk of introducing advanced technology to a less developed society. This could create a dangerous imbalance, giving rise to exploitation, inequality, or even the collapse of the culture we seek to assist. The temptation to help may be strong, but the repercussions could be catastrophic. On the other hand, withholding such knowledge might seem equally unjust, especially if the information or resources could prevent suffering or help another civilization reach its full potential. It's a delicate balance, one that requires careful reflection on the potential for harm versus the potential for good. Moreover, the preservation of both civilizations is paramount. If the interaction between two advanced societies leads to the transference of diseases or ecological disruptions, both worlds might suffer irreparable damage. Even the smallest biological or environmental disruption could lead to unforeseen consequences that threaten the stability and survival of both populations. Such considerations remind us that space exploration is not just about the pursuit of knowledge, but also about ensuring that we do not inadvertently cause harm to those we encounter. This brings us to the existential questions that accompany the idea of contact with alien life. How would such an encounter impact our identity as humans? How would it challenge our place in the universe? The discovery of extraterrestrial intelligence would force us to confront the limits of our anthropocentric worldview. It would compel us to ask deeper questions about what it means to be human and how we define life, consciousness, and intelligence. In the face of such profound challenges, we would need to engage in thoughtful dialogue, integrating diverse viewpoints and forging policies that prioritize peaceful exploration and mutual cooperation over fear, conflict, or domination. The ethical dilemmas that arise from the possibility of encountering alien civilizations reflect the values we hold as a society. They reveal the extent to which we are committed to empathy, understanding, and cooperation, even across the vast distances of space. These considerations should guide our actions as we push the boundaries of exploration. As we move further into the cosmos, we must ensure that our decisions are informed by wisdom, caution, and a deep respect for all forms of life, both familiar and unknown. Meanwhile, the horizon of space exploration continues to shine brightly with groundbreaking missions designed to unlock the secrets of the universe. These missions represent humanity's insatiable curiosity and determination to explore the unknown. One of the most eagerly anticipated projects in this new era of exploration is the return of Martian samples to Earth. Led by NASA and its partners, this effort aims to retrieve rocks and soil from the surface of Mars, potentially containing signs of ancient life. Bringing these samples back to Earth for detailed analysis could provide profound insights into the possibility of life beyond our planet. Such a discovery would forever change our understanding of life in the universe and our place within it. In addition to the Mars sample return, NASA's Artemis program is set to play a pivotal role in humanity's future exploration efforts. After more than 50 years, Artemis aims to return astronauts to the moon, this time targeting the lunar South Pole, a region believed to be rich in valuable resources, including water ice. This new phase of lunar exploration is not merely about landing on the moon, it is about laying the groundwork for future missions to Mars. The Artemis program will serve as a critical stepping stone in the development of the technologies and strategies needed for human missions to the Red Planet in the coming decades. Meanwhile, the James Webb Space Telescope is revolutionizing our understanding of the cosmos. Already operational, this engineering marvel is providing astronomers with unprecedented views of distant galaxies, exoplanets, and the earliest stages of the universe. Its discoveries are poised to answer some of the most profound questions about the origins of the cosmos, the formation of planetary systems, and the potential for life in other parts of the universe. The telescope's ongoing observations will undoubtedly alter the course of scientific thought for generations to come. Another exciting mission that stands poised to expand our knowledge is the Europa Clipper mission. This spacecraft is set to survey Jupiter's icy moon, Europa, which is believed to harbor a vast subsurface ocean beneath its frozen surface. The mission's primary goal is to assess the moon's potential habitability and search for signs of life beneath the ice. This exploration could provide vital clues to the existence of life beyond Earth, as Europa is considered one of the most promising places in our solar system for finding life. The Perseverance rover, currently stationed on Mars, is already paving the way for future human exploration. As it roams the Martian surface, it is collecting samples, conducting experiments, and testing critical technologies that will be essential for human missions to the Red Planet. The rover's work is not only about understanding Mars itself, but also about making the eventual journey to Mars safer and more achievable for human explorers. As these missions unfold, humanity stands on the precipice of a new era in space exploration. Every launch, every discovery, brings us one step closer to understanding the universe in ways we never thought possible. These missions are not just about exploring distant worlds, they are about unlocking the fundamental truths of existence. Each mission promises to deliver innovations, breakthroughs, and insights that will transform our understanding of life, our solar system, and the greater cosmos. Space exploration has revolutionized our understanding of the universe in ways that are nothing short of astonishing. In the past, our knowledge was largely based on limited observations from Earth. The early telescopes and human-driven observations could only offer a glimpse of the vastness of space, hindered by the constraints of our atmosphere and technology. But the launch of satellites and robotic missions has changed everything. These tools have allowed us to peer deeper into space, revealing the universe in exquisite detail, showing us not just stars and galaxies, but the very processes that shape them. One of the most significant breakthroughs came with the advent of space-based observatories. By launching telescopes beyond Earth's atmosphere, we removed the distortions caused by the planet's atmosphere, enabling us to view the cosmos in unprecedented clarity. With this newfound clarity, we were able to detect the faint light of distant stars, unlocking mysteries about their composition, their ages, and their life cycles. We now understand that our galaxy, the Milky Way, is but one among billions of galaxies scattered across an ever-expanding universe. This realization has shifted our understanding of the cosmos, transforming it from a singular, isolated space into a vast and interconnected web of galaxies, stars, and planets. Further missions, such as the Voyager spacecraft, have dramatically expanded our knowledge of our own solar system. These missions ventured beyond Earth's orbit, unlocking secrets about distant planets like Jupiter and Saturn and their moons. Through these explorations, we have learned about the complex atmospheres, diverse geological features, and potential for habitability on worlds such as Mars and Europa. These discoveries have illuminated the dynamic and diverse nature of our solar system, revealing not only the wonders of our own backyard, but also the processes that govern the formation and evolution of planetary systems across the cosmos. Through these missions, we are beginning to piece together the story of the universe, one discovery at a time. Exploring the mysteries of space has long been a pursuit of humanity's collective curiosity, but the discovery of exoplanets, or planets that lie beyond the confines of our solar system, has redefined the way we understand the universe. What was once thought to be an exceptional phenomenon has now become a regular finding, as thousands of these distant worlds have been identified. Their sheer diversity has astonished scientists, as many of these planets orbit their stars within a region known as the habitable zone, an area where conditions could potentially support life. This realization has sent ripples through both scientific circles and the public imagination, sparking a myriad of questions about our existence in the cosmos. Are we truly alone? What does it mean for life on Earth to discover that it may not be a singular occurrence in the vast expanse of the universe? Such discoveries are not just scientific, but philosophical, urging us to reconsider our place within this ever-expanding reality. As our understanding of exoplanets deepens, we have also witnessed the emergence of a powerful tool in space science, high-energy astrophysics. By studying extreme cosmic phenomena like supernovae, black holes, and gamma-ray bursts, astronomers have begun to chart the intricate life cycles of stars and ponder the ultimate fate of the universe itself. These violent and chaotic events, while initially baffling, have provided us with invaluable insights into the fundamental forces that govern the cosmos. The more we learn, the more we realize how much remains to be understood about the true nature of the universe and the fundamental laws that drive it. The discovery of such phenomena has challenged and, at times, overturned previously established notions of physics, forcing us to confront new realities about the nature of space and time. At its core, space exploration has become much more than a series of scientific endeavors. It has evolved into a profound philosophical inquiry, a journey that forces us to examine the very nature of existence. As we uncover more about the universe, we are faced with increasingly complex questions. What is the nature of life, and how does it arise? Are we a unique accident, or is life a common occurrence across the cosmos? Through these questions, space exploration continuously deepens our understanding of ourselves, our purpose, and our place in the vast and mysterious universe. It serves as both a tool for knowledge and a mirror reflecting the curiosity, the drive, and the search for meaning that lies at the heart of human nature. But no single nation or space agency can bear the monumental task of uncovering all the secrets of the universe alone. The sheer vastness of space demands collaboration. Across the globe, space agencies understand the importance of working together to tackle the enormity of exploration. Rather than competing, they come together, sharing their resources, knowledge, and technological innovations to foster a spirit of collective discovery. Through joint missions, these agencies combine their strengths, be it in scientific research, engineering capabilities, or financial support, to maximize the potential of space exploration. When agencies work in tandem, the whole becomes far greater than the sum of its parts, enabling them to accomplish feats that would be impossible to achieve individually. This collaboration is not confined to the planning stages of space missions. It permeates every aspect of the work. For instance, when a new astronomical phenomenon is detected by one agency, its findings are quickly disseminated to other organizations across the world. This rapid sharing of data ensures that discoveries are not isolated to one group, but rather become part of a broader, interconnected scientific community. By working together in this way, space agencies are able to refine existing theories, generate new insights, and make further observations, accelerating the pace of scientific discovery. Large-scale space projects, such as the International Space Station, ISS, epitomize the power of international collaboration. The ISS is not just a research facility in space. It is a testament to what can be achieved when multiple nations join forces. Scientists from diverse backgrounds work side by side aboard the ISS, conducting experiments that advance our understanding of life sciences, physics, and technology. These shared endeavors create an environment of innovation where unique perspectives and expertise from different cultures converge to push the boundaries of human knowledge. The success of the ISS shows that by pooling resources and working together, we can overcome the challenges that come with space exploration and benefit humanity as a whole. In addition to the operational side of space exploration, the global scientific community also engages in regular conferences, gatherings that bring together researchers, engineers, and visionaries to discuss the latest advancements in space science. These events are not merely opportunities for networking. They are forums for the exchange of ideas, the exploration of new possibilities, and the forging of new partnerships. They ensure that space agencies remain at the forefront of cutting-edge research and that the latest breakthroughs are shared globally. The collaborative environment fostered in these settings accelerates the pace of scientific discovery and fosters an ongoing dialogue that keeps all parties aligned on future missions and objectives. As the quest for knowledge moves forward, it is evident that space exploration, though driven by science, is ultimately an endeavor of shared humanity. By working together, space agencies around the world not only increase the efficiency and reach of their missions, but also enhance our collective understanding of the universe. Their cooperation transforms isolated investigations into a unified effort, allowing for comprehensive explorations that reveal the intricate and often awe-inspiring complexity of the cosmos. However, the challenges of deep space exploration are immense, and they require both ingenuity and perseverance to overcome. One of the greatest hurdles is the vastness of space itself. As spacecraft venture farther from Earth, the distances involved become staggering, and communication delays grow more pronounced. Signals sent to a spacecraft millions or even billions of kilometers away can take minutes, hours, or even days to reach their destination, making real-time communication virtually impossible. This presents a major challenge for mission control, as spacecraft must operate with a high degree of autonomy, making decisions and adjustments without waiting for instructions from Earth. This level of independence is essential for the success of long-duration missions such as those to distant planets or moons. Space itself presents numerous other dangers. One of the most pressing is the pervasive radiation that exists outside Earth's protective atmosphere. Cosmic radiation is a constant threat to both spacecraft and astronauts, with the potential to damage equipment or harm the health of crew members. While technologies such as shielding can provide some protection, the dangers remain ever present, especially on long-term missions. The extreme temperatures in space, ranging from intense heat to frigid cold, pose another major challenge. Spacecraft must be engineered to withstand these harsh conditions with materials and systems that can function reliably in the face of such extreme variations. On top of these environmental challenges, life support systems also play a crucial role in ensuring the safety and well-being of astronauts. During manned missions, especially those that last months or years, the supply of essential resources, air, water, and food, becomes a critical concern. Engineers have developed closed-loop systems that recycle air and water, ensuring that resources are used efficiently and waste is minimized. The goal is to create sustainable systems that do not rely on constant resupply from Earth. However, as these systems grow more complex, so do the risks of failure, requiring careful monitoring and constant innovation to ensure that everything runs smoothly. Beyond the physical demands, space missions also take a psychological toll on astronauts. The isolation, confinement, and vast distance from home can have significant mental and emotional effects. Long-duration missions place astronauts in environments where they are cut off from their families, friends, and the comforts of Earth. Maintaining psychological resilience is as important as physical health in ensuring the success of a mission. Rigorous training, careful selection, and strong support systems are vital in preparing astronauts for the mental challenges they will face during extended space travel. Coping with the isolation of space requires both personal fortitude and the support of a team, working together to maintain morale and focus despite the challenges they face. Thus, space exploration is not just about pushing the boundaries of science and technology. It is about confronting the complexities of human existence. As we continue to reach for the stars, we are not only seeking to understand the universe, but also to better understand ourselves. The path to the stars is as much about overcoming the obstacles within as it is about overcoming the obstacles in the vastness of space itself. The journey is long, difficult, and fraught with challenges, but it is a journey that humanity is destined to undertake together as we seek answers to the most fundamental questions of life and the universe. The challenges associated with funding and technological development remain some of the most significant obstacles in the pursuit of deep space exploration. The exorbitant costs of developing and launching missions that venture beyond Earth's orbit often spark intense competition for funding, with different scientific projects vying for limited financial resources. This intense competition can lead to delays, slowdowns, and missed opportunities, hindering the pace at which we can expand our reach into the cosmos. Despite these challenges, humanity's drive to understand the universe continues to push forward. Scientists, driven by an unyielding curiosity and an innate desire for discovery, press onward, overcoming the barriers that limit progress. In this quest, international cooperation has proven to be a critical factor, shaping the future of space exploration by fostering a collaborative environment. It is within this framework of unity that nations, each with its own unique strengths and resources, come together to pool their expertise, knowledge, and technological advancements. Space exploration, by its very nature, is an ambitious and costly endeavor that often requires decades of meticulous planning and significant financial investment. In such a high-stakes, resource-heavy arena, international partnerships provide a lifeline. By collaborating on large-scale projects, countries can distribute the financial burden, making it more feasible to undertake ventures that might otherwise be unattainable for any single nation alone. This collaboration extends far beyond financial support. Each country brings specialized expertise to the table, whether it be in the development of cutting-edge rocket propulsion systems, advanced satellite technologies, or the design of sophisticated spacecraft. The exchange of these capabilities leads to more innovative solutions, accelerating the pace of discovery and breaking new ground in our understanding of space. For example, one country may possess world-leading satellite communication technologies, while another may excel in creating powerful propulsion systems capable of taking us deeper into the cosmos. The fusion of these complementary skills results in missions that are far more capable and ambitious than any nation could accomplish on its own. Working together also opens doors to more complex and challenging missions. Through shared efforts, partners can take on projects that push the boundaries of what we thought possible. International collaborations allow for the kind of multidisciplinary work that can achieve feats beyond the reach of individual capabilities. The cooperative spirit that underpins many space missions is epitomized by projects like the International Space Station, ISS, a groundbreaking achievement where astronauts and scientists from multiple nations live and work together in space, conducting experiments that benefit not only their home countries but all of humanity. These joint efforts also foster a unique environment of knowledge exchange. Scientists and engineers from various parts of the world collaborate on research, bringing diverse perspectives and innovative ideas to the table. This cross-pollination of thought often leads to breakthroughs that might not have occurred in isolated environments. The ISS, for example, has been a laboratory for scientific experiments that have advanced our understanding of biology, physics, and material science, all thanks to the synergy of multiple nations working together. It's a living testament to the power of collaboration, where the combined resources of many countries have led to progress that benefits all of humankind. Additionally, the formation of international partnerships in space exploration serves a broader purpose. It has the potential to ease geopolitical tensions. When nations come together with a shared goal, in this case, the exploration of the cosmos, it helps to build trust and understanding. The peaceful pursuit of knowledge in space reinforces the notion that space is not the domain of any single nation, but belongs to all of humanity. In this shared endeavor, political boundaries become less significant, and the collective aspiration to explore, discover, and learn takes precedence over individual national interests. As we look to the future of space exploration, including ambitious goals like crewed missions to Mars and the establishment of sustainable bases on the Moon, the importance of international cooperation becomes ever more evident. These monumental tasks will require the combined efforts of numerous countries, each contributing its best practices, technologies, and ideas. It is clear that space exploration is no longer an individual pursuit, but a collective journey that unites all of humanity. The challenges we face are immense, but through unity we can overcome them and continue pushing the boundaries of human knowledge. Turning now to one of the most profound mysteries of the universe, the Big Bang Theory. Several key pieces of evidence have been uncovered that provide compelling support for this model of the universe's origins. The Big Bang Theory offers a picture of the universe beginning as a singular, hot, and dense point, then rapidly expanding to form the cosmos we see today. One of the most significant pieces of evidence supporting this theory comes from the discovery of cosmic microwave background radiation, a faint glow that fills the entire universe. This radiation is a remnant of the energy that once permeated the universe during its infancy, shortly after the Big Bang. Discovered in the 1960s, it provides a snapshot of the universe just after its birth, offering strong confirmation of the Big Bang's validity. Another vital piece of evidence supporting the Big Bang theory comes from the observation of the redshift of distant galaxies. As we look at galaxies that lie far away from us, we notice that they are all moving away, with more distant galaxies receding at faster speeds. This observation, known as the redshift, indicates that the universe is expanding. Just like the surface of an inflated balloon, as the universe expands, galaxies, which are analogous to the points on the balloon's surface, move further apart from one another. This discovery reinforces the idea that the universe began from a dense, compact state and has been expanding ever since. In addition, the relative abundance of light elements such as hydrogen, helium, and lithium provides further support for the Big Bang theory. The theory predicts specific ratios for these elements based on the conditions that would have existed in the early universe. Observations of the cosmic makeup of the universe show that the abundance of these light elements closely matches the predictions made by the Big Bang model. This consistency between theory and observation strengthens our confidence in the idea that the universe originated in a hot, dense state and has been evolving ever since. Taken together, these pieces of evidence, cosmic microwave background radiation, redshift observations, and the abundance of light elements, form a powerful and coherent picture of the universe's violent beginnings. They help to explain not only the origins of the cosmos, but also its ongoing evolution, reinforcing the Big Bang theory as the most robust explanation for the universe we see today. Each of these pieces of evidence provides a unique window into the past, offering clues about the conditions that existed in the early universe, and continues to inform our understanding of how the cosmos has developed over the billions of years since its birth. Thus, as humanity ventures further into space, both through collaborative international efforts and through expanding our scientific understanding, the exploration of the universe continues to offer us profound insights. Whether through the examination of the origins of the cosmos or the pursuit of missions to explore other worlds, the drive for knowledge remains a constant, guiding humanity forward into the unknown. Through innovation, cooperation, and discovery, we expand our horizons, unraveling the mysteries of the universe one piece at a time. Our understanding of the early universe has transformed dramatically over the course of the 20th and 21st centuries, evolving from philosophical speculation to scientifically grounded theories supported by empirical evidence. In the early years of the 20th century, the prevailing view of the universe was one of constancy, a static, unchanging entity that existed forever, untouched by time. Yet, this assumption would be upended with a series of groundbreaking discoveries that reshaped the entire field of cosmology. It all began with the pivotal work of Edwin Hubble, whose observations in the 1920s revealed that galaxies were receding from one another at a rate that suggested the universe was expanding. This realization was a seismic shift in the scientific community. The idea that the universe was not eternal and unchanging, but rather in motion, expanding, and evolving, had profound implications. It led to the development of the concept of a dynamic universe, ultimately pointing to the possibility that it had a beginning. This groundbreaking discovery set the stage for the Big Bang theory, a model that would take decades to fully develop. As research progressed, scientists and astronomers began to refine their understanding of the early universe. Initially, the Big Bang was often thought of as a simple explosion, a cataclysmic event that resulted in the formation of the universe. However, as data accumulated and technological advancements enabled deeper observations, a more nuanced picture emerged. The Big Bang was not merely an explosion in the conventional sense. Rather, it represented a rapid, exponential expansion of space itself from an extraordinarily hot and dense state. This new model described the universe as not just expanding outward, but also undergoing a profound transformation, with particles gradually coming together to form atoms, stars igniting, and galaxies slowly coalescing into the vast structures we observe today. One of the most critical pieces of evidence for the Big Bang theory came in the form of cosmic microwave background radiation. This faint, pervasive glow that permeates the universe is a remnant of the intense heat that filled the cosmos just moments after the Big Bang itself. Discovered by Arno Penzias and Robert Wilson in 1965, this radiation provided a snapshot of the early universe, frozen in time, and offered strong confirmation that the universe had indeed begun in a hot, dense state. As technology improved, so did the precision with which scientists could measure and map the cosmic background. The distribution of galaxies across the universe, along with subtle patterns in the cosmic radiation, led to refinements in our models, incorporating new theories such as cosmic inflation. Cosmic inflation, a concept proposed by physicist Alan Guth in the 1980s, revolutionized the understanding of the universe's earliest moments. Inflation suggests that in the first moments after the Big Bang, the universe expanded at an astonishing rate, far faster than the speed of light. This rapid inflationary phase smoothed out the small irregularities present in the fabric of space, leaving behind the large-scale uniformity that we observe in the distribution of galaxies today. While the Big Bang theory explains the overall expansion of the universe and the presence of cosmic microwave background radiation, it struggled to explain the remarkable uniformity of the universe across vast distances. Inflation provided the missing link, addressing the so-called horizon problem by suggesting that regions of space, which appeared disconnected, might have once been in contact before the inflationary period stretched them apart. In more recent years, our understanding of the universe has become even more complex as scientists have delved deeper into the mysterious realms of dark matter and dark energy. These elusive substances constitute about 95% of the universe's total content, with dark matter making up approximately 27% and dark energy accounting for a staggering 68%. While these components remain invisible to our instruments, their influence on the structure and expansion of the universe is undeniable. Dark matter plays a crucial role in the formation of galaxies, while dark energy is thought to be responsible for the accelerating expansion of the universe. Their existence and interplay have added layers of complexity to our models of the early universe, suggesting that the cosmos is influenced by forces and entities that we are only beginning to understand. The ongoing exploration of dark matter, dark energy, and other cosmic phenomena continues to refine our understanding of the universe's early stages. New breakthroughs, more sophisticated tools, and more detailed observations promise to shape and reshape our models of the cosmos. As each piece of the cosmic puzzle falls into place, we move closer to understanding the origins of everything we observe today, from the formation of the first stars to the complex interplay between matter and energy that has governed the evolution of the universe. Seconds after the Big Bang, the universe was an intensely hot and dense place, a state so extreme that it's almost impossible to imagine. To give a sense of scale, picture a vast ocean of energy, where particles flickered in and out of existence. At this stage, there were no atoms, no solid forms, and certainly no stars or galaxies, just an ocean of energy and fundamental particles in a constant state of flux. The temperature during this epoch was so high that it was capable of forging the very building blocks of matter. This period, known as the Planck era, represents a time when the fabric of space and time itself was still in a chaotic state, with the fundamental forces of nature, gravity, electromagnetism, and nuclear forces unified into a single entity. As the universe expanded rapidly, it began to cool. This cooling process allowed quarks, the elementary particles that form protons and neutrons, to come together and form the first atomic nuclei. This transformation was not smooth. It was a chaotic and intense period where particles collided and interacted in a fierce struggle for stability. For several minutes after the Big Bang, the universe remained too hot for stable atoms to form, and instead, a dense soup of particles raced around at high velocities. It was only after a few minutes that nuclear fusion began, allowing protons and neutrons to combine into simple nuclei, primarily hydrogen and helium. These first elements would lay the foundation for everything that followed. As the universe continued to expand and cool, the stage was set for the formation of stars and galaxies, leading to the cosmic structures we see today. The early universe was like a cosmic crucible, where the fundamental ingredients of the cosmos were forged under intense heat and pressure. This process was slow but steady, and over millions of years, it paved the way for the formation of the first stars, galaxies, and clusters of galaxies, which would eventually give rise to the universe we now inhabit. The theory of inflation added a new layer of depth to our understanding of the early universe. It not only accounted for the uniformity of the cosmos, but also offered a potential explanation for some of the most perplexing questions about the nature of space and time. According to inflationary theory, the universe underwent an extremely rapid expansion, many orders of magnitude faster than the speed of light, just fractions of a second after the Big Bang. This inflationary phase would have stretched space itself, smoothing out any irregularities and creating a uniform environment. To visualize inflation, one might imagine inflating a balloon. As the balloon expands, its surface becomes increasingly uniform. Similarly, the universe's rapid inflation stretched space to such an extent that regions far apart from one another became indistinguishable, explaining the observed uniformity in the large-scale structure of the cosmos. Through these groundbreaking theories and discoveries, our understanding of the early universe has progressed from a vague and speculative notion to a sophisticated, evidence-backed model. Yet, as we look further into the cosmos and refine our observations, it's clear that much remains to be understood. The universe is a place of mystery and wonder, and every breakthrough brings us one step closer to unlocking the secrets of its origins. The journey of understanding the cosmos is ongoing, and as technology advances and our theories evolve, we continue to uncover new facets of the universe's vast and fascinating history. In addition, this rapid expansion provides a compelling explanation for the observed flatness of the universe. When viewed from the perspective of large cosmic scales, the process of inflation serves to push the observable universe toward a geometry that is flat. This flattening effect is not merely a coincidence, but a natural consequence of the inflationary theory, which suggests that during its earliest moments, the universe underwent an incredibly brief but immensely rapid expansion. This event would have had profound implications, shaping the universe's large-scale structure and aligning it in a way that we still observe today. The theory of inflation also accounts for the intricate patterns that we observe in the universe. Tiny fluctuations that existed in the universe's very earliest stages were stretched out during this inflationary period. These minuscule variations, which might have seemed insignificant at the time, would later grow over billions of years into the galaxies, stars, and clusters of galaxies that populate the cosmos. By incorporating inflation into the Big Bang model, scientists are able to address several of the most perplexing puzzles that have stumped cosmologists for decades. One of these is the so-called horizon problem, which asks why distant regions of space appear to be so uniform in temperature and density, even though they should not have had time to exchange information with one another, given the finite speed of light. Inflation provides a solution by suggesting that these regions were once close enough to be in thermal equilibrium before the rapid expansion pushed them apart. Similarly, inflation addresses the flatness problem, why the universe's density appears to be so perfectly balanced, so close to a critical value. According to the inflationary model, this fine-tuning is a natural outcome of the expansion process. Thus, inflationary theory does more than merely offer a picture of how the universe came into being. It enhances our understanding of the origins of the cosmos and provides a coherent framework for explaining the complex and varied structures we observe today. The idea that the universe expanded exponentially in its earliest moments is a central feature of modern cosmology, offering explanations for a wide range of phenomena that previously seemed mysterious or inexplicable. At the heart of our quest to understand the universe lies the mystery of the Big Bang itself. This event, which marks the beginning of space and time as we know it, represents one of the greatest enigmas of modern science. While we are confident that the universe began as an intensely hot and dense state, the precise mechanisms behind this explosive event remain elusive. What, if anything, preceded the Big Bang? Could it be that our current understanding of time itself is inadequate to explain this earliest moment in the history of the cosmos? The very nature of this question challenges our fundamental concepts of time, space, and causality. Beyond the Big Bang, there are other profound mysteries that continue to captivate scientific minds. One of the most pressing of these concerns, the enigmatic substances known as dark matter and dark energy, which together comprise around 95% of the total mass energy content of the universe. Dark matter, though invisible, exerts a gravitational influence that is crucial to understanding the motion of galaxies and the formation of large-scale cosmic structures. Despite extensive research, its true nature remains one of the most tantalizing unknowns in physics. Uncovering the properties of dark matter could not only reveal how galaxies form and evolve, but could also provide deeper insights into the fundamental forces that govern the universe. Similarly, dark energy, which appears to drive the accelerated expansion of the universe, raises more questions than answers. Why does this mysterious form of energy exist, and what role did it play in the early universe? Understanding dark energy could potentially lead to revolutionary new insights about the fate of the universe and whether it will continue to expand forever or eventually reach a more stable state. Another area of intense interest to cosmologists is the theory of cosmic inflation. This concept proposes that in the briefest of moments after the Big Bang, the universe expanded at an extraordinary rate, far faster than the speed of light. While the idea of inflation offers solutions to several key cosmological puzzles, it also raises its own set of questions. What triggered this rapid expansion? Was it a universal phenomenon, or did it arise from local conditions unique to the early universe? Exploring the origins of inflation and its implications is one of the most exciting frontiers in modern cosmology. At the heart of these questions lies the challenge of reconciling two seemingly incompatible theories: quantum mechanics and general relativity. Quantum mechanics governs the behavior of the smallest building blocks of matter, while general relativity describes the behavior of large-scale cosmic structures. Despite their successes, these two theories have yet to be unified into a single framework. The search for a theory of quantum gravity, one that can encompass both the very small and the very large, remains one of the greatest challenges in theoretical physics. Is there new physics waiting to be discovered, or are we missing a fundamental principle that can unify these two pillars of modern science? In the quest to understand the cosmos, the concept of a multiverse has emerged as one of the most mind-bending and provocative ideas. If our universe is merely one of many, each with its own laws of physics and potentially different forms of existence, what does this mean for our understanding of our origin and the nature of reality itself? The multiverse hypothesis pushes the boundaries of both science and philosophy, offering a framework in which the entire cosmos could be far more complex and varied than we could ever imagine. These profound questions are not just the domain of scientists, but also of philosophers, theologians, and thinkers of all kinds. The search for answers to questions about the universe's origins, its structure, and its ultimate fate is a deeply human endeavor, one that calls into question not just where we come from, but the very nature of existence itself. Each discovery brings us one step closer to understanding the grand narrative of the cosmos and our place within it. The pursuit of this knowledge invites us to ponder the deepest mysteries of space and time, to explore the very fabric of reality, and to contemplate the vast unknowns that still lie before us. When we attempt to comprehend cosmic time, we are faced with a vast and intricate task. Scientists rely on a combination of observational data and well-established theories to piece together a coherent picture of the universe's history. Picture the universe as an immense book, where each page turn reveals an important chapter in the cosmic saga, from the explosive beginnings of the Big Bang to the slow but steady formation of galaxies, stars, and planets. Each page is written in the language of light, as every cosmic event emits energy that can be detected and analyzed by astronomers. To measure this cosmic time, astronomers use two primary methods. First, they observe the light emitted by distant celestial objects. The farther away an object is, the longer its light takes to reach us, which means we are essentially looking into the past. Light acts as a kind of time machine, allowing us to glimpse the universe as it appeared at different points in its history. By carefully studying this light, scientists can determine how far back in time they are observing and reconstruct key moments in the universe's evolution. The second method relies on studying the rate of cosmic expansion. Imagine a loaf of bread rising in the oven. As it bakes, the dough expands and the raisins embedded in it move farther apart. In much the same way, as space itself expands, galaxies move further away from each other. By examining this expansion, scientists can estimate the age of the universe and trace its evolution from the earliest moments of the Big Bang to the present day. Another key tool in this effort is the concept of cosmic redshift. As the universe expands, the light from distant galaxies is stretched out, shifting towards longer, redder wavelengths. This redshift serves as a direct evidence of the ongoing expansion and also provides vital information about the universe's age, size, and overall evolution. By combining data from the behavior of light, the expansion of space, and the movements of galaxies, scientists have been able to piece together a detailed history of the universe, one that tells the story of its fiery beginnings, its slow but steady cooling, and its eventual formation of stars, planets, and galaxies. Integral to our understanding of cosmic time is the theory of relativity, developed by Albert Einstein. This groundbreaking theory revolutionized our understanding of space, time, and gravity. At its core, relativity teaches us that space and time are not separate but form a single, unified entity known as space-time. Massive objects like stars and planets warp this fabric, causing smaller objects to move in ways that we now understand as the force of gravity. Rather than being a force acting at a distance, gravity is seen as the curvature of space-time itself. Imagine placing a heavy ball on a trampoline. The ball creates a depression in the fabric of the trampoline, and smaller objects placed nearby will roll toward it. In the universe, planets orbit stars not because they are simply drawn to them, but because the stars are bending the very space around them. This profound insight into the nature of gravity has changed our understanding of the cosmos, providing a powerful tool for predicting the behavior of celestial bodies and the evolution of the universe itself. The theory of relativity has reshaped our understanding of the universe in profound ways, challenging long-held concepts of time, space, and reality itself. At its core, it reveals that time is not an absolute, unchanging force, but something that can be shaped by the forces at work in the cosmos. This concept of relativity fundamentally alters the way we think about time, showing that its passage can vary depending on both speed and gravity. Time dilation, one of the theory's most mind-boggling consequences, illustrates how time can slow down in certain conditions, leading to a remarkable shift in how we perceive the universe. In its simplest form, relativity teaches that the flow of time is influenced by the motion of observers and the strength of gravitational fields. Consider a person standing near a massive object, like a black hole. Time for this person would pass much more slowly than for someone far away from such an immense gravitational force. This phenomenon is most easily understood through the concept of time dilation, which occurs when one object is in motion relative to another. The faster an object moves, especially as it approaches the speed of light, the slower time appears to pass for it compared to a stationary observer. This is a strange yet fascinating consequence of Einstein's insights. Imagine, for example, astronauts on a deep space mission traveling at speeds near the speed of light. While their subjective experience of time might be only a few years, decades would pass on Earth. This means that upon their return, they would discover that their friends and family have aged much more than they have. The implications are profound, not just for astronauts, but for our entire understanding of time. It challenges everything we know about the continuity of our lives, the ticking of the clock, and the irreversible flow of time from one moment to the next. Yet, time dilation is not limited to speed alone. Gravitational fields, too, have a similar impact on time. Near a massive body like a planet, time flows more slowly compared to areas where gravity's pull is weaker. Imagine you have two clocks. one on the surface of a planet and another hundreds of miles away in space. The clock closer to the planet's surface would tick more slowly due to the intense gravitational field, while the clock in space, far from such influence, would run at a normal rate. This means that someone living in a strong gravitational field would age slightly more slowly than someone in a region of weaker gravity. A person working on the surface of a planet, for instance, would experience time differently compared to someone living in orbit. These effects are a far cry from the rigid, predictable time that we experience in our daily lives. They reveal a universe where time is flexible and responsive to the forces around it. The flow of time, it turns out, is not something we can take for granted. Instead, it's something that can be altered by both speed and gravity. Such realizations invite us to reconsider our place in the cosmos and our relationship to time itself, suggesting a universe far more dynamic and complex than we could have ever imagined. Time dilation, however, is just one aspect of the extraordinary insights provided by relativity. Another captivating theoretical concept within this framework is the idea of wormholes, mysterious passages through the fabric of space-time that could potentially allow us to bypass the immense distances that separate locations across the universe. Imagine the universe as a vast, two-dimensional sheet of paper. On that paper, different points represent distant places in the cosmos. Now, if you take a pencil and fold the paper, you connect two far-off points, effectively bringing them together. This is a rough analogy for how wormholes might function. They could, in theory, allow us to travel from one distant point in space to another almost instantaneously, defying our usual notions of travel time. The potential implications of wormholes for our perception of time and space are staggering. If we could somehow enter a wormhole at one point in space and emerge at another, the journey would take only moments, regardless of the vast distance between the 2 points. This concept shatters our conventional understanding of travel time, making it seem as though we were stepping through a doorway rather than embarking on a journey across light years. But the potential for wormholes doesn't stop there. Some theories even suggest that, depending on the properties of the wormhole and the way it's used, they could provide a means for time travel, both to the past and the future. However, with such possibilities come profound challenges and paradoxes. For instance, entering a wormhole might allow a traveler to exit at an earlier point in time, creating a paradox where cause and effect no longer hold. How could one exist in two places at once, or alter events that have already taken place? These are questions that wormholes raise, and though the potential for time travel is tantalizing, it also brings with it the possibility of disrupting the very fabric of causality. The concept of wormholes forces us to rethink how we view time as a linear progression and space as a fixed dimension. Instead, wormholes offer a provocative new perspective, that both time and space could be manipulated in ways that were previously thought impossible. As we continue to explore the mysteries of space, the intertwined concept of space-time remains a critical cornerstone in our understanding of the universe. Space and time, once seen as separate entities, are now understood to be intricately linked in a four-dimensional continuum. This revelation, first introduced by Albert Einstein's groundbreaking work, shows us that gravity is not simply a force that pulls objects together, but a distortion of space-time itself. Massive objects like stars, planets, and black holes warp the very fabric of space-time, creating bends and curves that govern the movement of everything around them. Astronomers and physicists now study how objects move within this flexible, malleable fabric. Rather than thinking of planets and stars as moving through an unchanging backdrop of space and time, they consider how space-time itself is influenced by the mass and energy of those objects. For example, when studying the orbits of planets around the Sun or the motion of stars in distant galaxies, scientists must account for how these massive bodies curve the space-time around them. The closer an object is to a massive body, the more pronounced the warping of space-time becomes, which in turn affects the path of nearby objects. This has allowed us to make more accurate predictions about the behavior of celestial bodies and to understand phenomena like black holes, neutron stars, and even the expansion of the universe itself. Relativity, with its mind-bending consequences, continues to shape our understanding of the universe, from the smallest particles to the largest galaxies. It reminds us that the cosmos is far stranger and more complex than we could have ever imagined. As we venture deeper into space, and as our theories evolve, relativity will remain a guiding force in our quest to understand the very nature of existence. It reveals not just how the universe works, but also how deeply interconnected time, space, and gravity truly are, changing everything we thought we knew about the cosmos and our place within it. The study of the universe, from its smallest particles to its grandest structures, hinges on an intricate understanding of space and time. As our comprehension of these concepts deepens, astronomers have developed methods to interpret the light and signals coming from distant corners of the cosmos. The framework of space-time is critical in this regard, providing the lens through which celestial phenomena are viewed. One key phenomenon that illuminates the relationship between light and gravity is gravitational lensing. This occurs when light from far-off galaxies passes through varying gravitational fields. These fields warp the fabric of space-time, bending the path of light and distorting the images of distant objects. By studying these distortions, astronomers can glean crucial information about the distribution of unseen mass in the universe, known as dark matter, and even gain insights into the expansion of the universe itself. But the role of space-time doesn't end there. Gravitational waves, another major discovery tied to the concept of space-time, have furthered our understanding of the cosmos. Predicted by Einstein more than a century ago, these ripples in the fabric of space-time are generated by massive objects such as black holes or neutron stars, accelerating through the vast expanse of the universe. The detection of these waves, which was achieved only recently, not only confirmed key aspects of Einstein's theory of general relativity, but also opened a new realm of research. Now, scientists can study cosmic events, like the violent mergers of black holes or neutron star collisions, through a fresh perspective, providing unprecedented views of the universe's most energetic phenomena. By understanding these distortions in space-time, researchers continue to build upon their knowledge, creating hypotheses, analyzing complex data, and ultimately unraveling the mysteries that lie at the heart of the cosmos. The story of Stars 2 is a tale written in the language of space and time. Stars, like our sun, are born in massive clouds of gas and dust, known as nebulae, that scatter throughout the universe. These clouds, primarily composed of hydrogen, are the raw materials from which stars are forged. Over time, gravity begins its work, pulling the gas and dust together into clumps. As these clumps collapse inward, they form a dense core, a protostar. The energy generated by this contraction heats up the core, and as the temperature and pressure increase, nuclear fusion begins. This marks the beginning of the star's life cycle. Once fusion ignites, the star enters its main sequence phase, where hydrogen atoms are fused into helium at the core, releasing vast amounts of energy. This energy counteracts the gravitational pull, stabilizing the star and causing it to shine brightly for millions to billions of years, depending on its mass. As time passes, the star begins to exhaust its hydrogen supply, and the balance between gravity and radiation pressure shifts. For stars similar in size to our sun, this marks the beginning of the next phase of their life cycle. The star swells up into a red giant, and as the core contracts, the temperature rises, allowing fusion to continue, this time with heavier elements like helium. As the outer layers expand and cool, the star's outer appearance takes on a reddish hue. The progression of fusion in these red giants is essential as it creates the elements that will eventually be the building blocks of planets and life. However, the fate of stars larger than our sun is even more dramatic. These stars go through multiple stages of fusion, producing increasingly heavier elements, all the way up to iron. But once the core of such a massive star is composed entirely of iron, fusion ceases. Unlike lighter elements, iron cannot generate energy through nuclear fusion, and the star can no longer resist the inward pull of gravity. The result is a catastrophic collapse of the core, which triggers a supernova explosion. This explosion releases an enormous amount of energy and scatters the star's outer layers into space. This event not only marks the end of the star's life, but also contributes to the creation of new elements that will form future stars, planets, and possibly life. What remains after a supernova is a remnant, which could either be a neutron star or, if the original star was massive enough, a black hole. Neutron stars are incredibly dense, their cores collapsing into a city-sized object with a mass greater than that of the Sun. Black holes, on the other hand, have such strong gravitational fields that not even light can escape them. They are the most mysterious and extreme remnants of the stellar life cycle. For stars that are smaller than our Sun, the story unfolds differently. These stars shed their outer layers as they reach the end of their lives, leaving behind a dense core. Over the course of billions of years, this core cools and dims, eventually becoming a white dwarf. Unlike the violent end of massive stars, this process is relatively gentle, and the white dwarf fades away, marking the quiet end of a once bright star. In all cases, the fate of a star is intimately tied to its mass and the elements it has available for fusion. Smaller stars end their lives peacefully, while larger ones follow a path marked by explosive, violent events that shape the future of the universe. The cosmic cycle of stellar birth, life, and death plays an essential role in the ongoing evolution of the universe. It is a process of continuous renewal, with the remnants of old stars providing the material for new stars to form. Supernovae, the explosive deaths of massive stars, play a particularly important role in this cycle. These colossal explosions are not only the end of a star's life, but also the creation and distribution of essential elements like iron, carbon, and oxygen. The shock waves from these explosions push these newly created elements into space, enriching the interstellar medium. This process of enrichment is crucial, as it supplies the raw materials for the next generation of stars and planets. Without supernovae, the universe would be devoid of many of the elements that make life as we know it possible. Thus, stars are not just the luminous objects that light up the night sky. They are the furnaces that forge the elements of the universe. They live out a cycle of creation, transformation, and destruction, each stage contributing to the grand cosmic narrative. The energy generated through nuclear fusion in their cores powers entire galaxies, while their deaths give rise to new generations of stars, planets, and ultimately life. By understanding the intricate details of the stellar life cycle, scientists can piece together the story of the universe itself, a story that continues to unfold with each new discovery. Supernovae are not merely cataclysmic explosions marking the end of a star's life. They are pivotal events that ripple through the very fabric of the universe, leaving profound impacts on the surrounding cosmos. When a star reaches the end of its life, it detonates in a brilliant burst of energy known as a supernova, the aftermath of which affects not only the star itself, but also its immediate environment and even distant galaxies. The shockwaves from a supernova have the power to reshape the structure of an entire galaxy. As the explosion reverberates through space, it sends out intense shock fronts that compress surrounding clouds of gas and dust. This compression is no small event. It triggers new star formation, sparking a cycle of creation initiated by the death of a once mighty star. The interaction between supernovae and star formation is a delicate, interconnected dance, one that plays a key role in the ongoing evolution of galaxies. In this cosmic ballet, the death of one star gives rise to the birth of others, cycling through the phases of destruction and creation, weaving the complex and dynamic structures that we observe in the universe. But the influence of a supernova does not end there. The energy unleashed during these stellar explosions is so immense that it can strip away the atmospheres of nearby planets, rendering them barren and inhospitable. Whole star systems may be disrupted, their orbits and stability irrevocably altered. The intense radiation produced in the aftermath of a supernova can sterilize entire regions of space, leaving no room for life as we know it. Instead, a nebula, a glowing cloud of gas and dust, is left behind, a celestial graveyard of the stellar material that once made up the now dead star. Yet even in death, the supernova's contribution is not over. The remnants of these stellar explosions, known as supernova remnants, continue to evolve over time, providing an ongoing source of energy, raw materials, and even the possibility for new cosmic phenomena. In some cases, these remnants may collapse to form neutron stars, or, in the most extreme scenarios, even black holes, objects so dense that not even light can escape their gravitational grip. Supernovae are, in essence, both creators and destroyers within the universe. They distribute essential elements like carbon, oxygen, and iron into the interstellar medium, seeding the galaxy with the very building blocks necessary for life and new stars. These elements, forged in the heart of stars and spread throughout the cosmos, become part of a greater cosmic cycle, contributing to the dynamic and ever-evolving nature of the galaxy. Stars themselves are not merely the points of light we see in the night sky. They are colossal furnaces of nuclear fusion, where lighter elements like hydrogen are fused to form heavier elements like helium. As stars evolve, they continue this process, forging even heavier elements like carbon, oxygen, and iron. When a star reaches the end of its life, it often explodes in a supernova, ejecting these newly formed elements into space, where they enrich the surrounding interstellar medium. This enrichment is not just a random occurrence. It plays a critical role in shaping the very nature of the galaxy. The expelled elements mix with gas and dust, setting the stage for the formation of new stars and planetary systems. Even smaller stars, which do not end their lives in a violent explosion, contribute to the cosmic cycle. As they reach the red giant phase, they shed their outer layers gently, leaving behind a planetary nebula. This too adds essential elements to the galaxy, further enriching the interstellar medium and setting the stage for future generations of stars and planets. Over the course of billions of years, successive generations of stars give rise to a continually evolving cosmic landscape. Initially, the galaxy is composed largely of hydrogen and helium, the simplest and most abundant elements in the universe. But with each generation of stars, the galaxy grows richer in heavier elements, elements that are critical for the formation of planets and the emergence of life. Carbon, nitrogen, oxygen, these are the very building blocks of life, and they are formed and dispersed by stars as they live and die. Without stars, life as we know it would not exist, as the elements necessary for life are only produced in the high-pressure environments inside stars. In addition to their role in the creation of elements, stars are also central to the formation of planets. Picture the early solar system around a newly forming star. This environment is filled with a swirling cloud of gas and dust known as a solar nebula. Gravity begins to pull this material together, and as it condenses, it starts to rotate, forming a disk around the young star at the center. The energy from the star causes the materials within this disk to melt, vaporize, and redistribute. Small particles collide and stick together, eventually coalescing into larger bodies known as planetesimals. This process, the gradual accumulation of matter, is the crucial first step in the formation of planets. As the planetesimals continue to collide and merge, they grow larger, eventually forming full-fledged planets. In the cooler outer regions of the disk, volatile materials like ice condense to form gas giants. Massive planets with thick atmospheres and the ability to capture vast amounts of gas from their surroundings. In the hotter inner regions, rocky planets begin to take shape, formed from metals and silicates that do not easily evaporate. The star provides not only the gravitational force that initiates and sustains this process, but also the heat and radiation necessary for the materials within the disk to undergo the transformations that lead to planet formation. The type of star at the center of the system influences the type of planetary system that forms around it. The specific characteristics of the star, the temperature, the amount of radiation, the composition of the gas and dust in the surrounding nebula, determine the types of planets that will emerge. This interplay between star and planetary system creates an incredibly diverse array of planetary environments, each one a unique outcome of the cosmic interactions that shape it. Gravity, the fundamental force that governs the universe, is a constant presence in these cosmic processes. It is the architect of the universe, shaping everything from the smallest molecular clouds to the largest galactic superclusters. Within galaxies, gravity is responsible for pulling together vast clouds of gas and dust, which eventually condense to form stars. The birth of stars, in turn, has a profound impact on the surrounding environment, as the energy and radiation they emit further shape the galaxy. Gravity governs the orbits of stars within galaxies, creating a delicate balance that ensures order within the vast, swirling expanse of stars. When we zoom out to the cosmic scale, gravity plays an even more significant role. It dictates the arrangement of galaxies within clusters and superclusters, influencing their motion and even pulling them together over millions of years. This gravitational attraction leads to the formation of vast cosmic webs, intricate structures made up of galaxies, gas, and dark matter. Dark matter, although invisible and undetectable by traditional means, plays a crucial role in this process. Its gravitational influence helps explain why galaxies rotate the way they do, and why they appear to cluster together, despite visible matter not being sufficient to account for these behaviors. The complex and mysterious effects of gravity at this scale are still being studied, offering us a deeper understanding of the universe and its many intricate processes. In the end, supernovae and stars themselves are inextricably linked to the larger cosmic forces that govern the universe, from their role in creating and destroying to their influence on the formation of planets and the composition of galaxies. These stellar phenomena are integral to the fabric of the universe. Each supernova is a moment of cosmic significance, each star a building block in the ongoing evolution of the universe. And gravity, the unseen force that binds it all together, continues to shape the cosmos in ways we are only beginning to understand. Gravity is the unseen force that shapes our universe, its reach extending from the tiniest particles to the most distant galaxies. It's not only responsible for the orbits of planets and the trajectories of comets, but also governs some of the most spectacular phenomena in the cosmos, such as gravitational lensing. This phenomenon occurs when light from far-off objects is bent and distorted by the presence of massive bodies like galaxies or galaxy clusters. This bending acts like a cosmic magnifying glass, allowing scientists to observe galaxies and stars that would otherwise remain hidden from our view. It is one of the many ways gravity reveals the hidden wonders of the universe, stretching from the very fabric of space and time itself to the deepest corners of the cosmos. On both the local and cosmic scales, gravity is more than just a force. It's a sculptor, shaping the structure and evolution of the universe. It binds stars into galaxies, galaxies into clusters, and holds entire cosmic structures together. From the moment of the Big Bang to the present day, gravity has been at the center of this ever-unfolding story, guiding the formation of everything we see and even things we cannot yet see. Gravity is the invisible hand that choreographs the vast, intricate dance of the universe, its pull leading to the creation of some of the most complex and beautiful structures ever known to science. Two prominent theories help explain gravity's role in the universe: Newtonian gravity and Einstein's theory of general relativity. These two perspectives, though different, offer complementary insights into how gravity works. In the Newtonian view, gravity is treated as a force, one that acts across space and draws masses toward one another, like an invisible string pulling objects in its grasp. The strength of this force depends on two factors: the size of the masses involved and the distance between them. Newton's equations are incredibly useful, allowing us to predict the motion of planets, comets, and even objects on Earth with remarkable precision. However, in the early 20th century, Albert Einstein fundamentally altered our understanding of gravity with his theory of general relativity. Rather than seeing gravity as a force acting across space, Einstein proposed that gravity arises from the curvature of space and time itself, caused by the presence of mass. To understand this idea, picture a stretched out sheet with a heavy ball placed in the center. The ball causes the sheet to sag, creating a dip. Now imagine smaller objects placed on the sheet. They will naturally roll toward the ball, not because there is an invisible string pulling them, but because the sheet itself is curved. In the same way, massive objects cause space-time to bend, and this curvature alters the paths of objects moving through it. This insight is why planets orbit stars. What we perceive as gravitational attraction is really a result of the bending of space and time itself. One of the most remarkable consequences of general relativity is its prediction that gravity doesn't just bend space, it also distorts time. Near a massive object, time itself slows down when compared to areas farther away. This concept, so different from the constant, unchanging nature of time in Newton's framework, has profound implications for both our understanding of the universe and the ways we experience it. For example, astronauts aboard a spaceship near a massive star would experience time differently than people on Earth, where time would pass at a faster rate. This slowing of time, known as gravitational time dilation, is an effect that only general relativity can predict and explain. Furthermore, general relativity helps explain phenomena that Newtonian physics cannot, such as the bending of light around massive objects. This bending of light, first observed during solar eclipses, is another piece of evidence for Einstein's theory. When light passes near a massive object, such as a star or galaxy, its path is altered. This phenomenon, known as gravitational lensing, allows astronomers to peer deeper into the universe than they otherwise could, using the gravity of massive objects to reveal distant galaxies and cosmic structures that are billions of light years away. In the Newtonian model, gravity is simply a force between masses, pulling them toward each other across space. In contrast, Einstein's general relativity reframes this view, presenting gravity as a consequence of mass causing space and time to curve. This shift in perspective offers not only a more comprehensive understanding of how gravity operates, but also allows for more accurate predictions of how objects move in extreme conditions, such as near black holes or at speeds approaching the speed of light. The way gravity shapes the universe is awe-inspiring. It governs everything from the most mundane motions, like the fall of an apple from a tree, to the grandest events, like the collision of galaxies. Gravity binds stars into galaxies and influences the very formation of planetary systems. Imagine the Earth, for instance, locked in an eternal orbit around the Sun. This motion, which would otherwise send our planet flying into space, is kept in check by the Sun's immense gravitational pull. It's a delicate balance. The Earth is constantly trying to move forward in space, but the Sun's gravity pulls it inward, ensuring the Earth remains in a stable, predictable orbit. At a more grandiose scale, gravity is the driving force behind the formation of galaxies themselves. When countless stars are drawn together by their collective gravitational pull, they can collapse clouds of gas and dust, triggering the birth of new stars. Gravity also governs the structure of galaxies, causing some stars to be pulled closer together while others are pushed apart. Through these interactions, galaxies evolve, growing larger and more complex over time. The impact of gravity on the cosmos is profound, shaping not just the movements of celestial bodies, but also the very structure of space itself. Every interaction between two objects, whether it's a comet passing by a planet or two binary stars orbiting one another, is a direct manifestation of gravity at work. The delicate relationships between these objects, from the smallest moons to the largest clusters of galaxies, all owe their existence to gravity's unwavering pull. The universe, with all its chaos and beauty, is held together by this invisible force, which maintains a kind of cosmic harmony in the face of vast, unyielding forces. One of the most fascinating and visually stunning effects of gravity is gravitational lensing. This occurs when a massive object, like a galaxy or a cluster of galaxies, warps the space around it, bending the path of light coming from distant objects. Imagine a bowling ball sitting in the center of a stretched-out sheet. The ball creates a dip, and anything placed near it will roll toward the ball, influenced by the curvature. In a similar manner, the immense gravitational field of a massive body distorts the path of light as it travels toward Earth or a telescope. This bending effect can magnify light sources, making distant galaxies appear brighter and more detailed, offering astronomers a unique tool to study objects billions of light years away. Gravitational lensing also has the incredible ability to provide insights into the nature of dark matter, an invisible, mysterious substance that makes up a significant portion of the universe's mass. Because dark matter doesn't emit light, it's difficult to detect directly. However, the gravitational effects of dark matter can be seen through lensing as it distorts the light from background galaxies. This enables scientists to map the distribution of dark matter in galaxies and clusters, shedding light on one of the most profound mysteries of modern cosmology. In essence, gravity is far more than just a force. It is the architect of the cosmos, shaping the very structure of space and time. From the formation of galaxies to the bending of light, gravity is at the heart of the universe's most awe-inspiring phenomena, offering an ever-deepening understanding of the nature of the universe itself. Gravitational lensing is not merely a fascinating celestial phenomenon. It holds the key to unlocking many of the universe's deepest mysteries. It has become a vital tool in astrophysical research, helping us peer into the hidden regions of the cosmos. Despite its name, dark matter is invisible, offering no direct signal through light or radiation. And yet, its existence can be inferred by studying the bending of light caused by massive objects. This bending, known as gravitational lensing, allows astronomers to trace the presence of dark matter across vast stretches of space. By observing how light from distant stars and galaxies is distorted as it passes through or near massive objects like clusters of dark matter, scientists can effectively map out its distribution in the universe. What makes gravitational lensing so important is the way it allows scientists to probe areas of space that would otherwise remain beyond our reach. It offers an indirect yet reliable method to study dark matter, a substance that makes up approximately 85% of the mass of the universe, yet remains invisible and poorly understood. Through lensing, scientists don't just observe a cosmic phenomenon, they gather vital information about the fundamental building blocks of the universe itself. As they analyze the distortions in light, they gather clues about the nature of dark matter, a substance that could potentially reshape our understanding of gravity and the evolution of the cosmos. Moreover, gravitational lensing doesn't just help us identify the invisible. It has another captivating aspect. The phenomenon often produces multiple images of the same distant astronomical object. This occurs when the light from a galaxy or star is bent so intensely by an intervening massive object, such as a black hole or galaxy cluster, that it creates several images of the original source. This has profound implications for our understanding of distance and time. For example, these multiple images of a distant object might appear at different times, giving scientists the ability to observe the effects of gravitational lensing over time and space. As researchers uncover these multiple images, they reveal more about the underlying structure of the universe, challenging and refining our comprehension of the cosmic fabric. Incorporating gravitational lensing into their work, astronomers are uncovering layers of cosmic history that traditional observation methods could easily miss. The distortion of light provides an entirely new perspective on the universe, allowing scientists to observe distant objects in a way that transcends the limitations of conventional telescopes. This effect acts as a cosmic magnifying glass, revealing hidden galaxies, stars, and other astronomical phenomena that were once out of sight. As researchers continue to exploit this powerful tool, they are gaining new insights into the universe's structure and history, deepening our understanding of how cosmic forces operate on grand scales. However, the lensing effect does not just enrich our view of the cosmos, it also has the potential to reshape our entire understanding of fundamental forces. This, in part, ties into some of the most pressing questions in astrophysics and theoretical physics, such as the mysteries surrounding gravity itself. Gravitational anomalies, particularly those that defy the predictions of general relativity, have been a source of intrigue for decades. General relativity, which describes how massive objects warp the fabric of space and time, has long been our best theory for understanding the effects of gravity. Yet strange gravitational phenomena continue to emerge, suggesting that our understanding of the universe may be incomplete. One such anomaly is the surprising acceleration of galaxies, a behavior that defies conventional expectations. According to general relativity, galaxies should slow down as they move further from the center of their respective clusters. However, many galaxies appear to be moving much faster than they should, given the visible matter present. The most plausible explanation for this is the existence of dark matter, an invisible substance that exerts gravitational forces helping to hold these galaxies together. Yet, despite compelling evidence for the presence of dark matter, it remains elusive. We can infer its existence based on gravitational effects, but its true nature and composition are still a mystery. Moreover, some of the gravitational anomalies could suggest the existence of new forces or physics beyond our current models. This opens up the possibility of a new chapter in theoretical physics, one that might unify gravity with quantum mechanics. If such a theory were to emerge, it could drastically alter our view of the universe and the laws that govern it, laying the groundwork for a more complete understanding of the cosmos. These gravitational anomalies are not just puzzles waiting to be solved, they represent the frontiers of modern physics. With each new observation, scientists are forced to reevaluate existing theories that seeking deeper explanations for the forces shaping the universe. These anomalies are in essence invitations to explore new dimensions of reality and the fundamental forces that govern everything from subatomic particles to the largest structures in the universe. As we look ahead, astrophysics finds itself on the cusp of a major transformation, largely due to a wave of groundbreaking technological advancements. One of the most promising developments is the next generation of telescopes, which are designed to capture clearer, more detailed images of distant celestial objects. These new telescopes, many of which are space-based, are equipped with cutting-edge sensors that allow astronomers to observe a broader spectrum of wavelengths. This expanded range of detection will enable scientists to explore phenomena that were previously invisible to optical telescopes, including dark matter, exoplanets, and the faintest galaxies. The potential of these advanced telescopes cannot be overstated. They promise to reveal more than just distant stars and galaxies. They will allow scientists to investigate the very building blocks of the universe, shedding light on the processes that have shaped the cosmos since its inception. By observing celestial objects in previously unseen wavelengths, astronomers will gain a deeper understanding of cosmic events such as supernovae, black hole mergers, and the formation of galaxies. These observations will likely open new windows into the history and future of the universe. Another exciting frontier in astrophysics is the growing role of artificial intelligence and machine learning in data analysis. With the vast amounts of data generated by modern telescopes and space observatories, human researchers face an overwhelming challenge. AI and machine learning algorithms are being used to sift through these massive data sets, identifying patterns and anomalies at speeds far beyond human capabilities. These tools not only make the discovery process faster and more efficient, but they also enable astronomers to focus on the most promising leads, accelerating the pace of scientific progress. Machine learning models can process enormous data sets and make predictions about astronomical phenomena, all while uncovering hidden trends that might have been missed by human researchers. This capability is crucial as the volume of data continues to grow exponentially. By using these technologies to identify promising signals, astronomers are able to make breakthroughs more efficiently than ever before. These tools represent a transformative shift in how we conduct research, opening new possibilities for discoveries and enabling scientists to explore previously uncharted areas of space. Equally significant is the advancement of gravitational wave astronomy. The detection of gravitational waves, ripples in space-time caused by the acceleration of massive objects like black holes or neutron stars, has opened up a completely new avenue of exploration. These waves provide a unique opportunity to study cosmic events that cannot be observed using traditional electromagnetic signals. Instruments like the Laser Interferometer Gravitational Wave Observatory, LIGO, are already allowing scientists to detect these faint signals, offering a new way to explore the most extreme regions of the universe. Gravitational wave astronomy has the potential to validate many aspects of existing theories in physics and astrophysics, while simultaneously challenging long-held assumptions. By studying the waves produced by black hole mergers or neutron-star collisions, scientists are gaining insights into the behavior of matter and energy in some of the universe's most extreme environments. These discoveries are not only confirming aspects of general relativity, but they are also providing new information about the properties of black holes, the nature of space-time, and the overall structure of the universe. As these technologies continue to evolve, they will undoubtedly expand our understanding of the cosmos. The future of astrophysics is rich with possibility, as scientists harness the power of advanced telescopes, AI, and gravitational wave detectors to explore the unknown. With each new breakthrough, we are drawing closer to answers that have eluded us for centuries, while also uncovering new mysteries that will inspire future generations of researchers to continue the quest for knowledge. Advancements in materials science are playing a pivotal role in transforming space exploration. The development of innovative, lightweight materials combined with enhanced sensors is not just improving spacecraft design, but is expanding our ability to venture into deeper, more distant realms of the cosmos. These innovations open up new possibilities for exploring asteroids, comets, and the outermost planets, each mission offering a potential treasure trove of information that could shed light on the origins of our solar system. By delving into these ancient cosmic bodies, we unlock secrets about the early days of planetary formation, revealing how the solar system as we know it came to be. Additionally, the cutting-edge realm of quantum technology is beginning to make waves in astrophysics. Researchers are leveraging the unique properties of quantum computing to model and simulate complex astrophysical phenomena. With its ability to process vast amounts of data simultaneously, quantum computing allows scientists to simulate cosmic events with greater accuracy and on a scale that was once unimaginable. By simulating the behaviors of galaxies, black holes, and other large-scale cosmic structures, we gain insight into the fundamental forces shaping the universe. This advancement in computational power is enabling predictions and simulations of cosmic dynamics that bring us closer to a complete understanding of the universe's evolution. At the heart of these technological breakthroughs lies the confluence of advanced telescopes, artificial intelligence, gravitational wave detectors, and quantum technologies. Together, they are transforming the landscape of astrophysics. This rich array of tools not only enhances our ability to observe the universe in unprecedented detail, but it also allows us to make deeper, more accurate inferences about its fundamental workings. By weaving these innovations together, scientists are now able to probe the mysteries of the universe with greater precision, uncovering hidden layers of knowledge that were once out of reach. This integration of new technologies is expanding the frontiers of human discovery, revealing new truths about the cosmos and reshaping our understanding of the universe at large. The role of computational power cannot be overstated in this ongoing transformation. Think of computational power as the ultimate tool in a scientist's toolbox, constantly evolving and growing more sophisticated. This ever-expanding computational capability has opened the door to simulations and analyses that were once thought to be beyond our reach. A prime example of this can be seen in the study of supernovae. These massive stellar explosions, which occur at the end of a star's life cycle, involve processes that are so complex that they defy easy explanation. Through high-powered simulations, astrophysicists can model the collapse of a star and its subsequent explosion, taking into account an enormous number of variables, such as temperature, pressure, and the interaction between fundamental particles. These simulations provide an invaluable glimpse into the heart of one of the universe's most dramatic and awe-inspiring phenomena. Moreover, the vast quantities of data collected by telescopes and space missions provide another compelling example of how computational power is reshaping astrophysics. Telescopes gather images and spectra from distant galaxies, stars, and other celestial bodies, resulting in enormous datasets that can easily reach petabytes in size. Without the aid of advanced computing systems, it would be nearly impossible to process and analyze such massive amounts of information. This is where machine learning and artificial intelligence come into play. These technologies can sift through enormous datasets at lightning speed, identifying patterns and extracting insights that might take human researchers years to uncover. The synergy of computational power and AI is helping to reveal subtle cosmic phenomena that were previously undetectable. Computational technologies also facilitate the modeling of cosmic structures on an unprecedented scale. From simulating the formation of galaxies to modeling the dynamics of the universe's expansion, these simulations allow researchers to explore how the universe evolves over time. By comparing these theoretical models with real observational data, scientists are able to refine their understanding of the cosmos. One of the most profound mysteries being explored through these models is the nature of dark matter and dark energy, two of the most elusive and enigmatic components of the universe. As computational power advances, the tools and methodologies used to model these phenomena continue to evolve, helping to bring us closer to understanding the forces that govern the universe's expansion and structure. As computational technology continues to evolve, it is driving collaboration across disciplines. Astrophysicists are now working alongside data scientists, engineers, and even climate scientists, blending their expertise to tackle some of the most profound questions of our time. This interdisciplinary collaboration not only leads to new insights, but also fosters a deeper understanding of the universe, providing a more nuanced view of its complex and multifaceted nature. The advancements in computational power not only improve the precision of current research, but also open up new avenues of exploration, allowing scientists to venture further into the unknown. Astrophysics stands on the precipice of a transformative era, with groundbreaking discoveries poised to alter our understanding of the cosmos. Among the most tantalizing areas of research is the study of dark matter and dark energy, which together account for approximately 95% of the universe's total mass energy content. Despite their dominance, both remain shrouded in mystery. Dark matter is thought to act as an invisible scaffolding that influences the formation and movement of galaxies, while dark energy is believed to be responsible for the accelerated expansion of the universe. As new, more powerful observational tools come online, scientists are hopeful that they will be able to gather data that will reveal the true nature of these enigmatic components, potentially leading to one of the most significant discoveries in modern science. Simultaneously, the search for exoplanets, planets that exist outside of our solar system, is entering an exciting new phase. Advances in observational techniques are allowing scientists to peer deeper into distant star systems, studying the atmospheres and surface conditions of planets orbiting other stars. These exoplanet surveys are helping to identify planets that lie within the habitable zone, where conditions might be conducive to life. The discovery of Earth-like planets in such zones is one of the most exciting prospects in modern astronomy, as it could answer one of the most profound questions of all: are we alone in the universe? Another area of tremendous potential is the study of gravitational waves. Ripples in the fabric of space-time, caused by massive cosmic events such as black hole mergers. These waves carry information about the most extreme environments in the universe, providing a new way to observe and understand phenomena that were previously invisible. As the sensitivity of gravitational wave detectors improves, scientists are poised to make new discoveries that could further our understanding of the fundamental forces of the universe and the extreme physics governing black holes and neutron stars. Exploring our own solar system continues to provide valuable insights as well. Missions to Mars, for example, aim not only to search for signs of ancient life, but also to lay the groundwork for future human exploration. At the same time, missions targeting the icy moons of Jupiter and Saturn, such as Europa and Enceladus, are exploring the possibility that these frozen worlds harbor subsurface oceans that could support life. These discoveries, whether they are about the origins of life on Earth or the potential for life elsewhere, could have profound implications for our understanding of the building blocks of life and our place in the universe. As technological advancements continue to unfold, the future of astrophysics looks brighter than ever. With each new discovery, we are peeling back the layers of the universe, revealing its most profound secrets and expanding the horizons of human knowledge. The journey ahead is full of potential, and the cosmos is waiting to be explored like never before. In the coming years, we are poised to make significant strides in understanding the fundamental forces of nature. With advancements in experimental techniques and cutting-edge observations of high-energy particles in space, the path ahead promises groundbreaking revelations. The exploration of cosmic rays, for example, could unveil new particles and forces, offering a fresh perspective on the nature of the universe. This research may bring us closer to unifying the various physics theories that currently exist, bringing together forces like gravity, electromagnetism, and the strong and weak nuclear forces into a single, coherent framework. The future of astrophysics holds immense potential, with each new discovery acting as a stepping stone towards unveiling the deepest mysteries of the universe. The next few decades may very well be defined by these profound revelations, each breakthrough building on the last and significantly shifting our understanding of the cosmos. Not only will these discoveries reshape science, but they will also profoundly influence our philosophical outlook on existence itself. As technology continues to advance, our creativity will unlock new frontiers, and the universe, with all its vastness, may reveal wonders we have yet to imagine. One of the most exciting trends in modern astronomy is the rise of citizen science, which is transforming the way research is conducted. Citizen science involves the active participation of the public, enthusiasts, students, and amateurs alike in scientific endeavors, enabling them to contribute meaningfully to ongoing research projects. This democratization of knowledge has vastly expanded the scope of what can be achieved in the field. Gone are the days when astronomical discoveries were the exclusive domain of professional scientists and astronomers. Now, ordinary individuals can take part in the exploration of the universe, making significant contributions along the way. Consider the vastness of the universe, a seemingly infinite expanse filled with countless stars, galaxies, and celestial phenomena. The sheer scale of it all is staggering, and no single group of researchers could possibly explore it all on their own. This is where citizen scientists come in. They play a crucial role by analyzing enormous volumes of data generated by powerful telescopes and satellites. For instance, many citizen scientists assist in identifying exoplanets by examining light curves, which reveal subtle variations in the brightness of stars as planets pass in front of them. By spotting these dips in light, volunteers help uncover new worlds, expanding our knowledge of distant planetary systems. Citizen scientists also contribute to other important areas of research. Amateur astronomers, for example, provide invaluable data during rare astronomical events, such as comet sightings or the observation of supernovae. Their contributions often help to fill in gaps in the data, allowing professional astronomers to make more accurate and timely discoveries. This active involvement in the scientific process not only accelerates the pace of discovery, but also helps cultivate a sense of wonder and excitement about space. It brings the cosmos closer to the public, making science more accessible and relatable. Through citizen science, a profound connection is formed between the scientific community and the general public. When people are given the opportunity to engage directly in research, they gain a deeper understanding of the universe and the methods scientists use to study it. This fosters a sense of shared ownership and responsibility in the quest for knowledge, creating a global community of informed individuals who are passionate about space exploration. Beyond citizen science, the role of data in modern astronomy cannot be overstated. The landscape of astronomical research has been dramatically altered by the rise of data-driven exploration. In the past, most knowledge about the universe was gathered through direct observation using telescopes and scientific instruments. While these methods are still fundamental, the sheer volume and diversity of data available today has opened up new avenues for exploration. With the advent of more powerful telescopes, satellite missions, and advanced computational tools, astronomers can now collect vast amounts of data from multiple sources across the electromagnetic spectrum. This includes wavelengths of light that are invisible to the human eye, such as infrared, ultraviolet, and radio waves. These data-rich observations provide invaluable insights into the nature of celestial objects, offering a much more nuanced understanding of the universe. By combining these observations with sophisticated algorithms and machine learning techniques, scientists can identify patterns, anomalies, and correlations that would be nearly impossible to discern by traditional means. For example, automated systems can process massive data sets to detect cosmic phenomena like supernovae, gravitational waves, or even the faint signatures of distant galaxies. Such discoveries deepen our understanding of cosmic events and help us map the large-scale structure of the universe. In addition to detecting and identifying new cosmic phenomena, data-driven methods have also led to the creation of sophisticated simulations and models. These tools allow scientists to recreate complex events in the cosmos, such as the formation of galaxies, the dynamics of black holes, or the collision of neutron stars. By inputting real-world data into these models, Researchers can simulate various cosmic scenarios, gaining deeper insights into the forces and conditions that shape the universe. These simulations not only serve as powerful tools for testing existing theories, but also offer a way to predict new phenomena, like helping scientists stay ahead of the curve in their research. Another field that has greatly benefited from data-driven exploration is astrobiology. The search for life beyond Earth has been accelerated by data collected from planetary missions and space telescopes. By analyzing the characteristics of exoplanets, planets that orbit stars other than our own, scientists are able to assess their potential habitability. They use statistical models to determine whether these planets lie within the habitable zone, where conditions might be right for liquid water to exist. This information helps focus exploration efforts on the most promising candidates, guiding future missions to planets that may harbor the building blocks of life. The combination of big data and advanced analytical techniques has revolutionized our ability to explore the universe. It has expanded the scope of our inquiry, allowing us to ask deeper questions about the origins of the cosmos, the nature of dark matter, the possibility of extraterrestrial life, and much more. As our technological capabilities continue to improve, the insights we gain from data-driven research will only deepen our understanding of the vast and complex universe we inhabit. Every astronomical discovery not only adds to the body of scientific knowledge, but also has profound philosophical implications. These discoveries constantly reshape our understanding of humanity's place in the cosmos, pushing the boundaries of what we know about our existence. Each new finding serves as a piece of a larger puzzle, slowly revealing a picture that challenges our sense of identity and significance in the grand scheme of things. Take, for example, the discovery of exoplanets, planets that orbit stars beyond our own. In the past few decades, scientists have identified thousands of these distant worlds, and the more we learn about them, the more we realize how vast the universe is. Many of these exoplanets lie within the habitable zone of their stars, where conditions might allow liquid water to exist, an essential ingredient for life as we know it. The mere possibility that life could exist elsewhere in the universe has profound philosophical implications, forcing us to reconsider our place in the cosmos. Are we alone, or is life a more common phenomenon than we ever imagined? As our understanding of the universe expands, we are not only advancing science, but also engaging in a deep, ongoing conversation about the nature of existence. With each new discovery, we are forced to grapple with questions about the origins of the universe, the nature of consciousness, and our role in the grand cosmic narrative. It is a conversation that touches on both the scientific and the philosophical, offering a rich tapestry of insights that continue to shape our view of the world and our place within it. The exploration of the cosmos has always been an endeavor that challenges the limits of human understanding, compelling us to reflect on our place in the vastness of the universe. It is a journey that transcends the boundaries of science and philosophy, urging us to rethink the very nature of existence. Mapping cosmic structures such as galaxies and galaxy clusters provides a vivid illustration of the unimaginable scale and complexity of the universe. Through these observations, astronomers unveil the intricate web of cosmic forces that shape the cosmos, from the smallest of celestial bodies to the largest galactic superstructures. By understanding these structures, we are reminded of our own fragility and the fleeting nature of our existence, yet also of the profound connection we share with the universe. The discovery of phenomena like cosmic microwave background radiation offers crucial insights into the early universe, allowing us to peer back in time to an era billions of years ago when the universe was in its infancy. This radiation serves as a relic from the Big Bang, providing evidence that the universe began in a hot, dense state and has been expanding ever since. In reflecting upon this, we are reminded that our story is part of a much larger narrative, one that spans eons. This realization opens the door to deep philosophical contemplation about the origins of everything, not only our own existence, but the entire cosmic structure that surrounds us. As we uncover more of the universe's secrets, we encounter discoveries that challenge our very perception of reality. One such revelation came with the detection of gravitational waves, ripples in space-time created by the collision of massive objects like black holes. These phenomena serve as a reminder of the immense forces at work in the universe, operating on scales and in ways that are often beyond our comprehension. Gravitational waves, for instance, occur as objects of enormous mass accelerate through space, distorting the very fabric of space-time itself. To imagine such an event, the collision of two black holes, is to realize that the universe operates in a realm far beyond human experience. This knowledge challenges the centuries-old assumption that humanity holds a central place in the cosmos, suggesting instead that we are but one small chapter in a much grander story, unfolding across space and time. In addition to these awe-inspiring events, the continued exploration of distant galaxies, the study of dark matter, and the ongoing observation of cosmic expansion all help to deepen our understanding of the universe. As astronomers probe the farthest reaches of the cosmos, every new discovery not only reshapes our scientific knowledge, but also encourages a profound shift in how we view ourselves. The more we learn about the universe, the more we realize that our understanding of reality is constantly in flux. Each new piece of information, whether it concerns the nature of dark energy or the possibility of other forms of life beyond Earth, invites us to question our assumptions about existence and what it means to be human. This journey into the unknown is not just about collecting facts or discovering new phenomena, it is about reshaping our worldview. As our understanding of the cosmos deepens, it fosters a renewed sense of wonder and curiosity, urging us to ask questions about our place in the universe, the connections we share with other forms of life, and our responsibilities as stewards of our own planet. The more we explore, the more we realize that humanity is but one piece of a much larger, interconnected cosmic puzzle. With every new discovery, we are called upon to not only explore the universe, but also to protect the delicate balance of life on Earth. Throughout history, our relationship with the cosmos has undergone a profound evolution. Each significant breakthrough has shifted the way we perceive our place in the universe, often challenging long-held beliefs and reshaping entire worldviews. One of the most pivotal moments in this journey came with the work of Nicolaus Copernicus. In the early 16th century, Copernicus proposed that the sun, rather than the Earth, was at the center of our solar system. This heliocentric model, though controversial at the time, fundamentally altered the course of science, triggering a paradigm shift that forever changed humanity's understanding of the cosmos. The implications were far-reaching, as it challenged the geocentric model that had been accepted for centuries and placed humanity's home, Earth, in a less central, more humble position within the solar system. Following Copernicus, the work of Johannes Kepler further transformed our understanding of planetary motion. Kepler discovered that the orbits of planets were not perfect circles, but rather ellipses, a revelation that provided a more accurate description of the solar system. Kepler's insights helped lay the foundation for classical mechanics and revolutionized our approach to understanding motion in both the heavens and on Earth. His work also spurred a shift towards empirical observation and mathematical precision in the sciences, encouraging the development of a more rigorous, systematic approach to studying the natural world. In the 17th century, Isaac Newton's groundbreaking work in physics brought yet another dramatic shift in our understanding of the cosmos. Newton's laws of motion and universal gravitation unified the study of celestial and terrestrial motion, providing a framework for understanding the movement of objects on Earth and the forces that govern their motion. With the advent of Newtonian physics, humanity began to view the universe as a vast, interconnected machine, governed by predictable laws. This new perspective opened the door to further exploration and laid the groundwork for future scientific advancements, including the study of space exploration and astrophysics. As the centuries progressed, the 20th century brought yet another radical shift in our understanding of the cosmos. Albert Einstein's theory of general relativity revolutionized the way we think about gravity and space-time. Unlike Newtonian physics, which treated gravity as a force acting between masses, Einstein's theory described gravity as the curvature of space-time caused by the presence of mass and energy. This radical new perspective not only provided a more accurate description of large-scale cosmic phenomena, but also deepened our understanding of black holes, time dilation, and the expanding universe. Einstein's work fundamentally altered our understanding of the nature of reality and encouraged a more sophisticated inquiry into the fabric of the cosmos. In the mid-20th century, the discovery of cosmic microwave background radiation provided a compelling piece of evidence for the Big Bang theory. This discovery, which revealed faint radiation left over from the early moments of the universe, solidified our understanding of the universe's origins and evolution. It was a watershed moment in cosmology, not just for astronomers, but also for philosophers, theologians, and thinkers from all disciplines. The implications of the Big Bang theory prompted a re-examination of time, existence, and the nature of creation itself, as it provided a scientific explanation for the beginning of the universe, a topic that had previously been the domain of religious and philosophical inquiry. Each of these discoveries has marked a significant cultural and intellectual shift, one that has moved humanity away from an Earth-centered view of the universe and towards a more universal, interconnected perspective. And yet, even as we unravel the mysteries of dark matter, dark energy, and the possibility of parallel universes, we stand at the precipice of yet another paradigm shift. As our understanding of the cosmos continues to evolve, we are constantly reminded that the universe is far more vast, complex, and mysterious than we could have ever imagined. This ongoing journey of exploration will undoubtedly continue to shape our identities and our understanding of reality itself, offering new insights into the fundamental questions of existence. At the same time, cultural interpretations of the cosmos continue to influence scientific inquiry. Throughout history, different cultures have imbued the night sky with meanings far beyond its physical reality, interpreting celestial bodies through mythologies, religious beliefs, and philosophical frameworks. These cultural narratives have shaped the questions scientists ask, the methods they use, and the way they interpret their findings. In ancient civilizations, for example, the stars were not just distant points of light, but part of a divine order, influencing everything from agriculture to navigation. Observing the heavens was a sacred practice, and understanding celestial movements was crucial for the survival of these societies. In the modern era, our desire to explore the cosmos is often driven by a quest for meaning and purpose. Scientists today are not only seeking data and answers to scientific questions, but are also driven by a collective sense of wonder and curiosity about the universe. The pursuit of knowledge about the cosmos is deeply intertwined with humanity's age-old quest for meaning, as we continue to ask profound questions about the origins of the universe, the possibility of life beyond Earth, and the ultimate nature of existence itself. In this sense, our exploration of the universe is not just a scientific endeavor, but a deeply human one, guided by both our intellect and our imagination. Space exploration has long been a subject of intrigue, but different cultures approach this profound frontier with varying perspectives and attitudes. Some cultures view space exploration as a crucial step for humanity's advancement, a way to push the boundaries of our knowledge and capabilities. For others, however, this venture into the unknown is met with more caution. There is a strong emphasis on preserving the integrity of humanity and safeguarding the environment. Such diverse cultural attitudes can deeply influence the way space programs are funded, the nature of international collaborations, and the level of public enthusiasm for scientific endeavors. These differing viewpoints are not simply incidental. They directly impact the development and direction of scientific projects, often determining which missions are prioritized and how resources are allocated. In many ways, the relationship between culture and scientific inquiry is one of mutual influence. Cultural narratives shape the kinds of questions scientists pursue, what is deemed valuable or worth investigating, and what challenges are seen as worthy of exploration. At the same time, the discoveries that emerge from the scientific community can alter cultural beliefs, sparking new ways of thinking about the universe and our place within it. This reciprocal relationship is continuously evolving, with each breakthrough nudging both science and culture into new realms of possibility. Science, therefore, cannot be viewed as merely a technical or abstract endeavor. It is a deeply human pursuit, interwoven with our cultural identities, values, and collective aspirations. As we look ahead, the future of science promises revelations that could fundamentally shift the way we perceive the very nature of existence itself. One of the most captivating frontiers of this exploration is the enigma of consciousness. At present, we understand consciousness as a byproduct of the brain's complex activity, a phenomenon that emerges from the intricate interactions of neurons and synaptic connections. But what if consciousness is not just an incidental result of physical processes? What if it is something much deeper, an integral component of reality itself? This tantalizing possibility suggests that consciousness might not merely reflect the brain's activity, but might play an active role in shaping the universe, influencing the very fabric of existence. As research in neuroscience and physics progresses, new insights could emerge that bridge the gap between mind and cosmos, offering a revolutionary understanding of consciousness. Simultaneously, the field of physics may soon uncover entirely new dimensions of reality, expanding our understanding of space and time far beyond our current comprehension. Imagine for a moment that the 3 dimensions of space we experience daily are not the full extent of the universe's structure. What if additional dimensions exist, hidden from view but crucial to understanding the forces and particles that govern the cosmos? This concept challenges our most fundamental assumptions about the nature of reality, suggesting that we may be living in a universe much more complex than we realize, where hidden variables could influence everything from the behavior of elementary particles to the expansion of the universe itself. Cosmology, too, holds the promise of profound revelations. Dark matter and dark energy, which together constitute around 95% of the universe, remain elusive and poorly understood. These mysterious forces seem to shape the structure and dynamics of the universe, yet we cannot directly observe them. In the future, breakthroughs in cosmology may finally illuminate their true nature, answering fundamental questions about the origins, structure, and ultimate fate of the universe. Such discoveries could have far-reaching implications, reshaping our understanding of the cosmos and altering our sense of scale and place within it. They may even challenge the very concepts of time and space, suggesting that our universe is far more intricate and interconnected than we could have ever imagined. As scientists continue their search for extraterrestrial life, the implications of such a discovery are profound. Whether it is microbial life on distant planets or even intelligent civilizations elsewhere in the galaxy, the confirmation of extraterrestrial life would force humanity to reconsider its unique position in the cosmos. It would spark a series of philosophical and scientific questions about the nature of life itself. What does it mean to be alive? Are we truly alone in the universe, or is life a more common phenomenon than we have previously thought? These questions would undoubtedly lead to a reevaluation of the very foundations of biology, philosophy, and theology, encouraging us to think more broadly about our role in the universe. At the microscopic scale, advancements in quantum mechanics could also lead to astonishing revelations. The behavior of particles at the quantum level is already known to be strange and counterintuitive, with phenomena such as superposition and entanglement challenging our conventional understanding of reality. As we delve deeper into the quantum world, new principles could emerge that radically alter our understanding of causality, time, and space. Could it be that the very fabric of reality is not as solid and predictable as we once believed? Quantum mechanics might eventually unveil a universe much stranger and more interconnected than we are capable of fully grasping today. These avenues of scientific inquiry are more than just intellectual pursuits. They are keys to a broader understanding of our existence in a vast and complex universe. Each discovery, no matter how small, has the potential to alter our worldview, forcing us to reconsider fundamental questions about life, the universe, and everything in between. In this ongoing quest for knowledge, we must not lose sight of the deeper philosophical reflections that arise with each new breakthrough. What does it mean to be human in a universe that may hold secrets far beyond our current grasp? To navigate this journey of discovery, scientists must balance empirical evidence with theoretical conjecture. Empirical evidence, Knowledge gained through direct observation and experimentation forms the foundation of scientific progress. This tangible data allows scientists to validate or challenge theories and provides a framework for building new knowledge. On the other hand, theoretical conjecture involves imaginative ideas and models that extend beyond what is immediately observable. These hypotheses often arise from existing knowledge, but are designed to stretch the limits of our understanding, proposing explanations for phenomena that have yet to be fully explained. In scientific practice, this dynamic process begins with careful observation. Scientists gather data through precise measurements and experiments, looking for patterns or anomalies that might suggest new avenues of inquiry. From these observations, hypotheses are formed, tentative explanations that seek to answer the questions raised by the evidence. These hypotheses are then rigorously tested through experimentation, ensuring that they have a solid empirical foundation. Theories, however, are never static. As new data emerges, existing theories must be reevaluated. Some theories may be confirmed, others revised, and some may be discarded entirely if they no longer align with the available evidence. This process of constant refinement is one of the hallmarks of scientific inquiry. It is an ongoing journey of discovery, where each new finding leads to further questions, driving the evolution of knowledge. Science is not a static body of facts, but a dynamic, ever-evolving process that remains open to revision. It is through this willingness to embrace change and adapt to new evidence that our understanding of the universe grows deeper and more nuanced over time. This adaptability is what allows science to remain one of humanity's most powerful tools for exploring the unknown and uncovering the truths that lie hidden within the fabric of reality itself. Theoretical conjectures serve as guiding lights in the labyrinth of scientific discovery, offering not only hypotheses but also foresights into the vast unknown. They act as blueprints, sketching out potential phenomena yet to be observed, becoming a touchstone for future investigations. Imagine the raw power of these theoretical frameworks. They do more than just explain, they predict. If these predictions stand the test of observation, the theory becomes stronger, acquiring credibility. But if they don't align with reality, the theory becomes a springboard for further inquiry, prompting deeper questions and challenging established beliefs. In this way, science is an ever-evolving dialogue between what we can observe and what we theorize, each feeding into the other in a continuous loop. This relationship between theory and empirical evidence is not linear, but circular. Empirical findings offer new insights that refine existing theories, while theories suggest fresh avenues for exploration, pushing the boundaries of what we understand. Fields such as physics, biology, and cosmology are built on this dynamic partnership. Through this ever-tightening bond between theory and observation, scientists inch closer to a more comprehensive understanding of the universe. It is this synergy, this fluid balance between the abstract world of theory and the tangible world of evidence that drives scientific progress. It ensures that science is not just a theoretical pursuit, but also a grounded exploration, constantly tethered to the realities of the natural world. When it comes to communicating complex scientific ideas to the public, particularly those related to the cosmos, the challenge is clear. How can we make the incomprehensibly vast and complicated universe understandable without oversimplifying? The key lies in striking a balance, presenting intricate ideas in a way that is both accessible and compelling. One of the most effective ways to do this is through the use of relatable analogies. For example, explaining the expanding universe is often likened to inflating a balloon. As the balloon expands, the surface stretches, and galaxies like dots on that surface move further apart. This simple analogy helps audiences visualize the concept without requiring them to grapple with complex scientific terminology. Another critical approach involves breaking down sophisticated ideas into smaller, more digestible pieces. Instead of diving straight into high-level theories, it's important to first establish foundational knowledge that everyone can understand. For example, explaining the concept of gravity through everyday experiences, such as how objects fall to the ground or how planets orbit the sun, gives the audience a concrete starting point. Once they grasp these fundamental ideas, they are better equipped to tackle more abstract concepts like the role gravity plays in the formation of stars or the behavior of black holes. Visual aids play a crucial role in this process too. Diagrams, charts, and animations are invaluable tools for making abstract ideas more tangible. They simplify the complexity of cosmic phenomena, turning them into visual stories that can be easily understood. For instance, an animation of a supernova can vividly illustrate the explosive power of a star's death, showing how light and shock waves radiate outward, transforming what could be an incomprehensible concept into a dynamic visual experience. In this way, images become more than just decorative. They become integral to the learning process, drawing in viewers and helping them connect emotionally with the subject matter. Furthermore, integrating storytelling with visuals enhances the effectiveness of these educational strategies. Rather than just presenting data, a well-crafted narrative about the cosmos can pull viewers in, making the information more engaging and relatable. This approach allows complex ideas to unfold like a story, guiding the audience step by step through cosmic phenomena and their implications. Encouraging active participation through questions also enhances engagement. By posing thought-provoking questions and guiding audiences toward the answers, scientists and educators can create an interactive learning environment. This not only sparks curiosity, but also deepens the audience's interest and understanding, fostering a sense of personal discovery. Questions act as an invitation to engage with the subject matter, transforming passive learning into an active exploration. At the heart of all these strategies is the importance of clear, simple language. Using jargon-free, conversational language makes complex topics feel less daunting. The aim is to communicate not just facts, but the awe and wonder of the universe. When scientific discoveries are presented with enthusiasm and clarity, they spark a sense of wonder in the audience, making the universe feel more accessible and less intimidating. By bringing the mystery of space to life, we allow people to appreciate the beauty and complexity of the cosmos without getting lost in its complexities. Visualizations and simulations are indispensable in this endeavor. They transform abstract concepts into vivid, accessible images, enabling both scientists and the public to better understand phenomena that are otherwise too vast, too remote, or too abstract to comprehend. Consider the explosion of a supernova. This cataclysmic event, producing a fiery burst of energy and matter, is difficult to imagine without a visual representation. Through simulations, viewers can witness the event unfold in real time, watching the shockwaves ripple through space and observing how light expands outward across the universe. Such simulations help bridge the gap between theoretical physics and the visual experience, providing a much-needed anchor for understanding. Moreover, these visual tools allow for the representation of enormous, often counterintuitive scales, like the sheer size of galaxies or the vastness of the cosmic web. Imagine a simulation of the solar system where the distances between planets are depicted to scale. This visualization helps viewers grasp just how immense space is and how minuscule our solar system is in the grand scheme of things. It is one thing to hear that space is vast, but it is another thing entirely to see it represented in a way that brings this reality home. Simulations also serve as a powerful tool for scientific validation and hypothesis testing. For instance, when studying the formation of galaxies, scientists can create models based on current theories of gravity and matter. By observing how these simulated galaxies evolve, scientists gain insights into the processes that likely shaped our own Milky Way galaxy. In this sense, simulations don't just serve as a learning tool for the public, they are integral to scientific research itself. Animations, too, are vital for illustrating dynamic, ongoing processes that are difficult or impossible to capture through photographs alone. The motion of celestial bodies, the formation of stars, and the complex interplay of forces in a black hole are all phenomena that require dynamic, real-time visualizations to truly understand. Through animations, these processes become more than abstract theories. They become engaging, immersive experiences that draw audiences deeper into the mysteries of the universe. Documentaries and media as a whole play an indispensable role in this educational endeavor. Through stunning visuals, captivating narratives, and expert interviews, Documentaries bring the cosmos to life in ways that textbooks simply cannot. They provide a platform for scientists to share their discoveries with the public, transforming complex theories into compelling stories. When a documentary delves into the mysteries of space, exploring the life cycle of stars, the potential for extraterrestrial life, or the origins of the universe, it takes the viewer on a journey that extends far beyond Earth. These films do more than inform, they inspire. They provoke viewers to think critically about their place in the universe, to consider the nature of existence, and to appreciate the grandeur of the cosmos. Through accessible language, vivid visuals, and relatable analogies, documentaries can simplify even the most challenging topics. By turning these abstract ideas into stories, they allow viewers to see the universe in a way that feels both personal and profound. Ultimately, the power of documentaries lies in their ability to spark curiosity and wonder, fostering a deeper understanding of the universe, while also igniting a lifelong passion for exploration. In the rapidly evolving world of media and technology, the continuous updating of content is crucial. Platforms and outlets persistently refresh their material, keeping audiences informed with the latest scientific discoveries and advancements in fields such as astronomy and space exploration. This dynamic process does more than just relay information. It actively engages the public, keeping them connected to the pulse of modern knowledge. The collaborative nature of scientific study is evident in these updates. Experts, from astronomers to physicists, share their insights through documentaries, making the complex world of scientific inquiry more transparent. They demystify the often intricate process of research, showing how scientific knowledge is built through a combination of rigorous experimentation, observation, and theory. But the impact doesn't stop there. Documentaries do more than just educate. They spark public interest in space exploration and often serve as a critical tool in generating the support needed for scientific endeavors. A compelling film or documentary can ignite fascination with space missions, encouraging viewers to imagine the possibilities of human exploration beyond Earth's boundaries. In turn, this growing interest can lead to an increase in funding for research initiatives, fueling future projects that push the limits of human understanding. The excitement around space exploration can be contagious, inspiring a new generation of scientists, engineers, and astronomers who will one day carry the torch of discovery. By showcasing the thrilling endeavors taking place beyond our planet, media platforms become more than just information providers. They act as gateways to the universe, transforming the complex, sometimes abstract, concepts of space science into engaging and accessible narratives. These stories not only educate, but also motivate audiences to further explore the cosmos. Through the power of media, these cosmic adventures transcend the realm of experts, inspiring curiosity in everyday people. They serve as a bridge, connecting the scientific community with the general public, fostering a culture of wonder and respect for the vast mysteries of the universe. However, it is not enough to simply share information. Addressing misconceptions about the universe requires a multi-pronged approach that blends education, communication, and active engagement. The first crucial step is ensuring that the information being shared is clear and accurate. Fundamental scientific concepts must be articulated in a way that is easily understandable to a wide audience, from young students to older adults. This may involve breaking down complex ideas, such as the nature of gravity, the vastness of light years, or the intricate behavior of celestial bodies into relatable terms. Analogies from everyday life can be powerful tools in bridging the gap between advanced scientific knowledge and public understanding. Education plays an integral role in this process. By integrating astronomy and space science into the curriculum from an early age, we can foster a sense of wonder and curiosity about the universe. This approach not only enriches students' academic experiences, but also empowers them with the knowledge to critically engage with scientific ideas as they grow. Furthermore, this proactive integration of space science can lay the foundation for future generations who will embrace scientific thinking, question misconceptions, and challenge erroneous beliefs. Public outreach efforts also play an essential part in narrowing the gap between scientific communities and the wider public. Engaging documentaries, informative podcasts, and interactive exhibits in places like planetariums all provide accessible and enjoyable means for people to learn about space. Hands-on learning opportunities help spark interest and allow audiences to directly connect with the material. Equally important is when scientists, educators, and communicators make themselves available for discussions and public engagements. These interactions help address questions, clear up misunderstandings, and foster an environment of trust and openness. The rise of social media and popular science communication has further amplified the reach of accurate scientific information. Thoughtfully crafted explanations, infographics, and engaging storytelling about space discoveries can reach millions, allowing critical knowledge to spread more quickly and effectively. This direct engagement with the public also combats misinformation, offering clear and accessible insights into complex topics. However, it is crucial to remember that the goal isn't to dismiss people's beliefs, but to foster an open dialogue, helping them to better understand and navigate the vast world of scientific knowledge. Another important facet of addressing misconceptions is fostering critical thinking. Encouraging individuals to question, analyze, and seek evidence for themselves is an essential aspect of developing scientific literacy. It empowers individuals to sift through the noise of misinformation and discern fact from fiction. This practice doesn't just enhance individual knowledge, it cultivates a society that values informed, critical thinking and can appreciate the complexities of the universe. It builds resilience, enabling people to better evaluate the evolving information landscape. Equally important is the recognition that interdisciplinary collaboration is fundamental to enhancing public understanding of cosmic science. Think of the cosmos as an immense, intricate tapestry, each thread representing a distinct field of knowledge: physics, astronomy, philosophy, art, education, and beyond. When experts from these diverse disciplines come together, they weave a more comprehensive and engaging narrative about the universe. Space science, often perceived as daunting and filled with esoteric concepts, becomes more relatable when insights from various fields are brought into the conversation. For example, artists play a crucial role in visualizing distant galaxies, nebulae, and other celestial phenomena. Their work makes the wonders of the universe more tangible and emotionally resonant for the public. Likewise, educators and communicators can bridge the gap between scientific terminology and lay language while ensuring that the fundamental principles of space science are easily understood. This interdisciplinary synergy doesn't just enhance knowledge, it sparks creativity, encouraging new ways of thinking and problem solving. Furthermore, collaboration between different fields fosters innovative approaches to addressing the challenges of space exploration. For instance, when scientists collaborate with ethicists, they are better equipped to consider the broader implications of human space exploration on society. When psychologists contribute to the conversation, they help shape educational methods that cater to different learning styles, ensuring that more people can engage with space science in a way that resonates with them personally. This collective approach not only broadens our understanding of the cosmos, but also nurtures a sense of curiosity and exploration in individuals. The more we collaborate across disciplines, the more opportunities we create to challenge conventional wisdom, think critically, and inspire new ideas. By working together, scientists, educators, artists, and philosophers can provide a more holistic view of the universe, one that appeals to the mind, the heart, and the imagination. It is this collaborative spirit that will fuel future discoveries, inspiring generations to come to explore the endless wonders of space. In the ever-evolving field of astronomy, the combination of scientific exploration and the intricate art of storytelling has begun to shape the way the public connects with the cosmos. Interdisciplinary projects, which often blend the rigor of scientific inquiry with the depth of cultural and emotional narratives, have become essential in making complex astronomical concepts more accessible. Through these projects, science no longer stands as an isolated discipline, but is woven into the cultural fabric, creating an engaging experience that evokes emotional connections with the public. By intertwining scientific discoveries with human narratives, we not only educate, but also inspire a sense of wonder. This storytelling approach encourages people to see the universe not just as an object of study, but as something that resonates with our own human experience, full of mysteries waiting to be unraveled. Such interdisciplinary collaborations act as bridges, transforming highly abstract and technical aspects of cosmic science into captivating stories. This transformation makes these once distant concepts not only understandable, but also deeply fascinating. The beauty of this synergy lies in its ability to craft compelling narratives that stir the curiosity of individuals, making them more enthusiastic and informed. As a result, audiences become more invested in the pursuit of knowledge, eagerly diving into the complexities of space and the forces that govern it. The collaboration between scientific experts, artists, and communicators fosters an environment where the audience feels empowered, not just to learn about the cosmos, but also to grasp its profound significance in shaping our understanding of existence. Artificial intelligence, AI, and machine learning have revolutionized many industries, but their role in astronomy is nothing short of transformative. These technologies are reshaping the landscape of data analysis in astrophysics, offering tools that were once unimaginable. Historically, the process of analyzing astronomical data was a laborious, manual endeavor, requiring researchers to comb through enormous information gathered from observatories, satellites, and space missions. It was like searching for a needle in a haystack, or perhaps more fittingly, a grain of sand on a vast beach. Yet, with the rise of AI and machine learning, this process has been transformed into something much more efficient, precise, and insightful. AI excels in recognizing patterns, a skill that is invaluable when it comes to the immense data sets generated by space missions and telescopes. Imagine a researcher with a pair of eyes that can detect subtle changes in data, spotting faint signals that would otherwise go unnoticed by human observers. For instance, one of the most significant challenges in the search for exoplanets, planets that orbit stars outside of our solar system, is identifying the subtle dips in light that occur when a planet crosses in front of its star. These transit events are often incredibly faint, but AI-powered algorithms can detect these minute changes with astonishing accuracy. What once seemed like an impossible task for human astronomers has now become a matter of leveraging AI's power to identify and catalog these signals more effectively, making the discovery of exoplanets far more efficient. Moreover, machine learning goes beyond just pattern recognition. It has the ability to classify and categorize a broad range of cosmic phenomena. By training these algorithms on vast data sets that contain examples of various types of signals and noise, machine learning models can learn to distinguish between different types of cosmic events, such as supernovae, gravitational waves, or even asteroid trajectories. This capability not only accelerates the analysis process, but also enhances the accuracy with which researchers can identify events of interest. As a result, scientists are able to make more reliable predictions, issue more confident announcements, and respond more effectively to emerging discoveries in real time. One of the most significant advantages of integrating AI into astronomy is its ability to handle massive amounts of data. Modern telescopes and space observatories collect staggering quantities of information, far beyond what any single researcher or team could process in a reasonable time frame. AI systems, on the other hand, can analyze these colossal datasets in parallel, processing far more information simultaneously. This capability speeds up the research timeline, enabling scientists to test hypotheses, refine models, and confirm theories much more quickly than ever before. With this newfound efficiency, the scientific community is able to push forward with their exploration of the universe at an unprecedented pace. As AI continues to evolve and improve, its partnership with astrophysics is driving the boundaries of what we know about the cosmos. From uncovering new galaxies to investigating black holes and dark matter, the synergy between artificial intelligence and astronomy is unlocking new possibilities for discovery. The role of AI is not just a technical advancement. It represents a fundamental shift in how we approach the mysteries of space. By automating many aspects of data analysis, AI is freeing up researchers to focus on more creative and theoretical aspects of exploration, thus transforming the entire field of astronomy. In addition to its role in data analysis, AI is also becoming a critical component of spacecraft missions, where it enhances our ability to navigate, collect data, and make real-time decisions. For instance, NASA's autonomous navigation systems enable spacecraft to perform crucial tasks, such as identifying obstacles, charting courses, and making decisions based on their environment, without requiring human intervention. This ability is particularly important in space missions where real-time decision-making can mean the difference between success and failure. These autonomous systems are designed to detect hazards, optimize flight paths, and ensure spacecraft stay on track, significantly improving both the efficiency and safety of missions. Machine learning also plays a key role in robotic missions, such as the Mars rovers, where AI helps guide these vehicles across the rugged terrain of another planet. The Martian surface presents numerous challenges, from steep slopes to unpredictable weather patterns, and the rovers must constantly adjust their strategies. AI systems allow them to make decisions on the fly, such as determining the best path to take when to collect samples and how to adjust to unexpected changes in the environment. This capability allows the rovers to operate semi-independently, taking on tasks that would be difficult, if not impossible, for a human operator to manage from Earth. The role of AI and machine learning in space exploration is only going to grow in the coming years. As technology advances, so too will our ability to explore and understand the universe. The possibilities are endless, from discovering new exoplanets to deciphering the complex signals of deep space. What was once a distant dream, having machines assist in exploring the universe, is now a reality, and we are only scratching the surface of what AI can achieve in the realm of astrophysics. This collaboration between human ingenuity and artificial intelligence is pushing the boundaries of scientific knowledge and will undoubtedly lead to even greater discoveries in the future. The European Space Agency, ESA, is on the cutting edge of space exploration, integrating artificial intelligence, AI, into its Earth observation missions. By employing advanced AI algorithms, the ESA is revolutionizing how we monitor climate change and detect shifts in land use patterns. This technological leap is not merely a matter of efficiency, but is providing humanity with a much deeper understanding of global dynamics. These AI-powered systems allow for real-time analysis, enabling swift responses to changing environmental conditions and facilitating the development of effective mitigation strategies. The role of AI in space exploration has become indispensable as it empowers spacecraft and robots to take on tasks that were once deemed too complex for automated systems. By enabling these machines to analyze data more effectively and make real-time decisions, AI is opening new frontiers of discovery and providing us with insights into the universe's most profound mysteries. Artificial intelligence, in particular machine learning, is now one of the most powerful tools in the quest to unravel the complexities of the cosmos. Traditional methods of data processing simply cannot keep up with the staggering amount of astronomical data being collected. For example, consider the vastness of a library filled with millions of books. Manually reviewing each one would take an eternity. Machine learning serves as the intelligent librarian of this celestial library, sifting through mountains of data to identify subtle patterns and anomalies that might otherwise go unnoticed. These algorithms are designed to recognize the signatures of known celestial phenomena and apply this knowledge to new data sets, potentially uncovering never-before-seen objects or events in space. Astronomical data comes in various forms, from images captured by powerful telescopes to complex signals emitted by distant stars and black holes. Often these data sets are vast, and their sheer size can be overwhelming for human analysts. Machine learning algorithms excel in this environment, processing vast quantities of information at a pace and efficiency far beyond human capacity. For instance, they can detect faint signals that may indicate the presence of exoplanets, or they can identify irregular bursts of light that could signal a supernova explosion. As these algorithms are exposed to more data, they continuously improve and refine their predictions. Over time, they become more adept at recognizing previously undetected celestial phenomena, honing in on objects and events that eluded traditional analysis. It's akin to having a telescope that not only shows you distant stars, but also learns from them, gradually enhancing its ability to detect even the most obscure celestial bodies. The impact of AI on the speed of astronomical discoveries is profound. By efficiently processing extensive datasets and identifying key patterns, AI accelerates the pace at which scientists can make breakthroughs. With these advanced tools, researchers are no longer limited by the time it takes to manually sift through astronomical data. Instead, AI algorithms streamline the process, unveiling new celestial treasures hidden deep within the cosmos. This shift in how we approach space exploration could lead to the discovery of unknown planets, stars, and galaxies, expanding our understanding of the universe in ways we never thought possible. However, the integration of AI into astronomical research is not without its challenges. One of the most significant obstacles is the sheer volume of data produced by modern telescopes and space missions. This data can often be overwhelming, much like trying to pick out a single star from the endless night sky. As data scientists and astronomers work together to tackle this issue, developing algorithms that can process this vast information quickly and accurately becomes paramount. Without robust algorithms capable of handling such a colossal influx of data, valuable insights could be easily overlooked, potentially delaying scientific progress. Another major hurdle lies in the inherent complexity of the universe itself. The phenomena that occur in space range from the formation of stars to the chaotic interactions of black holes, each requiring a distinct approach for analysis. For AI systems to recognize meaningful patterns, they must be trained using high-quality, accurate data. If the data used to train these algorithms is incomplete or flawed, the AI could draw incorrect conclusions, much like trying to decipher a message with missing words. It simply would not convey the true meaning. Ensuring that AI systems are trained properly is crucial to the accuracy of the discoveries they help make. Collaboration is also a key factor in overcoming these challenges. Effective integration of AI in space research requires collaboration across multiple disciplines, from astronomy to computer science and engineering. The ability of scientists from various fields to work together harmoniously is essential for developing a shared understanding and building AI systems that align with the scientific goals of space exploration. This interdisciplinary cooperation fosters innovation and accelerates progress, as each expert brings a unique perspective and skill set to the table. Without this collective effort, the true potential of AI in astronomy would remain untapped. Ethical considerations also come into play, as AI increasingly plays a role in interpreting astronomical data. As AI systems make more discoveries, questions arise about the transparency of these automated processes. How do we distinguish between a discovery that has been verified by human researchers and one that is purely the result of AI predictions? This is a vital consideration, as the line between human analysis and machine-driven conclusions must remain clear. Transparency and accountability in the way AI is used will ensure that the discoveries made are trustworthy and scientifically valid. Moreover, the rapid pace of technological advancements poses an ongoing challenge. Just as stars in the universe can flare up unexpectedly, AI algorithms themselves are continually evolving. New models and techniques emerge constantly, making it essential for researchers to stay adaptable and well-informed in order to make the most of the best tools available. As AI evolves, so too must the way we approach its use in scientific research, as scientists work to stay ahead of the curve and fully leverage AI's capabilities. Despite these challenges, the potential for AI to revolutionize our understanding of the universe is immense. AI's ability to analyze vast amounts of data faster and more accurately than any human could is a game changer. The universe generates an unimaginable amount of information, whether it's the light from distant stars or the subtle gravitational waves caused by colliding black holes. Traditional methods of data analysis simply cannot keep up with the sheer volume of information being generated, often leaving valuable data unexplored. AI, on the other hand, can sift through these complex data sets with remarkable speed, identifying patterns and anomalies that might otherwise go unnoticed. For instance, when searching for exoplanets, AI can detect tiny variations in a star's brightness caused by a planet passing in front of it. This is a task that would take human researchers years to accomplish. But AI can process these fluctuations across thousands of stars in a fraction of the time. The result is a dramatically increased efficiency in the search for new planets, leading to the potential discovery of new worlds beyond our own solar system. In addition to searching for exoplanets, AI also plays a crucial role in simulating cosmic events. By using mathematical models based on the laws of physics, AI can predict the behavior of celestial bodies, such as how a star will evolve or what might happen during the explosion of a supernova. These simulations provide invaluable insights into the mechanics of the universe, offering a clearer understanding of how galaxies and other cosmic structures form and evolve over time. AI is also transforming how we interpret images from telescopes. With millions of images being captured daily by observatories around the world, the task of analyzing and classifying these images can be overwhelming. Advanced AI techniques can help sort through these images, identifying celestial objects and filtering out noise. This process significantly reduces the time it takes to analyze images, allowing astronomers to focus on the most promising leads and speeding up the discovery process. Furthermore, AI is enabling greater collaboration among scientists across the globe. By facilitating communication and providing common tools for data analysis, AI is breaking down barriers between disciplines and fostering a more interconnected scientific community. This increased collaboration is crucial for advancing our understanding of the universe, as it allows scientists from different backgrounds to bring their expertise together, leading to groundbreaking discoveries. As AI continues to evolve and improve, it will become an even more powerful ally in our quest to unlock the secrets of the cosmos. With its ability to process vast amounts of data, simulate complex phenomena, and assist in the interpretation of astronomical images, AI is poised to accelerate the pace of discovery. The impact of AI on space exploration will undoubtedly shape the future of our understanding of the universe, revealing hidden wonders and offering insights that could reshape how we view our place in the cosmos.